just simply has a left shift. Because in log-log plot, the droplets go from their initial diameter to the final diameter that corresponds to the fraction of volume occupied by the non-volatiles. So if the non-volatiles is 1%, the final diameter is about 22% of the initial diameter. So every diameter, every droplet reduces to 22% of its initial diameter. In terms of spectrum, it is simply a left shift. Therefore, you want log normal spectrum or Pareto distribution, whatever droplet that initially you put out simply has a left shift. But then you have to be careful that some larger droplets would have left the puff and would have fallen down to the ground. That will come as a upper droplet size cutoff. So the theory is extremely simple in that sense.
What about the former one, sir? With time?
With time, it just follows a d square. Well, it follows a modified d square law. It's not an exact d square law, because what happens is that as the droplet evaporate, more and more of the volume is really non-volatile. So the evaporation rate, even in dry weather, slows down as time goes on. It doesn't follow a very simple power law. But the thing is that if you're interested in droplets that remain airborne for a long time, it is the final spectrum that is of interest. How it is evaporating, whether it is 1 second or a second and a half, or whether the evaporation takes 3 seconds, sometimes is not that interesting or important. Because what we're really interested is, if somebody coughs, what fraction of those viral particles remain airborne, say for 5 minutes or maybe even an hour? How far can it go? For that question, all we care is what will be ultimately remaining airborne for a long time.
Okay. Thank you.
I have one question, Bala. So,
yes.
What about what are the effects of coalescence and breakups? Let's say of the droplets in this duration of the airborne.
Yeah, they may be important at the very beginning, but the volume fraction is so small that at least our simulation don't show any collision. But breakup, our assumption here is that they break up during the ejection process, and this is what people like Stefan Zaleski and other people champion, to find what the droplet breakup process, and we just simply take that broken up drop spectrum. Okay, so we don't want to simulate the breakup process, because that would require resolving individual droplets, which is just if you do that, then you just can't simulate 2 meters.
No, I was thinking of putting something, numerical parameters or something, which are associated with the droplets coalescence and breakups.
They are not important. They are not important.
Yes. Okay. So let us thank, if there are no more questions, to Professor Bala for giving this nice lectures. Thank you. Thank you very much, Professor Bala.
Thank you, Professor Balachandar, and thank you, Professor Sahu. It was a nice talk, and again we will sometime we will try to invite you to our beautiful campus. Thank you.
Yesterday we talked about it. I really missed that opportunity. I would have really liked to be there in person, not give this kind of a talk, but it's better than nothing. Thank you.
Thank you, sir. Good night.
It is nice to see you, Professor Balachandra, again.
Thank you.
Okay.
Bye.
Okay. Bye.
Good night. Good night.
Hello.
Hello.
Yeah.
Yes.
So it's Professor Sandeep Kumar Sahu, sir.
Yes,
Saha,
sir. Yes.
Yes, sir. Sir, we will start the session.
Yes, definitely.
Yeah. So
let me check.
Yeah.
Yeah.
Yes,
The
sir.
first paper ID is 110.
Hello, sir. Hello.
Yes. The
Sir,
first paper ID is 110.
yes, sir. Give me 1 minute. I'll
Yeah.
just check. Yes, check the presentation files.
Yes, yes, yes. So please check. Then I will start announcing the title.
Yes, yes, definitely, sir. Just give me 1 minute, sir.
Yes, yes, yes.
Yes, sir. We can start. We can
Yes.
definitely. Yes.
Yes.
Yeah.
The first paper is uh, is on the effect of duct location and shape of enclosure on forced convection heat transfer from fuel sub assemblies to air in a nuclear fuel storage vault. Okay, so I request the presenter, or we will start the online presentation now.
Welcome to all. I'm the research scholar at Homi Bhavan Institute, Ajika Mishra. A very warm welcome to all. I'm Vivek Kumar Mishra, research scholar at Homi Bhavan Institute, Ajika Kalpakkam. I'll be presenting my work titled Effect of Duct Location and Shape of Enclosure on Forced Convection Heat Transfer from Fuel Subassembly to Air in a Nuclear Fuel Storage Vault. My co-authors are Saroj Kumar Panda, Vishwanath Sen, MP Maya, and BPC Rao. The outline of the study are introduction, computational model, validation, results and discussion, and conclusion. Coming to introduction. Reprocessing of nuclear fuel is becoming increasingly popular in countries with limited uranium resources. The unburnt fissile material is carefully extracted from spent fuel and is enriched with fresh uranium and refabricated to fuel. This reduces the fuel wastage significantly. The fuel region has 1 meter length of fuel storage where decay heat is generated. The fuel is stored in a concrete or a metallic vault where it is cooled by forced air convection. The motivation behind this work is to maintain the temperature inside the fuel storage vault below 65 degrees Celsius in order to ensure longevity of the container. The concrete structure above 65 degrees Celsius slowly starts losing moisture and become uh, weak. So, in order to maintain the safety, uh, the cooling is necessary. The study can be helpful in identifying the hot spots where sensors can be mounted. This can further reduce the fuel storage cost. Most of the work in literature is focused on spent fuel in single enclosure. Even in multiple enclosure, the connecting region is a big cavity. In this study, we have studied different fuels like blanket subassembly, blanket magazine, fuel subassembly, and fuel magazine in different enclosure connected by a series of ducts. The primary objective of the study is to carry out numerical simulation of forced convection heat transfer inside the reprocessed storage vault of core subassembly plant. In this study, grid sensitivity analysis is done using ANSYS Fluent. The results predicted is compared with published experimental results of Wang and Chang. Different turbulent models are compared to predict the temperature accurately inside the vault. The duct location is optimized for better cooling of fuel. Effect of nozzle arrangement is studied to enhance air jet penetration. The fuel is considered to be Newtonian, incompressible and viscous. K epsilon turbulent model is used for this study. Simple scheme is used for pressure velocity coupling, and second order upwind scheme is used for discretization of mass momentum and energy conservation equation. The mass momentum and energy conservation equation are shown in the table below. The K equation and epsilon equation for turbulence model have been shown here. Now considering the boundary condition. The schematic of the storage vault is shown. The vault is divided in blanket and fuel region, storing blanket subassembly and blanket magazine, and fuel subassembly and fuel magazine. The blanket subassemblies and blanket magazines are 48 in number, whereas fuel subassemblies and fuel magazines are 96 in number. The inlets are maintained at atmospheric pressure and are connected to the blanket region. The outlets are at -10 mm of water column in fuel subassembly region. The interconnecting ducts between the two are shown in the figure. Grid independent study is carried out using coarse, medium and fine grid of size 5.2 million, 10.6 million and 13 million respectively. The comparison is made based on the temperature rise along the height of the vault. The grids around the vicinity of the subassemblies are taken fine to capture temperature and velocity gradient correctly. For validation, experimental results of Wang and Chang is taken. A cubical enclosure of side 2.44 meter is considered with inlet of 0.03 meter along the length of the cube and outlet of 0.076 meter is considered. A cube of side 1.22 meter generating 700 watt has been taken for study inside this enclosure. The temperature profile obtained along the height of the enclosure has been shown and is compared with the predicted results. The results are found to be in very good agreement with each other. A comparison of different turbulent models have been made in this study. Spart-Elmar K omega, standard K epsilon and SST K omega. It is seen that the different turbulent model predict temperature within a range of 1 degree Celsius. Among these models, standard K epsilon model converges much faster than other model, so it has been considered for further studies. Here we have analyzed the position of connecting ducts on air jet. For this, we have taken connecting duct at a height of 4 meter, 3 meter and 1.5 meter. It is seen that when the jets are connected on the top of the vault, the penetration of air jet is maximum. Whereas at the bottom, the jet penetration is low. Secondary swells are generated because of high velocity of jet at the interconnecting jet. Placement of duct at the top of the vault ensure better mixing of air. The effect of nozzles on air distribution is analyzed here. In order to increase the jet penetration, the interconnecting ducts are mounted with nozzles, which does increase the jet penetration, but because of this, the cross-sectional area of the connecting duct decreases, which reduces the flow. The rise in temperature of the fuel in fuel storage region is seen. The pressure inside the blanket and fuel region is also increases. The pressure in the blanket region goes to minus 0.1 Pascal. So in order to further improve the airflow, the edges of the connecting duct are smoothened. An increase in air exchange rate and decrease in temperature of fuel is obtained. But the pressure in the blanket region is still unsafe for operation. So in order to increase the airflow and decrease the pressure in blanket region, the number of connecting ducts between the blanket and fuel region is increased. It is seen that when the number of connecting ducts between blanket and fuel region is 8, the air exchange rate increases to 4.3 and the temperature of the fuel reduces by 10 degrees Celsius. The pressure inside the blanket region comes to minus 0.5 Pascal, which is safe for operation. The comparison of different turbulent model have shown that K epsilon model converges faster. The placement of the duct above the heat sources ensure better jet penetration and better mixing, due to which a more uniform temperature is maintained inside the vault. Cooling can be enhanced by connecting small number of small air jets instead of a large jet. It is seen that when the jet is placed below the heat source, the cooling is better compared to other cases. But swirling of air is seen because of high velocity of the jet. In references, a study of Wang and Chang on assessment of various turbulent model for transitional flow in a closed environment is selected for validation.
Okay. Thank you, Vivek, for presenting this within stipulated time. So forum is now open for question and answers. Please ask questions first. Okay. So if I hope Vivek is present here.
Yes, sir.
Yeah. So I have one question. Like you have used means you are showing that inlet boundary condition. So what boundary condition you have specified? Is a mass flow rate or a velocity or pressure?
No, sir, it's pressure, sir. At
Okay.
inlet, I have specified atmospheric pressure. At outlet, because of suction, minus 10 mm of water column pressure equal to minus 10 mm of water column is maintained, sir.
Okay. Okay. Thank
Okay,
you
sir.
very much. If there is no question, then we can move on to the next presentation. So the next presentation is, or the paper ID is 121, and the title of the paper is Role of Multiscale Roughness in Sustaining the Enhanced Heat Transport Regime for Rayleigh-Bénard Convection. So the authors are Mukesh Sharma and Arnab Kumar De.
Yes, sir. Available, sir.
Yes.
Hello, everyone. I'll be presenting my slides on the topic role of multi-scale roughness in sustaining enhanced heat transport regime for Rayleigh-Bénard convection. Just the outline. First is the introduction, followed by problem description, then results, and lastly conclusions. Introduction. Rayleigh-Bénard convection is an ideal model which is used to study thermal convection. It is a bottom-heated and top-cooled configuration where flow is unstable as denser fluid is above lighter fluid. Above a critical Rayleigh number, only convection starts. Convection takes place inside Earth's outer core, atmosphere, oceans, oceans, stars, etc. It also finds application in various engineering and industrial fields. Why we need to consider convection with rough surfaces? In nature, convection happen over rough surfaces. Hence, we need to take into account rough surfaces. Now, it is also known that rough surfaces enhance heat transfer if we choose suitable roughness symmetry. Enhanced heat transport is highly desirable for various industrial applications. Problem description. Here we have shown governing equations under Bossiness approximation for the fluid flow. First is the continuity equation. This is the continuity equation, momentum equation, and energy equation, where values of alpha u, alpha b, alpha t depends on the normalizing scales for velocity, where we have used free fall velocity scale for normalizing, the values for which can be seen in this table. Numerical details. Triangular random roughness is employed in our present setup, that is 2D rectangular box of aspect ratio 2:1, where air is taken as working fluid, and finite volume method is used with collocated arrangement of variables. Grid is structured, non-uniform in y direction, where Kolmogorov scale is resolved for spatial resolution. Rough surfaces are handled using diffuse interface immerse boundary method such that body resolution is comparable to grid. Order of time integration is second, where temporal resolution is taken in such a way that Kolmogorov time scale is resolved and Courant number is less than 0.2. Convective term in momentum equation is handled using Adams-Bashforth scheme. Diffusive and buoyancy terms are handled using Crank-Nicolson scheme. To solve set of linear algebraic equations, SIP by CG stab is used as solver. Parallelization is done using MPI libraries. Results. In this slide, we have shown instantaneous temperature contours for Rayleigh 10⁸, 10⁹, 10⁻10. It can be seen that at the lowest Rayleigh number, that is 10⁸, flow inside the cavities is viscosity dominated. Major contribution in plume emission is from taller roughness elements, but with increase in Rayleigh number, as thermal boundary layer thickness decreases, smaller roughness elements also start to protrude thermal boundary layer, and their effect is visible in terms of increased plume emission. At the highest Rayleigh number, 10⁻10, flow structures are extremely fine. Plumes are emitted not only from the tip of the roughness elements, but also from the sloping surfaces. Next, we have shown Nusselt number scaling with Rayleigh number, where using least square fitting, Nusselt number scaling is obtained as this. A scaling exponent of 0.43 indicates that enhanced heat transport regime is achieved throughout the Rayleigh regime explode. Next, we have compared Zhu et al.'s data, where they have considered multi-scale roughness of sinusoidal type. At lower Rayleigh number, our present roughness configuration gives higher values, but at higher Rayleigh number range, Nusselt number seems to become comparable. Next, decomposition of the domain into plumes and background region is carried out using criteria proposed by Imran and Schumacher. Plumes are considered to have strong correlation between vertical velocity and temperature fluctuations. When product of vertical velocity and temperature fluctuations exceed above a certain threshold of the instantaneous global max of V prime theta prime in the entire domain, a region is quantified as plume, else background region. In this figure, extracted plumes from the method is shown for 3 different Rayleigh numbers at delta equal to 5%. Here, regions in black are plumed regions, while white color region indicates background regime. The idea behind using different thresholds is to observe cutoff dependency for plumes, if there exists any. In this figure, we can see that volume fraction of plumes decreases with increase in Rayleigh number, irrespective of threshold. Whereas for background, volume fractions increases with increase in Rayleigh number. These results are in agreement with that observed by Imran and Schumacher for their study inside a cylindrical cell. Next, we have compared volume fraction of plumes and the associated thermal dissipation with smooth surfaces. It can be seen that for rough surfaces, for both 1 and 5 threshold, 1 and 5% threshold, both VPL and epsilon PL, that is volume fraction of plumes and dissipation, are higher for rough surfaces. Also, there is slower decay of volume fraction of plumes and dissipation with increasing Rayleigh number, which suggests that effect of roughness configuration is sustained even at higher Rayleigh number. Further, volume time average buoyancy production and dissipation are compared between smooth and rough surfaces. It can be seen that both buoyancy production and dissipation are higher for the rough surfaces, which implies that rough surfaces exhibit higher turbulent heat flux and dissipation rates, which are signs of higher plume emission frequency in rough surfaces. Conclusion. Multi-scale roughness has enabled us to sustain local half scaling for the explored Rayleigh range. Small-scale roughness elements were found to play an important role in sustaining enhanced heat transfer at higher Rayleigh number. Also, we have observed that nearly all roughness elements contribute in plume emission at the highest Rayleigh number, that is Rayleigh tens per 10. And we have shown the enhancement of plume emission in rough surfaces from instantaneous temperature contours, volume fraction of plumes, turbulent buoyancy production, and dissipation. Thank you.
Hello, everyone.
Yeah. So thank you for the presentation. Now you can ask questions to the presenter. Okay. If nobody is asking question, I have one question.
Yes, sir.
So that how did you create that nanostructure or roughness,
That
microstructure, say? Yeah.
So these roughness structures we have for these creating these roughness structures we have used subroutines that are available in Fortran 90 platform. We have these subroutines random seed and random number. To create a roughness element, we have used a particular a random number for both wavelength and amplitude, that is width and height, and that is carried out for all the elements of for the particular surface, whether it is top or bottom. By that means we have created these rough surfaces for top and bottom plates.
Achha, the one thing I didn't understand little bit, that you have to mesh it, that the roughness basically, correct? So yes, how did you mesh? That I didn't get.
Sir, this is handled using diffuse interface immersed boundary method, sir. Okay. Sir, in this in this method, this solution is solved for a whole domain. It is solved for this rough body also, but it is taken care by using this volume fraction concept.
Okay, volume fraction means, are you going to porosity, something like that?
No, sir, not porosity, but it means a single momentum equation is solved, where this contribution of this this whole domain is solved for these governing equations, but okay, this the effect of this roughness is taken into account while we are using volume fraction. That is,
okay,
for regions where outside these rough surfaces, we will have volume fraction that is 0, and for this thing for body
One.
it will be 1, so it will get cancelled out when we are solving this effect.
Okay. So, but you don't need to measure that roughness. I'm just asking.
Sir,
No.
grid is created for the whole domain.
Okay.
But while solving, it is taken care by this procedure, diffuse interface immerse boundary method. This roughness is taken care.
Okay. Thank you very much. Okay. So yeah. So all the best. So next presentation, the paper ID is 172. The title is LES and DNS of symmetrically roughened turbulent channel flows. Authors are Harish Bharma, Karthikeyan Jagadishan, Bhagesh D. Narasimhamurthy, Amit P. Kesarkar. So the presentation will be made by, I believe, Harish Bharma. So please start.
Hello everyone. My topic of presentation is LES and DNS of symmetrically roughened turbulent channel flows. In this study, turbulent flow in a channel roughened with square ribs is simulated using LES and DNS. The square ribs are of height 0.1 h, where h is the half height of the channel, and are placed at constant pitch width lambda, which is equal to 0.8 h. This simulation is carried out at two Reynolds numbers, Re tau 180 and Re tau 400, where Re tau is basically Reynolds number based on channel half height and friction velocity. The domain length for Re tau 180 is 12.8 h in streamwise direction, 6.4 h in span, and 2 h in wall normal direction. In case of Re tau 400, the streamwise direction length is reduced to half, 6.4 h. LES exclusively resolves the large scales of motion, while the effects of subgrid scale motions are modeled. In order to separate the large scales of motions of the flow, a filtering operation is done. In this study, a box filter is used where the filter dimension is equal to that of the grid spacing. This is the governing equation of the filtered fields, where the dynamic Smagoronsky model is used to model the subgrid scale stresses. And for the DNS, three-dimensional instantaneous equations for incompressible flow are solved. A parallelized finite volume solver, MGLED, is used to solve the discretized form of governing equations. A second-order central differencing scheme is used for solving convective and diffusive fluxes. Adam-Bashforth method is used for forward time integration. Coming to boundary conditions, periodic boundary conditions are used in streamwise and spanwise directions, while on all the solid surfaces, no slip boundary condition is used. A uniform staggered grid arrangement is used in spanwise and streamwise direction, while in wall normal direction, the grids are stretched towards the wall, basically having a high resolution in the near wall region. In order to arrive at an optimized usage of total mesh points, a grid convergence study is performed using 7 different grids for Re tau 180 case, while 4 different grids for Re tau 400 case. These grids are different in terms of size and distribution. Error involved in an LES is a sum of discretization error and subgrid scale modeling error. This total LES error, ideally it reduces with increase in resolution. But in some cases, based on the domain used, this discretization error and the modeling error can nullify each other, causing a coarse grid to perform better than a finer grid. In order to judge these grids, an index defined by Selig et al. Is used, which is based on turbulent kinetic energy. Here KRES refers to resolved turbulent kinetic energy from LES, while KDNS is from DNS simulation. The profiles of this index of quality is depicted here. Here, this is for the Re tau 180 case. The grid 7, which is the finest of all those 7 grids, is observed to be performing better than other grids, while grid 1, which is the coarsest grid in the Re tau 400 case, is observed to be performing better than other grids. These are the mean streamlines extracted from LES and DNS of rough channel flow at R rate of 180 and 400. With increase in the Reynolds number from 180 to 400, a new secondary vertex is observed to develop in the downstream side of the rib, while the saddle point, which is farther away from the wall in case of 180, is observed to move closer to the wall in case of 400. Comparing the LES and DNS, the statistics from the LES datasets are in good agreement with that of DNS. The flow resistance in a rough channel flow is a combined effect of form drag and skin friction. The local skin friction coefficient can be calculated as a function of wall shear stress and centerline velocity. The wall shear stress varying over pitch is evaluated at cells adjacent to the wall. The pitch average skin friction coefficient is depicted along the length of the pitch. The negative values here indicate the recirculation zone in the bottom of the cavity. On the other hand, the form drag is caused due to the pressure difference between the front and rear sides of the rib. The coefficient of form drag can be evaluated in this way. Average values of coefficient of skin friction and form drag are depicted in this table. So it is evident from this that the form drag is dominant one, differing by 2 orders of magnitude when compared to the skin friction. And a moderate increase in the skin friction coefficient is observed on increasing the Reynolds number from 180 to 400. The vertex structures are plotted based on the definition given by Jeong and Hussein, according to which the vertex surface can be identified with second eigenvalue of velocity gradient tensor. So what we see here are the isosurfaces of lambda 2, and they are colored with Z plus, that is the height above the wall in wall normal coordinates. In case of R rate of 180, it is found that most of the structures are found within the roughness sublayer, and the structures very close to the wall are aligned in span-wise direction, while the structures away from the wall are aligned in stream-wise direction. Even in R rate of 400 case, the vertex structures in the near wall region, considerably within the rib height, are aligned in span-wise direction, whereas majority of the structures over the rib are aligned in stream-wise direction. Due to the coarse grid used in LES, it could moderately capture the vertical structures in R rate of 180, but in case of R rate of 400, it failed. In order to highlight the anisotropic effects of surface roughness and its dependency on the Reynolds number, the anisotropy tensor is examined. The Reynolds stress anisotropy tensor, based on single point correlations, is defined by this equation. The variation of significant components of this tensor across the one half of the channel are presented in the figure for R rate of 180 and R rate of 400. Here, in order to highlight the roughness effects, the results from the DNS of rough channel at R rate of 180 and 400 are compared respectively with the results from DNS of smooth channel at R rate of 180 and 395, where the smooth channel results are from Abe et al. In smooth channel flow, the streamless component of turbulence is observed to be the most dominant one in both R rate of 180 and 400 cases, while the other two components B22 and B33 are negligible. This shows the anisotropic nature of the smooth channel flow. In comparison to this, the rough channel flow is more isotropic in nature. In both cases of R rate of 180 and 400, the profiles of rough channel flow coincide with that of smooth channel flow at a region above the roughness. This supports the Townsend hypothesis, which basically says the statistics beyond the height of roughness sublayer will be similar for the same Reynolds number flows irrespective of the shape of the wall roughness. As per Lumley and Newman, any Reynolds stress that can occur in a turbulent flow will correspond to a point within this so-called Lumley triangle. A location of this point in this triangle indicate the shape of the Reynolds stress tensor. The values of gamma and eta at any point in a turbulent flow can be determined from their corresponding Reynolds stresses, and the result can be plotted in the gamma eta plane. The diagonal boundaries of this triangle indicate axisymmetric limits of the turbulence. With gamma less than 0 indicate an oblate spheroid shape of the Reynolds stress tensor, while the boundary with gamma greater than 0 indicate a cigar-shaped Reynolds stress tensor. The top curved boundary indicate an elliptical disc-like shaped Reynolds stress tensor, while the origin indicate an isotropic limit, which indicate an spear-shaped Reynolds stress tensor. The points marked in the figure correspond to the pitch average Reynolds stress profiles in the mid-cavity region. The size of the marker is made inversely proportional so that the points corresponding to the near wall region are marked with larger size, while away from the wall are marked with smaller size. As observed in the figure, both smooth channel and rough channel flows, the distribution of data points away from the wall are more skewed towards the right linear boundary, indicating an axisymmetric state of the turbulence. This implies that the streamwise component of the anisotropy tensor prevails over the spanwise and wall normal components, which are nearly equal in magnitude. The points from the channel centerline approach the isotropic corner of the plot. In the case of smooth channel flow, the near wall points are in the two-component state. This is because due to the presence of the wall normal component of Reynolds stress vanishes very close to the wall, while the streamwise component dominates the spanwise one. It is important to note that this elliptical disc-like shape is that of the stress tensor, which is actually caused due to the rod-like shaped eddy turbulence in the flow as a result of vertex touching in the near wall region. In case of smooth channel flows, the variation of anisotropy is monotonic in the near wall region for both Areto 180 and Areto 400, while in case of rough channel flows, an abrupt change is evident around the half height of the rib, where gamma is changing from negative to positive. So this is the case for both 180 and 400. With increase in Reynolds number, not much change is seen in the smooth channel anisotropic behavior, while in case of rough channel flow, a significant variation is seen, especially in the near wall region. This table depicts the computational cost of various simulations done in this study. The simulations are performed in different processors and whose specifications are listed here. To conclude, LES is able to capture the statistical features of the flow with a grid size which is less than 1/5 of the size of the grid used for DNS. This is for the both Areto 180 and 400 cases. The distribution of three-dimensional instantaneous vertical structures represented using lambda 2, they have exhibited as streamwise oriented structures above the rib height, while they are spanwise oriented within the rib height. It is observed that the roughness causes more isotropy to the flow in comparison to the smooth channel flow, where the flow turbulence is majorly dominated by the streamwise Reynolds stress component. Increase in Areto of rough channel flow has caused more isotropy to the flow in the near wall region, while there is no significant variation in the region away from the walls. These are the articles referred in this study.
Okay, thank you for the presentation. Now you can ask questions. Okay, if nobody is asking question, I have one question like, I didn't see any validation. So is there any validation done in this work?
Sir, the RE400 rough case is actually a published study.
Okay.
Yes, sir.
Published study means by some other group.
Yeah, yes, sir.
So you have compared
the DNS. We have compared all the LES results with the DNS, and that one of the DNS is a published study.
Okay. So how much difference you got between that result and your result?
Sir, very it's almost insignificant. We have compared the RMS of fluctuations also. So yeah, it's very acceptable.
Okay.
Hello, am I audible?
Yes, sir.
Yes. You can ask.
Yeah, I have just one query. You showed in one of the slides the number of samples are 400. I didn't understand that. What is that number? 400 number of samples?
Samples. You mean the number of samples collected to average for the statistics?
Is it spatial sample or temporal sample?
No, they are temporal samples. So the samples are collected at an interval of eddy turnover time scale. So basically we are averaging the statistically uncorrelated data. So we average for a very long time and then work with those statistics.
But is it not true that 400 number of spatial temporal samples are too low for any converged statistic?
Actually, these the low you can decide whether they are low or high when you see that these statistics are not changing beyond certain time. So what we do is we collect the statistics for some number of samples, and then again collect the statistics for another number of samples, and then compare. If you still see there is a difference between these statistical results, then you should be running the simulation for more longer time. And if these statistical results are matching no matter how many times you collect the samples, then it means that it is fully developed, and you'll not see a furthermore change in the simulation. I mean, in terms of statistics. So that's what we call fully developed flow.
While checking, which order statistics you checked? Second order, first order, second order, third order, which one?
We went up to second order.
Second order statistics. Okay, thank you.
Yes, sir.
Okay, thank you for this presentation. So we will move on to the next presentation. So next presentation is laminar to chaotic transitions for flow through a pipe with twisted tape insert. The authors are Parag Chaware and CM Sevatkar. Paper ID is 174.
I am there, sir. I am there.
To the next page. Page
Then
number 49.
so Parag Chowdhury is also there.
Date.
Yes, sir. Good morning. The topic of our presentation is laminar to chaotic transitions for flow through a pipe with twisted tape insert. This is the outline of our presentation. Twisted tape are heat transfer augmentation device. Those are used to enhance the heat transfer in heat exchanger. There are many passive heat transfer augmentation devices available, but twisted tape is the most popular amongst that because of its cost, its less maintenance and compactness. It can be easily retrofitted into the heat exchanger. Twisted tape imparts the swirl to the flow that increases the turbulence, and turbulence disturbs the boundary layer and you get the more heat transfer. Twisted tape is being investigated by many investigators since 1950s. Most of the investigations are in experimental form. Some simulation data is also available. The results reported are mostly in form of Nusselt number as a function of Reynolds number, Prandtl number, and a twist ratio. Manglik and Burglas has made a significant contribution in the area, and they have shown that twisted tape shows better performance in the laminar regime than in the turbulent regime. However, although the twisted tape is studied widely, there is a little information available about flow transition in presence of twisted tape from laminar to turbulent. Most of the researchers have assumed the critical Reynolds number as a 2000 or 2300 for in presence of twisted tape, which is same for the smooth tube. So, considering the literature, the objectives of our present study are to understand the flow transitions on the way from laminar to chaotic, to investigate the route to chaos in the flow, to investigate the flow reversal phenomena occurring in the way to chaos, and to analyze the flow physics and causes of. The transitions are studied using LES, that is large eddy simulation technique. The subcritical stresses are modeled using the well model, that is wall adapting local eddy viscosity, SGS model. Finite volume method is used for domain discretization. The simulations are carried out using ANSYS 17. Bounded central differentiation schemes is employed for handling convective terms. Second order schemes with simple algorithm are used for pressure correction, and transient formulation is handled with bounded second order implicit scheme. This is the grid that we have used for our simulation. We have used a hybrid grid. The structured grid is used at the pipe wall and tape surfaces to capture the boundary layer, and unstructured grid is used in the core. These are the boundary condition. At the tape and tube wall, we have used Nozzle boundary condition. At the inlet, we have used the velocity boundary condition. And at the outlet, we have used pressure outlet boundary condition. At the inlet, we have given a fully developed velocity profile so as the flow should be fully developed from the start of the pipe. The physical properties of the fluid and flow and the flow are considered to be constant, and fluid and flow are considered to be incompressible. About the grid resolution study, uh, grid resolution study in case of large eddy simulation is done by using Lessig technique. That Lessig technique gives you the result how much flow is resolved and how much flow is modeled. So we have carried out Lessig index for all our simulation. The Lessig index for all our simulations was more than 0.85. That shows that 85% flow is resolved and only 15% is modeled. The maximum y plus value in case of our simulation is 0.6. The non-dimensional grid spacing in streamwise and spanwise direction is also checked. The results obtained through simulations are validated with the available literature results by Agarwal and Rajarao and Manglik and Verglas. It has been observed that the simulation result shows very good agreement with the available literature results. So comparison is shown in the diagram. To understand the transition in presence of twisted tape, we have used the velocity profile, the power spectral diagram, and the phase portrait. We have observed that the flow is typically laminar up to Reynolds number 700. From 700 onwards, a little periodicity is found in the flow, and at 1000 Reynolds number, the flow is observed to be periodic with single fundamental frequency. At 1100 Reynolds number, the flow is also observed to be with single frequency, but one harmonic. As we increase the Reynolds number, at 1150 Reynolds number, the flow is turning into quasi-periodic, means we get two fundamental frequencies. Those are incommensurate in nature. So at 1150, we have observed that the flow is quasi-periodic. When we further increase the Reynolds number, the quasi-periodicity continues till Reynolds number 1300. At 1300 Reynolds number, we got three frequencies, fundamental frequencies, F1, F2, and F3. And those three fundamental frequencies are incommensurate in nature. Here, the velocity profile for 1250 and 1400 Reynolds number is shown. We can see the flow is periodic at 1250 and it's chaotic with four fundamental frequencies at Reynolds number 1400. The phase portraits also suggest the same. We have observed very interesting phenomena when we increase the Reynolds number beyond 1400. When we increase the Reynolds number beyond 1400, instead of flow remains chaotic, the phase portrait observed to be contracting and flow turning into quasi-periodic at Reynolds number 1500. And we increase, and after increasing the Reynolds number from 1500, at 1700, the flow is turning into periodic again. So the phase portrait goes on shrinking, and at 1700 it converts into limit cycle. So at 1400 the flow was chaotic, at 1500 it becomes quasi-periodic, and at 1700 it becomes chaotic. So the flow from chaotic, the flow again turning into periodic flow. When we increase the further Reynolds number, the periodicity continues till Reynolds number 1900. However, the phase portrait goes on expanding, but the frequency remains a single fundamental frequency. At Reynolds number 2000, the flow suddenly becomes chaotic with large number of frequencies. The phase fault rate also suggests or shows the chaotic nature of flow. So thus from 1700 the flow remains periodic till 1900, and at 2000 the flow suddenly becomes chaotic without going into quasi periodicity again. So these are the results from our simulation. The flow is quasi-periodic up to Reynolds number 1250. The flow is chaotic at 1300. Phase space goes on shrinking and it regains the quasi-periodicity at 1500, and flow is found to be periodic at 1700. So the one possible reason for turning the flow into periodic again could be the Coriolis forces. Those are produced the normal pressure gradients proportional to the rotating speed. These pressure gradients has got stabilizing effects. So fluid particles which is moving outwards in with the Coriolis force is forced back by the inward pressure gradient in the flow being larger than the Coriolis force acting on the fluid particle. So the instabilities in the flow are suppressed and turning the flow into periodic again. The periodic behavior of the flow is continuous till Reynolds number 1900. At 1900 Reynolds number or beyond Reynolds number 1900, the inertial forces overpower the stabilizing forces and flow becomes chaotic. So no quasi-periodic nature is observed here during the transition from periodic to chaotic after Reynolds number 1700. So coming to the conclusion, the flow in presence of twisted tape is studied numerically using LES technique. The flow is quasi-periodic with two incommensurate fundamental frequencies with F1 and F2 at Reynolds number 1250. The flow converts to chaotic with additional incommensurate fundamental frequency F3 at Reynolds number 1300. At Reynolds number 1500, flow enters into quasi-periodic regime again. The flow regains periodicity at Reynolds number 1700, and flow adopts the chaotic nature at Reynolds number 2000 without going through quasi-periodicity route again. Although we have studied these transitions, more investigations are required to be carried out to understand the heat transfer process when the flow is going through transitions. More qualitative and quantitative investigations are required to understand the transition physics. So the investigations are going on. These are the references that we have cited during our studies. Thank you for your attention.
Thank you for this presentation. Now you can ask questions.
Nirva, have you done the homework? Yes, ma'am.
Okay, so my one question is that means you are stating some explanations, okay, or giving some explanations.
Yes, Nirva, have you done your homework? Yes.
Quasi-periodic, correct? So my question is that have you checked the explanation means by plotting the forces and plotting this pressure gradients?
Yes, sir. We have plotted the pressure gradients, and these pressure gradients are found to be are more on the inner side and or they are more at the center of the pipe than, and they are very lesser at the outer side, and the pressure gradients are varying as we changing the Reynolds number.
Okay. Another thing, when you do the validation, so what is the range of Reynolds number you have validated, over which you have validated your model?
We have checked for friction factor, sir.
No, but what is the range of Reynolds number you have checked?
We have validated over the entire range.
Yes.
From 100 to 2000.
Okay.
Whatever is available in the literature given by Manglik and Bargul especially.
Yes, yes.
That has been done.
Okay.
Homework for number 11.
Then we can move on to the next presentation.
Thank you.
presentation is the paper ID is 175. The paper title is Fingering Instability with Sphere on Flat Geometry in a Lifted Helisaw Cell. Okay, this is done by, this presentation will be done by Uddipta Singha and Prasanna S. Gandhi. So we can start now.
Hello everyone, I am Udipta Singha and the title of our paper is Fingering Instability with Sphere on Flat Geometry in a Lifted Helisaw Cell. This is the viscous fingering phenomenon, also called the Safman-Taylor instability, which is seen on the interface dividing two fluids which are confined in very thin spaces or porous media. The necessary condition is that the higher viscosity fluid is being pushed against by the lower viscosity fluid. This can be seen in other geometries called the radial Helisaw cells, where typically air is used as the lower viscosity fluid and it is pushed against high viscosity fluid already occupying the Helisaw cell. Another variant of the Helisaw cell is the lifted Helisaw cell, where the plates confining a liquid film are separated from each other, and as they are separated, the surrounding low viscosity fluid, which is air, invades the liquid domain and destabilizes the interface. In existing literature, the Safman-Taylor instability in the lifted Helisaw cell is well described. Typically, the gap between the two plates in a Helisaw cell is kept constant. However, there are many works which describe a gap variation in the Helisaw cell. Such gap variations are limited to only straight taper and also only linear Helisaw cells and injected radial Helisaw cells are described. There are not many experimental works and only theoretical analyses are shown. Therefore, there is a gap in the research which motivates us to find the fingering phenomenon in a smoothly increasing gap variation by use of a spherical plate. We are also motivated by the fact that such a configuration aids in robust and repeatable flows of low viscosity fluids, for example, biological liquids. It is expected that this radially increasing cell gap will stabilize the system and suppress viscous fingering. We begin with a linear stability analysis. Here, the Navier-Stokes equations in cylindrical coordinates are integrated over the varying cell gap, and a pressure Poisson equation is obtained. The pressure and perturbation parts and solve for separately by the two boundary conditions shown here. The kinematic boundary condition gives an expression for the rate of change of the interfacial deformations, that is the radius of the outer interface, and in this way we define the growth rate of instability as shown here. Following the linear stability analysis, we arrive at the stability criterion for our sphere on flat linear lifted Helisaw cell configuration, where the key dimensionless parameters that are controlling our system are found. The three parameters are the capillary number, which can be controlled by controlling the plate separation velocity, the aspect ratio, which can be controlled by controlling the dimensions of the liquid film at the start of plate separation, and the dimensionless curvature of our spherical plate. Thus, the growth rate is found over all wave modes. The expression holds good in the limit of the flat plate, where we can imagine a flat plate to be a spherical plate of infinite curvature. Perform experiments to study the qualitative effects of the three controlling parameters of our system using Newtonian liquid, that is silicon oil. In our experimental setup, we have kept the top plate fixed and the bottom plate is mounted on a movable lab jack. that is driven by a stepper motor. The bottom plate is mounted on a ball and socket joint to maintain parallelity with the horizontal plane, and an encoder is used to track the motion of the bottom plate. In our experiments, we try to identify two regimes, that is the stable regime and the unstable regime. In the unstable regime, we see fingers appearing on the interface. Initially, the number of fingers is very large in the fingering regime, and gradually they collapse into each other and diminish as the plates are separated. In the stable regime, there is no fingering from the start of separation, and thus a smooth circular interface is obtained. Our aim is to characterize the system and find out parameters for which the system may either exhibit the stable behavior or the unstable behavior. In this plot, we have shown the capillary number versus aspect ratio. This curve is
Hello.
yes.
Means the presentation is suddenly stopped.
The video has been paused from the organizer's end, I guess.
Okay. So organizer, please check whether it is running or not, this presentation. Can you please check because yeah, okay, voice is not coming, that means.
The voices, is there any problem with the playing? I can.
You can start actually.
Yeah.
To make up the thing.
So yeah. So in the last, yeah, so it is visible that.
Yeah. You please start from this slide. Okay. Just quickly.
So it is visible that in the last slide we showed the experimental results for silicon oil, where we divided the parameter space of capillary number and aspect ratio into two parts, into the stable regime and the unstable regime. And in this plot, we show the results obtained from the linear stability analysis. On the left side plot, we have the three parameters: capillary number, delta, the aspect ratio, and beta, the dimensionless curvature of our spherical plate. So all three parameters are independently controlling the stability of the interface during lifting in our helicocell setup. On the right side, we have validated the number of fingers appearing and diminishing over time on the outer interface as the plates are separated. The theoretical curve here is obtained from the wave number corresponding to the maximum growth from the linear theory. So we see that there is a decent match, although it can be expected that due to nonlinearity, much departure was expected, but the match here is quite decent. In the Next slide. So, and continue and conclude the next slide is the conclusion curve. So yeah, so we have
Hello.
Yeah. You can little bit
So,
move forward.
so if the presenter has the slides in his mobile or laptop, then he can also show it.
so that is not possible at this time, but yeah, so I can just conclude this is just the conclusion slide. So
Yeah, you carry on. You give the conclusion. You make the conclusion. Udipta, you please.
Being constantly muted. The effect of the three control parameters were also experimentally verified and shown by linear theory, and there is a good match between the experimental and theoretical predicted number of fingers. Now, the key result in our paper is the stability map, which will be useful for finding the parameters when we are using our system to produce stable or unstable interfaces as required by different applications. So in particular, we are pursuing an application where biological liquids like blood having low viscosity are being manipulated in our geometry and for different applications. In our system, performing robust experiments is very easy with good repeatability. Thank you.
Okay, thank you very much for the presentation. So if anybody has question, please ask him. Okay, I have one question like that how you analyze or how you do the stability analysis?
In the theoretical part, we start with the lubrication momentum and continuity equations following the lubrication approach because it is a thin film of liquid.
Yes.
And then we perturb the pressure around the base value. These small disturbances are expressed in terms of the growth rate, and then if the growth rate is greater than 0, we say that the system is unstable, and if it is less than 0, it is stable.
Okay.
And experimentally, it can be directly observed.
Okay. So there is some region where some mismatch is there with your experiment and your theory.
Yes.
So but apart from that, matching is good. So what is the region at that means you are saying instability means there in that region the instability is very high in that way.
Yes. So the linear theory assumes a very small disturbance at the onset of the instability. So it is expected that there will be departure
as the time progresses. But this criterion that we have set is the wave number corresponding to maximum growth. There is even better match that we have not reported here when the criterion is set to the growth rate associated with the maximum amplitude of the fingering.
Okay. Okay. Thank you very much for your presentation.
Thank you, and I apologize to all for whatever hitch was there. Thank you.
Thank you. Not a problem. Thank you. So then we will move on to the next presentation. The paper ID is 182. The paper title is Stability Analysis of Pressure Drop Oscillations in Two-Phase Flow System. And the authors are Alok Kumar and Sunit Singh. So,
yes, sir, I am present here. Alok Kumar.
Yeah, so Alok will present the presentation.
Yes.
Well, no voice is coming.
Again, sir, there is voice problem, I think.
So the problem is with the video, or it is with the system?
Sir, I think the problem is there with the video itself.
Okay. So then, Alok, you can you, is it possible to share your screen and present quickly?
Yes, sir. Sir, I have a recorded video of the same, and that is also audio enabled. So I think I should play that.
So is it possible that organizer, is it possible to give to play the video from his end?
Yes, sir. Yes, sir. It is possible.
Yeah. Please
start
from your side. So I request other presenter also keep handy of their presentations. So in case some glitches is there, then we can actually play from their end.
Oh, sorry. Sir, I think it will not be because it is showing that there is no shareable video there.
Okay, sir. In that case, we'll play the video.
Okay. And then you talk.
Sir, but the audio was there in the video, I think.
Yes, audio is there, but there is some disturbance kind of.
So can you little bit restart the thing? Is
Sure,
it possible?
Sure.
Yes, so please start with the first slide.
No, means start with the system in the sense that maybe this MS or team, whatever, maybe there is some problem.
I think there is problem in the recording only, sir.
Oh.
We'll play the video, sir.
Okay, you play the video, then Alok, you please give presentation, okay?
Okay, sir. Okay. So from here I will start only. So the title of the current work is actually Stability Analysis of Pressure Drop Oscillations in Two-Phase Flow System. So I will first talk about the stability analysis. So stability analysis is actually nothing but the study of temporal or spatial behavior of a system. When we give the perturbation to the system, if the system comes back to its normal operating conditions, then we say that the system is stable. That we can also see from the figure below that we have a parabolic dynamics and we have the system at the red ball. If we are giving a perturbation to the red ball, so the system will initially oscillate and then it will come to its normal operating conditions, and so we will say that this system is stable. On the other hand, if it's not coming back, it goes away and settles to some other operating conditions, then we say that the system is unstable, and also that we can see from the given figure. Yeah, so the question arises that how can we show that in the mathematical thing. So we know that all the dynamical systems are represented by either PDOs or ODEs. So suppose we have a system of equation that is representing our physical system, that is dx by dt is equal to some function of x comma p, where x is the position vector and p is the parameter vector. So suppose we are introducing a perturbation of delta x to the system. So we are giving that perturbation into the equilibrium point. Suppose we have a equilibrium point of x naught. So what will happen? We will introduce into the equation 2, and if we are expanding it by the Taylor series expansion, so we will have the equation 3, where f of x naught comma p are will vanish because it is the equilibrium point, so it will vanish the function. And also for sake of the linear stability analysis, we are neglecting the higher order terms. So we have got with the equation 4, which is actually the change in the perturbation is actually the Jacobian matrix into the delta x, and Jacobian matrix is nothing with the matrix of first order derivatives of the system of equations. So now all the stability analysis will only depend on the eigenvalues of Jacobian matrix. So eigenvalues are nothing but the roots of the characteristic equation of this Jacobian matrix. So if the real part of these eigenvalues will be negative, that we have already seen in the previous presentation, that if the eigenvalues, real part of the eigenvalues will be negative, then we will say that the system is stable, otherwise it is unstable. So next slide please. So yes, so here we will explain the second term of the title, that what is pressure drop oscillations. So suppose we have a system which is given in the below figure. We have a text section, we have a supply tank, and we have a surge tank which is giving the required compressor volume. So to have pressure drop oscillations in a system, we need to have a surge tank to provide a compressor volume. It could be a system inherent compressor volume, or we can provide like which we have given here. So the system will operate at the operating points where the characteristic equations will intersect each other. So the characteristic equations or characteristic figures are given into the figure above. So we have a n shape curve and the q1 and q2. So q1 is nothing but with the pressure drop versus flow rate curve of the this pump, which we have the driving force, which is the external component, and the n shape curve is nothing but the pressure drop versus mass flow rate curve of the test section. So wherever these two curves will intersect, we will operate the system on over there. So we can clearly see from the n shape curve, because it has two positive slope regions and one negative slope region. So these two positive slope regions are actually the single phase regions. On the extreme right, we have positive slope region from point C to point B. That is actually for single phase liquid region, because if the flow rate will be very high, so for the given constant heat flux to the fluid, the system will actually be not vaporized much, so it will be in single phase liquid region. On the on the left point from A to D or D to A, it will be in completely vapor region. But into the negative slope region, that is from A to C, the fluid will be in two phase region. So that is the area of interest where we want to work on, and we have taken the condition. Suppose we are operating into the two phase region, and the pump is in the negative, that is given by pump characteristic is given by point q1. Now if I am giving a perturbation at point where these two curves are intersecting, then the question arises, what will happen in that case. So that is the major question which we want to introduce into the current study. Yes, next slide please. Yes, so now I will introduce one more term, that is Hooke bifurcation. So usually that this drastic change in the dynamics is studied by bifurcation analysis in mathematics, and one particular bifurcation which has been used in current study is Hove bifurcation. So Hove bifurcation is the bifurcation which occurs only at those points where we have the real part of eigenvalue is equal to 0. So suppose we have eigenvalue x plus iy and x is equal to 0. That means iy is corresponding to the eigenvalue, and either it could be negative or positive. So depending on the nature of this sign, we will analyze that the oscillations are growing or they are decaying. So here in this current study, we will see that whether we are getting the Hove bifurcation, and also depending on the time period and the frequency of the oscillations, we will match that whether these oscillations are matching with that of the given experimental oscillations. If they are matching, then we will say that this Hove bifurcation is corresponding to the that pressure of oscillations which are given into the system, the theoretical work. Next slide, please. So here we have the system. The system has been taken from the given S-Kakak reference. So we have two system applications. One is for the surge tank pressure, and the second is for the flow rate into the surge tank. Here delta P is a function of M, is given the internal characteristic which we have already talked, that it will be of N shape, and it will give the required dynamics because the pump characteristic will not change. It will the internal characteristic will change, so the intersecting point will also change, and depending on that we will see that what is happening to the dynamics. Yes. So we have taken experimental data and we have interpolated delta P as a function of M, and we have taken to fit more. So we have taken the fourth order polynomial. So that is given here. We will also non-dimensionalize it later. First, yes, please. Please change the slide. Yes. So here is the final non-dimensionalized system of equation. We have done non-dimensionalization about the steady state points which are given into the given reference. Here we are having delta P as a function of M and M plus delta M. So that will also give some insight about the general conclusion that what is happening if we are moving around the given equilibrium points. If it is more than that, what will happen? Otherwise, what will happen? Yes, so please. So what we have done that this work was already done in theoretical. This work was done already in analytical way using some software. So what we have done here, because the system of equations is very small, so we can also do it by pen and paper. So we have done it. We have written the Jacobian matrix, and we have written all the root analysis, and we have written the inequalities, and we saw that whether these are also matching. So Jacobian matrix is given by equation 6. Then we use the root analysis, and we have got to the final inequality, which is equation 9. And now we will put the equilibrium mass flow rate capital M into this inequality, and then we will say that whether the delta P which we have obtained from the polynomial is it matching with that or not. Yes. So these are the results which we have got. We have got two Hove bifurcation points, which means that into the negative slope region we have two extreme points, one for the negative single phase liquid region, one for the single phase vapor region. So on those two extreme points, if the external characteristic curve will move, then at that point the Hove bifurcation will occur. That means that on the right hand of the internal characteristic, these two extreme points, on the extreme sides we will have a stable region, and between them the negative slope region will be unstable. And also with the eigenvalue analysis, we can see clearly that the position of Hove bifurcations are exactly matching with the point where this figure 6 is intersecting the point 0, the line 0. So the region between the Hove bifurcations is showing the positive real parts of the eigenvalues. That means that the region is unstable, and on the extreme sides we are seeing that the eigenvalue is negative. That means the system is stable in these points, in those points. Yes, next slide. Yes, so from there we can conclude that stability analysis of the existing model demarcates between the stable and unstable regions, obtaining to the Hopf bifurcation, and also the eigenvalue analysis is exactly matching with what we have got from the Hopf bifurcation, and also it is showing that the system is stable on the both sides where we have positive slope region, and it is unstable on the between the middle side where we have the negative slope region, and the conjugative occurrence of Hopf bifurcation shows the unstable nature of the negative slope region of the internal characteristic curve. And also we have got the conclusion that periods occur in the region corresponding to non-negative eigenvalues. Thank you.
So thank you for this presentation. Thank you for the nice makeup. So you can say, if anybody can ask questions, please ask.
Yeah. So how we did this bifurcation analysis mathematically for this work?
Okay, so we have a package called MetCont in MATLAB. So we have used that.
So it's a software, right? MetCont.
Yes, yes.
Or package.
Software actually.
So you write code there.
We gave the system parameters. We gave all the equations, and then we do the one-dimensional analysis.
So it automatically calculates this bifurcation value. I mean.
Yeah, but we have to give the initial conditions by on or, and then it will give that whether at the point it will actually give the stability boundary, and those points where this stability boundary will demarcate, it will show the point that whether it is going in which direction. So then we can guess, or then there are other tools which we use, that there is Hopf or any other bifurcation there is.
Okay, fine.
Okay, thank you. If there is no more question, we will move on to the next presentation.
Okay, thank you, sir. I'm sorry for this thing. The video was enabled actually with the audio. I don't know how it is happening. Okay, sorry.
It's okay. So you have done finally. Anyway, so
Okay.
Next presentation. The paper ID is 183. The authors are Narsingh Jha and Victor Steinberg. And the title of the paper is Elastic Instability in Straight Channel with Viscoelastic Fluid Flow. Yeah, I hope I believe there is some problem from your end, organizer. Oh, is it what is to be done? So again, the presenter, can you present, please?
It will be tough because we are in different time zone.
Okay. So what is to be done, the organizer?
We'll try to adjust the volume.
No, some glitch is there in transmitting the audio. So I suggest, can you please reset the thing? Can you just again log in MS Office? Is it possible then only?
sir, logging in again won't help because the video itself, recorded video itself has problem.
Okay, so okay, then you go from the beginning. I'll try.
Okay, sir.
Start from the beginning.
Okay, sir.
From the beginning. First slide. Go to the first slide. Introductory slide. First. This is second. Yeah. Hello. Good morning, all. I'm nursing, and this work is done with Professor Victor Steinberg at Weizmann Institute of Science. I'll be presenting about elastic instability in a straight channel with viscoelastic fluid flow. And what I mean by that is, say I have a straight channel and we have like dilute viscoelastic fluid flowing through that, and that can we have some kind of instability there at much smaller Reynolds number. And at much smaller, so elastic flow in a straight channel is linearly stable for all Reynolds and Weisenberg number. And I want to see that is there any nonlinear instability there. So this work is an experimental work, and so I'll be presenting about the experiments what I have done. Yeah, go to the next slide, please. So first I'll motivate the problem. So this viscoelastic fluid flow in pipe or channel can be seen, say, in oil pipeline in Alaskan region where they use polymer to reduce the drag. Or it's used in fire line where polymers are used to increase the flow rate. Or our sneeze is also a cough or sneeze when we do at much higher impact. Usually it's higher Reynolds number flow, and our mucus is usually viscoelastic in nature. Apart from that, there are applications even at a smaller Reynolds number, which is in, say, microfluidics or in curvilinear channel. Or it is used in oil extraction from rocks or groundwater remediation, microfluidic mixing. Just to mention, our blood is also elastic in nature. So some of this understanding can be extrapolated to that. Yeah, next slide, please. Yeah, so when we put polymer in flow, so you can see in the first left figure, usually they are in coiled state. But if there is shear or extensional flow, then what the flow can do is it can stretch the polymer. And the moment polymer is stretched, the elastic stress field is generated because of the elastic stress on the polymer. And once you have this elastic stress field, then you have like usual Navier-Stokes equation, or you have momentum equation. But on top of that, you have elastic stress field equation also. And even though your like Newtonian part of flow is unstable because of this elastic stress field, this can create extra instability, and we are interested in that the presence of elastic stress field, how does it affect the total dynamics, and can it make the flow unstable? But the thing is, once the flow becomes unstable, anyway, you will have different wall drag, mass, momentum, and energy transfer. And you can see on the bottom right figure that this polymer, like how does a stretched polymer looks like in the flow. So initially they are in coiled state, but if they go through a stretching, then you can see the stretched polymer. Next slide. And we are interested in this, that can it go to nonlinear instability, because curved streamlines, if the streamline itself is curved like curvilinear channel, then it is shown that it is like linearly unstable. So it's fine, it's well studied. So but then this straight streamline has its own application, and it can be used later to understand even the high Reynolds number cases, to understand turbulent drag reduction and turbulence there. And the question is, if it is unstable, what are the scenarios, transition mechanism, coherent structures and coupling. From one of the guests, there is some external noise. Can he mute his mic? Arjun. Yeah, next slide, please. So these are the experimental setup, because as we are doing instability analysis, means instability experiments, it's important that you don't have any uncontrolled perturbation in your system. So for that, everything has to be kept on optical table and quiet environment first. Second, we can't use pump, so we use nitrogen cylinder to pressurize the tank, and then this fluid goes through the channel. And we use some cylinders, 11 cylinders in span wise and 3 in stream wise, to perturb the flow. Or here, because it's elastic fluid and velocity field is linearly stable, so we have to perturb the elastic stress field, not the elastic field, because Reynolds is also very small. So perturbing velocity anyway doesn't do anything because your inertia is very small. So that is the key point here, that one has to perturb the elastic stress field. And if one wants to perturb elastic stress field, it's important that he has either elongational, mostly like elongational flow in the system. That's why we put 100 micron cylinder, and across that we have elongational flow. Because of that, all the polymers are stressed here and they are perturbed. And then far downstream in the channel, we looked at how this instability looks like. Please go to the next slide. Yeah, and then we use, like, as it's slightly bulky system, you can't keep it on microscope. So we have like home built microscope kind of thing for PIV. And the result which I'll be presenting today is mostly from pressure measurement and high speed PIV in this system. Yeah, next slide, please. Next slide. Yeah, this side. Next slide. Slightly one slide before, you missed one slide. Next. Slightly go ahead. Forward. Yeah, fine. So to perturb the elastic stress field, you can see that for Reynolds 0.1, obviously Weisenberg is high here. Weisenberg is roughly around 100. You already have instability. So you have like vorticity behind the cylinder at cylinder Reynolds number of 0.1, but Weisenberg is of the order of 100. So these instability or these vorticity creates the stressed polymer, and we look into that the dynamics of this elastic stress field generated by this stressed polymer. How does it affect the far downstream channel flow, viscoelastic channel flow? And you can, even if you look at the spectra, you see that you have huge fluctuation and algebraic decay near the cylinder. Yeah, next slide, please. Yeah, so now we look into the far downstream where perturbation from the cylinder is gone. Due to limitation of time, I won't talk about how do I make sure that there is no effect of cylinder geometry here. It's just the perturbation which is convected downstream. So on the right top, you can see that it's normalized friction factor. So CF friction factor by laminar friction factor. So if it's 1, means flow is laminar. If it's more, and you can see that at around Weisenberg of 25, you have transition to elastic instability, EI. Then it goes through elastic turbulence, ET, and then it goes to drag reduction. And we are interested in this regime, that what happens to instability, turbulence, and drag reduction, why we have different regime and other things. So on the bottom left, you can see that you have fluctuation in span-wise velocity, and bottom right, you can see that RMS of pressure and RMS of velocity both increases with Weisenberg. Again, I would just remind that Reynolds in all these cases are very small. It's around 0.01 to. So in those small Reynolds number in channel flow, you can have pressure instability, like pressure fluctuation, velocity fluctuation, elastic instability, and we are interested in this because it is important to understand many of the practical things. Next slide, please. Yeah. So now if you look into the structure, coherent structures, how do the structure look like? So if you see, so there are 3 row, first row is for velocity, second row is for vorticity, third row is for gradient of a span-wise velocity. Gradient of the span-wise velocity gives us a sense of a stream-wise structure in flow. And if you look into the velocity, bottom, like top left, you see this white, like red and blue band. Red is positive velocity, blue is negative velocity. Which signifies that there is relation between that, and soon we'll see that once you have high, so this is elastic wave energy versus Weisenberg. So when you have high wave energy, then you have very organized structure. As once wave energy reduces, you don't have that strong structure, which suggests that this wave energy feeds the energy to these cycling of structure like streaks and all. And due to that,
And no audio is coming.
hello organizer, please go to the next slide. Yeah. Thank you. So if you look into the velocity spectra, so at initial Weisenberg, you have like a spectra of -2 minus, and it increases with Weisenberg and reaches to -3.2, which is signature of elastic turbulence. So it's been theoretically shown that if flow has elastic turbulence, then the spectra will be around, it should be high, like exponent should be smaller than -3. So we have -3.2, which signifies we have elastic turbulence here for cyan color. But again, if we increase the Weisenberg further, then it goes to drag reduction, if you remember friction factor plot. And in the drag reduction, you have like two regimes, first -1, then -2. And if we increase it further, then again it starts organizing to new kind of a state. Again, the spectra starts increasing to -2.5, and the initial signature is going off. Yeah, next slide, please. So what I showed you in viscoelastic flow, that you have we have formation of streaks, and then this streaks interface starts becoming unstable. We could see the perturbation at the interface, and then due to nonlinear interaction, these streaks becomes unstable, and you have both streak and roll. And due to limitation of time, I couldn't show that once these streaks goes through instability, it's very similar to KH like instability. But the dynamics is very different because you don't have inertia here. So it's like elastically driven Kelvin-Helmholtz like instability. Then it goes to chaotic state, complete thing becomes chaos. And then again, chaotic state decays and new structure, new streaks form. But the new thing over here is that this complete cycle is governed by the cycle of elastic wave. So the time period of this cycle is equal to the time period of elastic wave. And this is very different from the classical Newtonian picture where you have streaks, it forms, like it becomes unstable and it grows, and then you have streamwise rolls, and these roll again convex along the shear and forms the streak. Yeah, next slide. Next slide, please. Okay, next slide is conclusion slide. So I'll conclude that what we saw, what I showed you in this presentation is like in straight streamlines in channel flow can also go through instability at Reynolds much less than 1. But Weisenberg, when Weisenberg increases, so Weisenberg is control parameter here. Weisenberg increases, flow goes through instability, and friction factor increases up, and along with that you have, we looked into the structure, so you have streamwise streaks and streamwise rolls there, and along with that these streaks can become unstable through Kelvin-Helmholtz like instability, and we have presence of elastic wave, which is very important in gradient here because it feeds the energy to the flow and also it decides the cycling. And when we looked into are these hysteretic in nature or not, so this instability was not hysteretic in nature, which means that this is not.
Thank you. So,
thank you.
Considered in this study, like linear or non-linear?
So this is channel.
Hello.
Yes, yes.
So this is 2-dimensional large aspect ratio.
Okay. Thank you very much.
Thank
you very much. Then we will move on to the next presentation. So,
Hello, sir. Yeah.
can you please present?
Yeah, sure, sir.
Yes.
So, yeah. So, can you just play it from the beginning? Yeah. So my name is Vishnu Venugopathi. I'm from IIT Guwahati. So I'll be talking about mean mint and its characteristics in turbulent relevant convection in a cubic cell. Next slide, please. Hello. Hello.
Yeah, you are audible. Please continue.
Yes. So relevant convection is a bottom heated and top cooled configuration of a fluid layer. So here you can see in the figure there is a fluid layer which is sandwiched between two surfaces, of which the bottom one is heated and the top one is cooled. It finds its application in a lot of fields, including the convection dynamics inside the Earth's crust, atmospheric flow, stellar convection. And to quote some of the industrial examples include the cooling of electronic chips, then metal solidification process, etc. Even heating a pan of water in our household can be considered as a crude example of RBC. Now, the next slide, please. Now, moving directly onto the problem. So we have carried out direct numerical simulations of turbulent convection inside a cubic box. This is a schematic of the flow domain which we have used. So with the boundary conditions. So we have used isothermal surfaces on both the bottom and top walls. So there is the bottom one is heated and the top one is cooled, and all the lateral walls are adiabatic. In the study, we are mainly focused on the flow structures, then the large-scale circulation, or rather called as a mean wind, then its characteristics, then its effect on the boundary layers and dissipation rates. Next slide. Moving on to the numerical methods. We have considered 3D finite volume discretization. We're used by ECG step, which is preconditioned with SIP, that's strongly implicit procedure. Since these are very high-end simulations, we have used parallelization, which is based on domain decomposition, and the communication between the different domains are carried out using standard MPI libraries. So these are the dimensionalized, non-dimensionalized momentum, mass, and energy conservation equations. We have non-dimensionalized using the height of the container as a length scale, and for velocity scale, we have used the buoyancy scale, that is root g beta delta dx. RA and PR are here the Rayleigh number and Prandtl number respectively. Next slide, please. So here I'll just briefly discuss the grid and code validation. So one of the highlight of the study is that we have been able to achieve a very high Rayleigh number of up to 10⁻⁹, which is a very rarely attempted in this kind of flows. So we have used a Prandtl number of 0.7 considering air. So while considering such very highly resolved or high-end numerical simulations, it's very important to aptly identify the grid size which we are using. So for this, we have actually considered two criteria. One is that the boundary layer should be aptly resolved. For this, we have necessitated like close to 6 or more number of grid points should be there within the thermal boundary layer. And the second criteria is which we have considered is that the mesh size should be resolved all the way down to the Kolmogorov scale or approximately in that range. So here in the table, we have shown the Rayleigh number, the grid size used, then the number of points within the boundary layer, then the Nozzle number computed using different techniques. So the first one is Nozzle number based on the surface gradient at the bottom wall. Then the Nozzle number computed based on the dissipation rate, whereas first is thermal, then viscous. So you can see that all these values are comparable, which shows that the numerical simulations are well resolved. Then again, for comparing with existing study, we have compared the results with the study by Kasperovsky and Sia. So you can see that the Nozzle number reference, which is their Nozzle number, is also quite matching with our results. And also the maximum grid size, the ratio of maximum grid size to Kolmogorov scale is also always close to 1 or of the order of 1, which again says that the simulations are well resolved. Now, next slide, please. So now moving directly on to the results. So here we have shown the temperature isosurfaces for different Rayleigh number, starting from 10 power 7, 10 power 8, 5 10 power 8, and 10 power 9, that is highest Rayleigh number achieved. And the bottom panel shows the temperature contours at the midplane, it's a horizontal plane. So clearly you can see that as the Rayleigh number is increasing from left to right, the structures actually become finer and finer, and also they become sharper. And another aspect which is quite evident is that they become more wall bounded. So at the highest Rayleigh number, it's very apparent that the hot and cold plumes, which is you can see the temperature isosurfaces, they are mostly separated and they are segregated towards the corner walls. So such a kind of organization is usually referred to as the mean wind or the large scale circulation, in short the LSC. So in this study, we will be focusing on this LSC and its effect on the boundary layers and the dissipation rates. So next slide, please. Yeah, so in this, let's discuss more into the details of LSC. So like I said, here in the left side, it shows the temperature isosurfaces for the highest Rayleigh number, 10 power 9. So for better identification, we have shown the temperature contours in the two diagonal planes. So that is D1 and D2, which is marked by that green dashed line. So in D1, again, we have shown the temperature contours. So it's very evident that the hot and cold plumes are segregated on opposite sides of the lateral wall. They form this large scale structure, the LSC. And entirely different flow structure is seen in the opposite diagonal, that is D2. To further get more information of these flow structures, we have shown the time average contours. So here, the bottom panel actually shows A and B, shows the temperature contours in these diagonal planes. And we have also superimposed the average velocity vectors. So interestingly, you can see that in the diagonal plane containing LSC, that is marked by the frame A, you can see along with the LSC, there exist two corner rolls. So these are very important vortices. They actually play a significant role in the sustaining this large scale structure, the LSC, and also its dynamics. In the other plane, we have identified a new structure, which we call as a four-roll structure. So these are actually counter-rotating vortices, four vortices, which exist in the other diagonal plane. And these dynamics of these two planes are interlinked. And so we can move on to the next slide, please. So here we have actually studied the vertical velocity in these diagonal planes. So it's important that the vertical velocities actually gives you an idea about the strength of the large scale circulation. For example, so you can see in the first panel on the left side, we have shown the average vertical velocity along the diagonals. That is, one is D1 and the other is D2. So D1 is marked by the LSC diagonal and D2 is the non-LSC diagonal. So you can see that clearly the velocity in the LSC diagonal is, the magnitude of velocity is quite higher, and it's almost negligible in the non-LSC diagonal. So it's prevalent, the large scale structure is actually prevalent in the LSC diagonal itself, which was expected. And again, you can see it peaks near these walls, which again shows the wall bounded nature of the flow. And then if you increase the, now this was for 10 power 7 Rayleigh number, 10 power 7. And if you increase the Rayleigh number, so here in the right side panel, we have compared the average velocity with for three different cases, 10 power 7, 8, and 9. So you can see that as the Rayleigh number is increasing, the magnitude of the velocity increases. Also, they become more closer to the walls. So this again indicates that as the Rayleigh number is increasing, this large scale circulation structure, it becomes stronger and stronger, and also it becomes more closer to the walls. That is, they become more wall bounded. And as a result, you can see there is an increase in bulk homogeneity. So clearly you can see for the black line, which indicates the 10 power 9 case, at the bulk region, it's almost a straight line with magnitude close to 0. So this signifies the bulk homogeneity at that pretty high Rayleigh number range. Next slide, please. Can you move on to the next slide? So, so what we find is that the appearance of LSC significantly affects the dynamics of the boundary layer structures. So here we have evaluated the boundary layers in the top and bottom surfaces, top and bottom. And the frame A actually shows the temperature isosurfaces for 10 power 7. Then the frame B shows its the average temperature isosurfaces. So note that here we have considered averaging during a time window when the LSC is staying in a particular plane, and that diagonal plane is marked by that dashed line in the top of frame B. So from this average temperature contours or that field, we have computed the boundary layer thickness at the top and bottom. So what we find is that for example, in frame C, which shows the temperature contours in the bottom plate. So the regions where this hot plumes arise from the bottom plate, this shows a higher thermal boundary layer thickness, and this region which is diagonally opposite to it, which is where the cold plumes which is coming from the top plate splashes onto the bottom plate, these areas show a lower temperature, the thermal boundary layer thickness, and similar effect is observed in the top plate also. So then we have actually plotted how these things vary along this diagonal, that is along the LSC diagonal and non-LSC diagonal. So moving on to the next slide. So here we have shown the thermal boundary layer thickness along the LSC and the non-LSC diagonals. So it's so what we observe is that as we said, along the LSC diagonal there are regions where there is high thermal boundary layer thickness and low boundary layer thickness. So this along this LSC there is a asymmetrical boundary layer thickness, and across LSC there is a symmetrical boundary layer thickness. Now moving on to the next slide. So finally we evaluate the effect of LSC on the thermal dissipation rate. So here the frames A and B shows the thermal dissipation rate in the diagonal planes D1 and D2, and D1 is where we have the LSC. So it's clearly seen that you can see near the top and bottom plates dissipation is significantly higher, close to boundary layers, which is as expected. And the frames C, D, and E show the horizontal planes. So C and E are near the top and bottom plates, which is within the boundary layer region, close to boundary layer region, and D is the mid plane. So again, the top and bottom region, it shows significantly high dissipation rate, and the red regions in these planes C and E again indicates the region from the plumes coming from the opposite plate splashing onto the horizontal onto the boundary layer. So these regions are associated with higher gradients and results in high dissipation rates. And so these things were quite expected. And one interesting thing which we found is that dissipation is significantly higher in the regions where two counter-rotating rolls interact. So what I mean to say is that in case of the LSC diagonal, so here along with the LSC there are two counter-rotating rolls. So the regions where these smaller vortices interact with the LSC, these regions are associated with a higher dissipation rate. So you can see those regions near to the arrow marks. There is a dark red region. So these are those regions where the counter-rotating rolls interact with the LSC. So these regions are associated with a higher dissipation rate. And similar phenomenon is observed in the four-roll structure plane, where you can see two counter-rotating rolls from the either side interacts in a mid-planar region. So in the mid region of plane B, you can see a higher dissipation rate. And this is much clearly seen in the frame D. You can see that the LSC is marked by the diagonal line, the dashed line, and on the opposite side, there is a top right corner and the bottom left corner. There are regions associated with high dissipation rates. So these are due to the interaction between the two corner vortices, the counter-rotating vortices of the four-roll structure. Now, yeah, can you please move on to the next slide? So with this, I wind up my presentation. So these are the main conclusions of the study. We have been able to identify, we have been able to attain a very high Rayleigh number regime, and in which we have identified the LSC and the four-roll structure in different planes. Then we have quantified the vertical velocity distribution in the LSC and non-LSC plane, and also seen how it varies with increase in Rayleigh number. So as the Rayleigh number increases, the strength of LSC increases. It becomes more dominant and wall bounded. Then finally, we have studied how it affects the boundary layer and the dissipation rates. To get more information on this study, you can always refer to our recent paper in Physics of Fluids. So thank you.
Thank you for the presentation. So if anybody has any question, please ask. Okay, so if nobody has any question, thank you very much to the presenter. Then I believe this session is finished. Then we can the next session can be started basically.
Okay. Sir, we are extremely sorry for the glitches you found during this, and for the participants, it was quite difficult to do that. So we apologize for that.
Not a problem. Thank you very much. So I appreciate actually participants or presenters. Yes, they have quickly actually finished their thing and make up the thing basically at this moment. Thank you all.
Okay, thank you, sir.
Okay. Thank you very much.
Thank
you very much, Professor.
Okay,
thank you.
So then I'm leaving. Okay.
Okay. Thank you, sir. Good morning. Hello, Professor Talukdar.
Good morning. Good morning.
Good morning. So can we start the session of Professor Drush?
Yes, I'm ready.
Okay, sir, you can introduce about Professor Drush, then we'll start the video.
Sure. Good morning, everyone. A very hearty welcome to Professor Drush, organizers and participants of FMFP. It gives me immense pleasure to introduce Professor Drush and sharing this session of FMFP. Thanks, Professor Dalal, for giving me this opportunity to share this session of Professor Drush. It's not easy for me to introduce Professor Drush with a few sentences. I met him back in 2002 at IIT Guwahati, just in front of the guest house, which was used temporarily as a conference hall at that time. I came to know about this person a lot when I worked with him at his institute for a longer period of time. He headed this institute of fluid mechanics with more than 80 staff, out of which probably about 50 plus people were basically PhD students, postdocs, and many guest professors. More interestingly, there were always a lot of Indians in his institute at any point of time. If you see any of the old IITs in India, you'll find at least 2 or 3 faculty who worked with Professor Drush at some point of time. If you see, he's a professor full of ideas, full of enthusiasm, extremely hardworking, and one of the renowned person in fluid mechanics in Europe. A brief bio about him. Professor Drush studied aeronautical engineering at the Technical University of Stuttgart in Germany and completed his MSc and PhD degree at the Imperial College of the University of London. Afterwards, he worked as a special research center at the Technical University of Karlsruhe, Germany, before he became a full professor at the University of Erlangen-Nuremberg, also which is in Germany. After retirement in 2007, he opened up his own company, FMP Technology, as a CEO, where he is still active. He continued there his research work in fields like laser Doppler anemometry, laminar and turbulent flows, extended Navier-Stokes equations, microchannel flows, coating and drying equipment, etc. For his work, he obtained various national and international prizes and is a member of 5 scientific academies. I request Professor Drust to start his lecture, which is solutions of some unresolved problems of fluid mechanics. Professor Drust, please.
Thank you. Good morning, everybody. Welcome to my presentation on solutions to some unsolved problems of fluid mechanics. I'm glad you could come. Usually I see in the audience whom I am talking to. That's now not possible, but I hope that quite some people will listen to this presentation. Let me start out to thank Professor Dalal and the organizing committee to invite me to this presentation. And I was hoping that I can use the conference as an excuse to visit India once more and meet many friends here who usually come to this meeting. Let me now briefly explain what I mean with solutions and unsolved problems. But before I do this, let me show you some historical picture here. I have drawn here on this picture the names of the various contributors to fluid mechanics. As you can see, it is quite a number of people who have contributed to the development of fluid mechanics. Usually we start out with Leonardo da Vinci, up here, and go then down through Bernoulli, through Euler, through Laplace. But I think the major contributions and the ones most important for my presentations is Navier and over here Stokes. They derived the Navier-Stokes equations, and we are using them these days for getting solutions to fluid mechanics problems. I'm asking whether they are really problems. Are they not just tasks which we can now solve with these equations, and we can solve them with numerical methods, analytical methods, and experimental methods? We are in this time now, where the necessary methods for measurements, methods for computations have been developed. The golden age of fluid mechanics exists, but as you will see, there are still some problems we cannot solve properly in fluid mechanics. Let me start out to explain the kind of problems I would like to tackle, at least to introduce you to some ideas about these problems. A problem does, in my opinion, not exist if you can solve it analytically, if you can solve it numerically, or investigate it experimentally. That is a fluid mechanics task, and we can get a solution by these methods we have available and the suitable equations or the test equipment. But a real problem is in fluid mechanics if we get theoretical solutions by solving the Navier-Stokes equations here, the continuity equations and the energy equation. And if you then investigate the flow experimentally, and there is a difference. And now you have to decide what is the problem. You have two solutions. Both solutions are correct, but there is a difference. That are the kind of fluid mechanics problems I would like to talk about. Here now, one of these problems, microchannel or microcapillary flows. Here you see on the right, on the left-hand side, the results of Maurer for mass flow measurements, the mass flow through the microchannel. Theoretically, solving the Navier-Stokes equation, we get this solution, a parabolic velocity profile. If you go to smaller and smaller channels, and of course, higher and higher pressure differences, as you can see here, you find you get a difference between the solution to the Navier-Stokes equations and the measurements. This is now the kind of problem we have. And of course, we can not solve this problem really by modeling, because we would have to model the molecular interaction with its rough surface. So here is now the kind of problem I think we have and we need to solve somehow. You get a higher mass flow rate through a small channel than you should get solving the Navier-Stokes equations. Now, very often we think this is a microchannel flow problem particular to this flow. This is not the case. Have a look here. There's no channel. You have an obstacle in a supersonic flow and you get a shock. And this shock wave, as it's called, has now an ideal solution, which is this line here. So the pressure, the density in this case changes at this location. Experimentally, you find a change given by these points. And the line is the solution coming from the Navier-Stokes equations. The difference is there between experiments and theoretical solutions of the equations. And of course, now we have the kind of problem we would like to solve. There is a third problem I've indicated. This is a flow through a pipe. The flow is turbulent and it is heated from the wall. You can see this from the temperature distribution. Of course, as you go downstream, what you have is the velocity U increases because of the expansion of the flow, and also the temperature increases because the flow is heated from the walls. And again, you see now the theoretical solution and the experimental findings disagree. Of course, here now it can be that the K epsilon equation is incorrect, but some hints are also there that we have a similar problem to microchannel flows, and this is what I would like to explain to you. Have now a look at the equations. See if the equations, the predictions are not agreeing with the experiments, and we have the initial conditions and also the boundary conditions correct, then there must be a defect in these equations. And this I would like to point out. Let us start out with the Navier-Stokes equation. You have here on the right-hand side, you have the molecular transport of momentum. Don't call it friction. It is the transport of molecules of momentum. Similarly, you have in the energy equation the molecular transport of heat, of energy. But have a look at the equation here of the mass. There is no molecular mass transport in these basic equations of fluid mechanics. This is the major reason why we get these defects in some of the flows. Some of them I have indicated. So with a conventional Navier-Stokes equation, we have no mass diffusion. And if we now introduce this mass diffusion, we get the extended Navier-Stokes equations. And I will use these shortenings here to explain which kind of equations I'm using. Here now, the explanation for the missing term of diffusive mass transport, so molecular mass transport. Have a look at this checked area. Through this checked area, this can be the area of a cube. Through this checked area, you will find that molecular motions will transport mass. So there's a mass transport from here to through the checked area. It's indicated at that point. The last time the molecules interact with other molecules is one mean free pass away from the checked area. So then the properties UM and rho at this location are transported up. There's also a transport of the molecules down through this, from this upper area. And this is now that combination of properties that enters the mass transport by molecules. Minus if the transport is downwards, plus if the transport is upwards. UM is given here for, you can now take series expansion, and then you will end up with these terms. And you can now build the products between these terms, and when two terms are different, have these different operators in them, we take them out, being smaller than the terms that consist of these terms here, or combinations of one term with a gradient. At the end, you end up with this mass transport by the molecules. And you can see it depends on the mean molecular velocity and the mean velocity of the molecules and the gradient of density, or the density and the gradient of the velocity. So you end up with this equation. Now you can use the ideal gas law and get now the correct derivations here, expressed once in density and temperature and once in pressure and temperature. Out comes two terms. This is fixed mass diffusion term. And then the temperature term here is Sore's mass diffusion term. So both terms are known, for example, in physical chemistry. And they are used there, but we are not using them in the mass transport equations of fluid mechanics. If there is mass transport, there is also energy transport, heat transport. So we can now do the same thing. There is heat transport from the bottom, there is heat transport from the top, and this is the top one down, and this is the bottom one up. And you can again take the difference, and then you get the diffusive transport of heat by molecules. Again, you can now derive this expression, and you might see that this is the mass transport, and multiplied by Cp times T gives you now the additional heat transport there is. This heat transport comes from the mass transport, which we are missing in the in the mass transport equation. And at the end, you get an expression here for the ideal gas, and you can do it also for the ideal liquid, as I show later on. As a last term, we have the transport of momentum. Here you can see the transport of momentum we usually have. It's this frame one. And then you have now again, due to the mass transport, which we are missing in the continuity equation, times uj and ui, that are the momentum transport terms that you get additionally in the Navier-Stokes equation. So we have different equations, and they are now shown here. And you can, they are very similar, but in this velocity, you have now the convective velocity and the diffusive velocity. Here also. And this is now the tau ig term, which is also expressed in terms of total velocity. If you now put in the ideal gas law, you get this equation. And then you end up with a full set of equations you can also solve, but for total velocity, you get the convective and the diffusive velocity. That's the diffusive part, or this is the diffusive. For an ideal liquid, this is the equation. The T here should be an xi, so I'm sorry for this. Now, let's take now this extended Navier-Stokes equations and solve it for microchannel flows. What you get now is this solution for the pressure difference Maurer used. And if you now do the computation for that pressure difference, you see that the numerical solution goes, also the analytical solution, which is possible here, goes directly through the data of Maura. We do not need any modeling. We do not need to take care of this complex structure of the wall in order to get slip flows introduced. I can also not imagine how you can deduce slip flows from this kind of a rough wall interacting with molecules. Now, let's look at the shock wave. Here you see the Navier-Stokes equations. That's the ideal gas without any viscosity, you would lie here. Then if you take the solution by the conventional Navier-Stokes equation, you end up with this line. So there's a difference between the experimental results and this numerical solutions to solve shock waves. Of course, you can now model again what I have done here with a combination, but you don't make it quite. But if you now solve the extended Navier-Stokes equations, the line goes straight through the experimental results of Maura. Here now let's look at the turbulent case. The dark points are the numerical solution with a classical K omega model. The points here, the circles, these large circles, are the experimental results. And if you now take the extended equations and you solve it with the K omega equation, you get some improvement. Of course, it's not perfect. Part of this might be due to the modeling of the K omega equation, which is the conventional one, and it should possibly be modified to when you use the extended Navier-Stokes equations. Nevertheless, you get an improvement, and more work is needed in this field in order to see how one can get better predictions when high temperature gradients exist in heated pipe flow. Let me now come to a second problem. In the first problem, basically there was a defect in the Navier-Stokes equations, and I explained this, and I showed that you can overcome this defect. We can extend these equations. You might say, why did nobody else find this? The reason is, in my opinion, quite simple. We have a tendency to believe these equations and then find outside of the equation reasons for the discrepancies which I have shown you on microchannels, channel flows, on supersonic flows, and strongly heated flows. The other problem I would like to tackle is indicated here. It's the laminar pipe flow. Here you see the pipe. Inside of the pipe, you see parabolic velocity profiles. And we know from many theoretical investigations that these parabolic velocity profiles are inherently stable. So you can knock them, but the viscosity will damp this disturbance out. An excellent summary of the existing work is provided by Schlichting. And if you look at this work and also some additional publications in the literature, you get these results. On this side, you get the critical Reynolds number, and at the bottom, you have the diameter of the pipe, and you can see there is not a single critical Reynolds number coming out, but a whole set of Reynolds numbers. And you also find the bigger the pipe, the higher the critical Reynolds number you can get. So if you want high Reynolds number, stable laminar pipes to be investigated, take big pipes. Of course, then you need big blowers and you need all kind of big apparatus. But nevertheless, this is what the literature presents. Now, why is this so? So there is definitely a discrepancy between the theoretical results here and the experimental findings. So we have a problem in the sense I have said I will consider them in this presentation. Here now, once again, what do we compare? We compare a pipe flow, which is infinitely long in the theoretical treatments. It has a set parabolic profile. And now we disturb this velocity profiles, and the disturbances are damped away. And we compare this with a blower, which provides the flow through this test rig. It has some flow control, a diffuser, plenum chamber, and nozzle. And then it has a long pipe, and the length is different from one experiment to the other. There's also equipment, measuring equipment, associated with this test rig, and we blow this air into a laboratory of different size. The laboratory walls are indicated here, and it's quite clear the differences which you have just seen, here in Reynolds number, come from these differences in the test equipment employed by the different investigators. Let us have a look at the cause of these differences. I start out with a blower. This is a blower which you have on one side of the test rig, here, and it provides the flow through the pipe. Now, what property must this blower have to get the laminar to turbulent transition of pipe flow investigated? Here you see the friction factor of this blower is going down. At the point where the transition occurs, the friction in the pipe must go up, and this, of course, there's no means to do this. So basically you can expect flow jumps. It finds now out it should increase the pressure, but this blower cannot do this for this flow rate, so it will go back, and at the end you get all kinds of disturbed flow, but not the kind of disturbance you would like to have to go from this low point here up to the upper point. This is now the result. You have a laminar flow, and if you now increase the velocity by increasing the power output of the blower, you find that the flow finds, well, I should go turbulent. But then the conditions of the blower are not there to do this, so it jumps back. And this happens, and basically you get these kind of flow phenomena that are called in the literature slugs. Puffs are also there. They have a very similar behavior. Now, if you want now to study what really happens here, you must build up a test rig of this kind. In this case, we are using here a mass flow controller. So this mass flow controller can allow us to blow out air, and you use the increase on the high pressure side, the increase of the pressure, to increase the flow rate here. In this case, it is a slow process, as slow as our blower. You can, however, have another means to control this mass that is faster, so it can react very fast to the requested change in pressure or in flow rate. That's the plenum chamber. I will say something about that plenum chamber. And here you have an iris diaphragm where you can disturb the flow. We know if you don't disturb the flow, it will not turn turbulent. So since we want to study transition to turbulence, we must have some kind of a disturbance here. We have chosen this iris diaphragm to get the disturbance generated. It's automatically controlled, so you can close it, so put in a disturbance, remove the disturbance, and in this way get short disturbance, and we can see how these grow in the pipe. We used pipe between 0.5 and 8 meter in length, giving us longer times to observe these disturbance-caused flow disturbances. Everything was controlled by a computer, and we recorded everything and evaluated the data afterwards. And here's now the test rig. The test rig is, here is the test rig is quite normal, apart from this disturbance element here. So what you now see is this mass flow controller. This I would like to explain here. The flow goes in the test rig here. In these sketches, I have drawn it in this direction. You have here a 3 millimeter closed ball, and this ball can be opened so that a pressure increase or a pressure can be used here to get force flow in this direction. If you increase this pressure, more flows goes. And this mass flow rate is now depending on this pressure change. If you change pressure, it is a slow change of mass flow rate. However, this mass flow controller can also be operated by changing the position of this ball. This ball is the same as here. So if you now leave this pressure constant, you can open and close this fast and therefore control the mass flow rate by this area change. And this allows us now to see what the blower or the airflow generator is causing in terms of transition. Now, this is what happens. You open and close this device, and then this disturbance grows, and I show it here for the 8-meter long pipe. Over the distance, here you open and closed the, let's say this iris diaphragm, and then afterwards the flow, or let's say the flow grows in length, and at this point it leaves the pipe. So we only measure at the end of the pipe, and then it leaves the pipe. Before and after, the flow stays laminar in spite of these disturbances. So the laminar flow is there for the parabolic velocity profile, but there is a region where we can force the flow to become turbulent. Why that is so, I explain in a moment. Now, here is this length growth indicated. 8 meter, here you have triggered the flow. This is now the turbulent region. Here you close, not you close, here the flow leaves the pipe, and of course the flow afterwards is then laminar again. Very structured turbulent flows. It's very repeatable. This flow has about 20 trials, so 20 slugs, very precisely generated, very precisely observed, and they lie over each other. What you can also see is here, the front part of the pipe grows faster. The back part grows smaller, and this velocity difference is the reason for this growth of slug flows. So you can study turbulent flows in a well-controlled manner. Now let us have a look at some other situation. In this case, we have used the mass flow control system like this blower, and we obtained the kind of flows we knew from our pipe flow, but well controlled. In the other case now, which I would like to study, I use now here the fast change possibility of our air supply device. And I look now, in this particular case, at a plenum chamber. These plenum chambers have a tendency to oscillate. I've taken the results of Maurer. I've written the results of Maurer, and I've looked at the oscillations he measured. These plenum chambers with pipes going out behave like Helmholtz resonators. So they oscillate, as indicated here. And this oscillation depends on the length of the pipe, on the pipe diameter, on the shape of the plenum chamber. Everything influences it. If that frequency agrees with the mean velocity divided by 2 times the pipe length, you get a resonant. And it is now this resonance that controls your flow. This is what we have investigated and what we have measured. Here you can see now what you can produce with this test rig. If you run the flow now with this fast change in flow rate device, you get a completely different critical Reynolds number distribution than if you run it in terms of high pressure with a high pressure device. So this explains why you can have different results as you have them in the literature. Nevertheless, all literature uses blowers, or they use mass flow control systems, but the mass control systems are used very similar to the blower. So that's why all the data in the literature look alike. The highest critical Reynolds number we found is that of Fedinger. He used about 50 millimeter pipe, and the critical Reynolds number was measured to be about 1,000. In our case, when we run now the critical, the mass flow controller by that small ball, what you find out is you get 100,000, or you should get 100,000 if you run it with a fast control. But apparently at this Reynolds number, we already trigger some other device, so we could get this 100,000, but for some reasons, sometime later, it jumped down to a smaller value. It never jumped back again. So when you had once this critical Reynolds number adjusted, it would not go back. Nevertheless, it is interesting that you can manipulate the laminar to turbulent transition, the critical Reynolds number, by changing the blower, if you want, in this particular way. What do you now get? Here you see we have a critical Reynolds number of 7,000. That's what you get if you run this test rig with the pressure device to control the flow rate. If you now increase the flow rate, it jumps up and you get puffs and slugs. If you now use this ball bearing to encross the ball to control the flow rate, you get now oscillations. And these oscillations are fantastic, but the flow never turns turbulent. It oscillates and it stays turbulent until it catches sometimes another mechanism that turns the device turbulent. Look also at the Reynolds numbers. Before we had Reynolds numbers of 5,000 to 8,000. Now we have Reynolds numbers here of 53,000 to 41,000. And you see, sometimes you can drive that flow in a laminar oscillating manner into up to Reynolds number of 60,000. And then when you try to adjust it again, coming from the upper side, it only goes to 53,000. Nevertheless, with these fast changes, you can keep flows laminar, but oscillating, of course, up to 50,000. Let me now come to an end. I started out by explaining that the Navier-Stokes equations, the Navier-Stokes equations, the continuity equation, and the energy equation have a defect. This defect comes from the mass transport equation. There you can see 0, 0 on the right-hand side. On this case, you have on the right-hand side a molecular transport of momentum, a molecular transport of energy, but we have no molecular transport of mass. This is also the reasons that you can see in some of the textbooks on heat and mass transfer, that the heat transfer section has, let's say, 400 pages, and the mass transfer section has 50 pages. Why? There is no mass transfer. And this is, I think, a defect that we need to eliminate. I've done this for the extended Navier-Stokes equations, and I could see that discrepancies for microchannel flows can be eliminated. Discrepancies for shock waves can be discriminated. And discrepancies, or if you want, problems for heat transfer in turbulent pipe flows could be at least improved. Here are now, for these conventional equations, conventional form of the basic equation of fluid mechanics, the diffusion terms, no mass diffusion. The Fourier term represents the heat transport, and this is the Newton, the molecular transport term for momentum for Newtonian fluids. This is wrong, at least for laminar, this is wrong for ideal gas flows. If you take ideal gas flows, you can derive these terms. And this MI is now introduced on the continuity equation, where on the right-hand side it was 0. This term also influences the heat transport. It influences the momentum transport. And if you put these diffusion terms into the basic fluid mechanics equations and you solve them, some of these equations that cause problems these days, the problems are eliminated. If you now look at microchannel flows, which I started out with, you can now see that the world is more perfect now. Down here, above Knudsen number 1, we have molecular dimensions in our flow cases. Down here, we are quite some distance away from molecular dimensions. And we are still using nowadays the, let's say, methods of modeling in order to get agreement, although molecular dimensions are not in place yet. This is not the case if you use here the extended Navier-Stokes equations, and as I have shown, you can get a good agreement. So my suggestion is to use extended Navier-Stokes equations, at least in those cases where you have high pressure and high temperature gradients. I hope I could show you that the Navier-Stokes equations require extensions. Introduce them when necessary and get good results. Thank you very much. Good morning, everybody.
Thank you, Professor Drust. It's quite an interesting discussions of extended Navier-Stokes equation. Basically, to summarize, you have considered 3 different things. One is like the flow through microchannel, where conventional Navier-Stokes equation doesn't work. Then when there is a transition from laminar to turbulent flow, then also the Navier-Stokes doesn't work. And of course, with the shock wave. So before, and of course, there is one interesting thing is that in application, in books of heat transfer, as you were mentioning, that if there are 400 pages, there are only 20 pages per mass transfer. Even in our lectures also, we do the same thing. We have 40 lectures in heat transfer and finally 2 lectures in mass transfer. So that tradition still continues now also. I think before I ask you something, I'll take it to the audience because there will be more enthusiastic people in the audience to ask you a few questions. Please go ahead if somebody have any questions to Professor Drust.
Hi, I'm Shraman here. I have a question. The extended Navier-Stokes equation for the mass diffusion, you have a term for temperature. So how does that play a role? Density, I can imagine something, but for the temperature, how does that play a role in terms of mass diffusion?
You know that the molecular motion, the velocity of the molecules, depend on the temperature. So what you have, if you have a temperature gradient, you have on one side of that checked surface I have shown, you have a higher velocity, because the temperature is in the velocity term, and you have a lower velocity just on the top of that checked surface, and that gives you differences in the velocities in the molecules, and if you enter that into the equations, you get this temperature term. This temperature term is the reason why you have Sorey heat transport in fluids.
Okay, so is that equation derived from kinematic theory of molecules, kind of?
I started out with the Boltzmann equations, and I integrated and did all the kind of situations or all the kind of derivations, and at the end I did not understand what physically happens. Then I went back and I used mean velocity, molecular velocity considerations, and I got the same results. So what I have shown you is not the treatment of each individual molecule, but the treatment of the mean motion of the molecules, and it comes out perfectly. You get all the terms right. And if you look at the equations for Sorey, you also see you get the Sorey diffusion coefficient, which is amazing.
Yeah, thanks. It has been a very nice to go through your presentation. Thank you so much, Professor.
Good afternoon, sir. My name is Saroj Kumar Panda. I am a researcher in Department of Atomic Energy, Government of India. So we used to talk, my supervisor used to talk about you and your work many times during my PhD in IIT Delhi. So so it's a dream come true seeing you, listening you in a live session. So my query is, many times we generate experimental results, and also we generate predictor results from simulations. So sometimes we call it, it's a good result. Agreement is very good, and sometimes we call it as agreement is poor. So my query is, what basis we are judging it actually? Is there any parameter to judging it actually? Because that question is there in my mind since years. And what percentage error is acceptable, sir?
You see, the situation, if you do numerical calculations, presumably that's what you have done. Yeah. Now you get some additional things in. That is the accuracy of your numerical computation. So you get numerical errors coming in addition. So you first have to make sure that you get good numerical results with sufficient agreement, let's see, with the sufficient or accepted errors. And now what is accepted, that's very much depending on yourself. If you have a lot of money at a time, you can get very precise computations. If that is not the case, sometimes in industrial computations that's the case, then you have to accept somewhat less good results. Now, there are two things. One thing is definitely the case. You can look at these n dots, which I have given here in the equations, and then what you can put in is your numerical results because you know your gradients. And if n dot comes out to be small, then you're sure you're not having these effects I was talking about. So that's possibly one way to see how good your computational results are in comparison to the real solution using the extended Navier-Stokes equations.
Okay, sir. Thank you, sir.
Now you see that sometimes when I came out with these extended Navier-Stokes equations, I got very much criticized, and I took the attitude, well, criticize. I know that these derivations are right, and if you don't accept them, then that's your business and not mine. Then I found out, however, that we have a lot of very good students doing their PhD with us in fluid mechanics, and we should point out this shortcoming of the existing Navier-Stokes equations and ask them to look into it. And I'm sure then people will find out that possibly, or clever people will then contribute to this and get this topic further. Okay. Important to me is also the second case, the laminar to turbulent transition. Basically, what I've shown there, it cannot be that we have the Navier-Stokes equations and let's say a set parabolic velocity profile, and we predict inherent stability.
Okay.
And then in the experimental case, we get turbulence. Now, why is that so? The turbulence comes from the equipment and not from the laminar profile in the pipe. I think this is also a topic one should put some clever students on it and see what comes out.
Okay, sir. Thank you so much, sir. Thank you.
Is there any more questions from audience? Professor Biswas.
Good morning, Professor Durst. It was really, a delight to meet you again, although not physically, through virtual media. I think Professor Wang is also present in the audience, Anbang Wang. This is really not a question, maybe in the form of discussion. This formation of slugs and plugs in transition, this is a very well-known classical problem, started with Professor Rota, and probably it was concluded by you through your students and through very good publications. My point is that this slug formation and plug formation and this part of transition, this has really the paradigm where inherent disturbances come from ambience. Like this happened in the case of, if we go by the classical experiment of Professor Reynolds, Osborne Reynolds, that in the Cavendish lab, when he used to do experiments in the night, he used to get transition around 3,000, 4,000 Reynolds number, and in the day, and in the night, the transition used to take place. Flow used to be stable even for Reynolds number of 8,000 or 10,000. He got once 10,000. So basically, the disturbances that come from instruments, that come from surface, that comes from disturbances that come from surroundings, those disturbances can create a difference, but finally, that transition again. We get back to the laminar regime if the kinetic energy is not sufficient to support the disturbances, and this was very nicely done through this, almost like a super pipe you used, and I know all the equipment used there. Even the this disturbance was created by this aperture controlling this aperture of the disturbances. Fraction of a second, it created disturbances and it went out. But with all this, I'm just, what I'm trying to say that probably this has no apparent connection with the modification of Navier-Stokes equations that is proposed.
I agree with you. The second problem has nothing to do with the first part. So there I did not use the extended Navier-Stokes equations because I felt what we are studying there has nothing to do with strong pressure gradients and strong temperature gradients, but it has to do with the equipment we apply. And we should be clear, I always didn't say this, turbulence is a question of the equipment we use and not so much of the jet we are studying or of the pipe flow we are studying. It is the equipment we have to drive the flow cannot do what the transition requires. That's basically the message of the second part.
Right.
So turbulence, we are trying to look at local phenomena in a pipe, and it is driven by the blower in the back. This is, in my opinion, something we should look closer at in future investigations.
Absolutely correct. And probably I can add something that the pipe which you used is really a super pipe. I mean, its manufacturing accuracy is absolutely amazing. And that is why just the elimination of puffs and slugs were possible, and it could be shown that it comes from the artificial disturbance that was created at the entry.
Yes, yes. I should mention Professor Pishwas was also involved in some of these investigations. Quite a number of people I did not mention here. I had one slide where I had all given them, but to get this lecture here recorded was quite something. And at the end, we had to take it out because even in the third trial to get a good presentation going, it didn't work.
No, that is not the point. But point is really, having such accurate equipment like the pipe you used and your historical experiment of this backward facing step. They are also the accuracy of the positional accuracy, dimensional accuracy is really amazing. And, it is to be appreciated for the years to come. I mean, creating such absolutely accurate test facility. It is probably not possible anywhere and everywhere. It was only possible in, under your tutelage in LSTM. I do not know whether, such equipment can be given to or this are being used by others, or it should be continued such accurate equipment.
Yeah, now it is standing around doing nothing, which is a pity. Yeah.
Thank you, Professor Durst. Thank you.
Thank you also. Thanks for the nice words.
And let me also tell to the audience that Professor Durst, all of us can wish him for belated happy birthday. No.
Yes, thank you.
Belated happy birthday.
Happy birthday, Professor Durst.
Thank you.
Professor Dalal, you have some question.
I don't have any question. Just thank you, Professor Durst, for the wonderful lecture. I would request Professor Biswas to switch on the video, so it will be nice.
Okay.
Sir.
I thought that the bandwidth problem. Okay.
Yes, yes. Now it is looking fine. And also, I request Professor Wang to switch on the video. Then it will be very good.
You are muted.
Professor Talukdar, you please go ahead. Professor Talukdar.
Yeah. No, I have a simple question because I work in heat transfer. So by using extended Navier-Stokes equation, will there be a change in Nozzle number at the fully developed regime?
I'll see again. You are using the extended equation, and in which case you are asking you get the same results?
For example, in a microchannel, if I apply an extended Navier-Stokes equation where you have a mass diffusion, so will it increase the Nozzle number compared to a conventional Navier-Stokes equation?
It depends. It will, because what you have is now you have also let's say if you do not have any strong temperature gradients, then it will only through the pressure term increase the transport. If you have now the temperature and you have, let's say, if you have a high pressure gradient but a small temperature difference, you will have a higher number because of but it's driven by the pressure gradient. If you now have a very strong temperature gradient, you get an additional term coming from the temperature gradient. Okay. If you do this kind of work, take these equations in, and it is very amazing what you can see that come out. And you could see by comparison with Mara's data that you get agreement with the experimental results, and this shows that the numerical or analytical expressions allow you to get it inside what you observe experimentally.
Okay. Thank you.
Let me say one thing. I just realized now, in the turbulent case of the laminar turbulent transition, the plenary general results were by Mesmer, and I said Mara. This was a mistake.
Okay. I think there is no more question from the audience. Amrez, we can close this session by thanking Professor Drust.
Thank you.
Okay, thank you, Professor Talukdar, and thank you, Professor Drust, and all other audience here. And Professor Biswas, if you want to continue, means the session, it is open for us, means just to discuss in any topic. So we can go ahead with that. And Professor Wang, if you also if you can participate, it will be very nice.
I mean, I'm not really prepared for this impromptu discussion, but having Professor Durst among us is really amazing and absolute delight, because we can get ourselves enriched with his knowledge, with his suggestions, with his advice, and especially people who are planning for newer experiments or who are thinking about converting some paradigm into correct experimental paradigm, from where the real conclusions of long-lasting value can be drawn. They can probably get in touch with Professor Durst, discuss their problems, and I'm sure they will benefit a lot. Professor Wang is also here, so I will leave the podium for Professor Wang. Professor Wang.
Thank you very much for those words.
Yeah, Professor Durst.
Hello.
It's nice to see you, although not physically.
Yeah, thank you very much for coming to this meeting, and at least it gives me an opportunity to see you through television once again.
Yeah, it's really nice talk I heard. Yeah. But it's only a pity. Here is a little bit in Taiwan. My system, I have some egg to disturb my hearing about this, but in any case, I saw from the slides and to enhance the hearing problem, I cannot catch quite of that. And have you any suggestion for the future, especially for the young generation, when they are making, for instance, they are making microfluidic and so, and have you any suggestion, direction for them?
One of the things is sometimes we get annoyed if we get two different results for one solution of a let's say of a flow phenomena. And we should not. We should think about the difference and see where does it come from. This was basically the message I was trying to get over. Let's say if we're doing fluid mechanics, the following, we set up numerical properties of a particular flow and we solve them. Results. Definitely, this is also necessary because we have now these fantastic methods and we can use them to solve tasks in fluid mechanics. And if we do this as an only let's say, way to deal with fluid mechanics, then we will have no progress. We need this progress that we say it's impossible that people who did not have the numerical methods available, also some of the analytical means or the numerical means, that they have obtained all results of basic results of fluid mechanics in the 18th century. That I don't believe. We should look at these equations, the background of these equations, and see that we can use them, use the differences to find out where we can put in points and get improved equations, improved methods for the measurements, or for the investigations.
Okay. Yes, thank you. I think this will be a very delightful for the young generation to think about and progress further in the future. Yeah. And I heard you have birthday in this December, and happy birthday for that. And
thank you.
And it's really nice to see you are still so healthy as before, without any change.
Well, you see, I have learned that if you want to become old, then you must have a lot of birthdays. So that's if you want to stay healthy, you must do some activities, and possibly the best activities you can have is in fluid mechanics.
Okay, yeah, and sorry, I have a meeting in 3:30, and I need to leave. And I thank all of the organizer and all participants. And I hope you could have still a very interesting talk with Professor Durst. Professor Durst, I need to leave and say goodbye to you.
Thank you for coming to this presentation. Yeah.
Yeah. Thank you. Goodbye.
Goodbye.
Thank you, Professor Wang.
Yeah.
Any discussion or any from audience? I think there are no questions. Professor Talukdar, so please go ahead.
Yeah, Professor Bruce, hopefully we'll see you very soon. When pandemic is over, definitely we'll see in Germany for sure if you are not coming here.
Yeah, I would have really come to this meeting because, as I said at the initial part of my lecture, this would have been an excellent opportunity to meet you all. And I also hope it happens once more somewhere in the world.
Sure, yeah, it was exciting for me also. And and in the morning at home, I told I am going to, sharing a session for Professor Drust, which is a good news for my family too, because being here.
How's your family? Is it fine? Are they fine?
All good. My son is working now. He is a mechanical engineer working for a startup company in Bangalore. And my daughter is in class 11 now.
Oh, wow, they grow, huh?
Yeah, we are going home.
Say hello to your wife and also to the children. My wife is also sitting there, so she also says hello to all of you. And also Professor Bishwas, hello from myself and from my wife.
Yes, my heartfelt greetings to you, Frau Durst, and the entire family. It is, as I said, absolute delight to see you even from distance, and I look forward to meet you personally, whether in India or in Germany or elsewhere. I'm looking forward for the next opportunity to meet you.
Thank you very much. Thank you. And thanks for coming to this presentation. Yeah.
Okay, then Amresh will close this session here.
Professor Dalal.
Yeah.
Yeah, thank you.
Yes, thank you. So I would like to thank the speaker, Professor Drust, for accepting our invitation and means delivering this wonderful lecture. And also I would like to thank Professor Bishwas for attending this lecture and Professor Wang. And I thank Professor Talukdar for chairing this session. And I thank all the participants who attended this lecture. So thank you very much. So we are now means again we will meet at 1:30 for the keynote lectures. Thank you very much. Bye bye.
Thank you very much, and have a nice conference. Yeah. Thank you. Bye.
Have a nice day. Bye.
Thank you.
Let me quickly introduce the problem and its background and where we currently stand. thin leaves, paper curds, they actually fall under their own weight. However, when the density ratio between the object and the surrounding fluid is near about 1, then the trajectories through which the object fall becomes complicated, and it's a subject of fluid mechanical studies. It involves complex fluid structure interaction, stability of the trajectories. In trajectories, the established regimes are mainly three: flutter, which tumble, and the chaotic regime. To universally obtain different regimes, different shapes of plates are actually unified according to the dimensionless moment of inertia, which will be defined later on. From 0.16 to 0.4, it is known as flutter, which is shown in the right here. Tumble, sorry, the flutter. The tumble proceeds from 0.4 to 3, which gives us an impression of complete rotation, and the flutter to tumble transition occurs generally near about 0.4, which is generally known as chaotic regime, which shows the signs of both flutter and tumble. In the current study, we have added multiple plates to see the effect of the proximity of each plate on the stability of the trajectories and the role of complex vorticity dynamics in deciding their trajectories. As the current study involves multiple plates, it is essential that we
yeux est trop grand pour comprendre des choses aussi petites. Tu es trop grand pour comprendre des choses aussi petites. Tu es trop grand pour comprendre des choses aussi petites.
Hello, good afternoon. Welcome, Professor Pradeep and Professor Taggi.
Hello, Professor Amrez.
Good afternoon, Professor Dalal.
Good afternoon.
Good afternoon,
So
Professor
let us
Pradeep.
wait for few minutes, okay?
Sure.
Yeah.
And also more participants in the YouTube.
Yeah.
So let us wait for another 3-4 minutes, then we will start.
Right. Sure.
Yes. Thank you. So Professor Pradeep, I think means already you have checked how to present, and I think you are using
Yes,
Microsoft
we
Teams.
use it for our classes. So I can just check if this connectivity works.
Yes.
If my audio is okay, then I will just check if my slides are.
Yes, audio is fine.
Yes, Professor Pradeep, we can see the first page
All right,
of your
great.
presentation.
Sure. That's fine. Thanks.
Okay, so let us wait for a few minutes, and then Professor Taggi will start. Okay.
Sure. So I think Professor Pradeep is also chairing the next session in the same hall, right? Hall
That's
3.
right.
Yes.
That's
Okay.
right.
Yes.
And one small question I have, that the time is given from 1:30 to 2 p.m.
Yes.
So should we keep 2-3 minutes for question answer? Like Professor Pradeep, how long would you?
It depends on time. Say you can 5-7 minutes is flexible. There is no problem because we have break in the year, so you don't worry. So another 5 minutes if you want to take, no problem after 2.
Okay.
Yeah, I have time for 25 minutes, so I can wind up by 1:55.
Yes. So it is because we have some time for break, so that will be adjusted.
Okay.
Thank you.
Thank you, Professor Pradeep.
Hello, Professor Tyagi.
Yes,
So we
I'm here.
request you to start. We request you to please start the session.
Okay. Thank you very much. Very good afternoon to all the participants to this keynote lecture by Professor Pradeep, whose title is Understanding Instabilities in Axial Flow Compressors. Professor Pradeep is currently professor in the Department of Aerospace Engineering at IIT Bombay. He completed his bachelor's in mechanical engineering from Calicut University in 1998. Subsequently, he pursued master's and PhD from the Department of Aerospace Engineering at IIT Kanpur. After completing his PhD, he joined IIT Bombay as an assistant professor. His research interests are in the areas of turbo machinery, aerodynamics, design and performance evaluation of turbo machinery using passive active flow control methods. Professor Pradeep has supervised 8 PhD and around 58 master students at IIT Bombay. He has over 90 publications in international journals and conferences. He is also a co-inventor in 3 granted patents. So it gives me great joy in welcoming Professor Pradeep, and I invite him to please share his screen with the members and kindly start the presentation. Thank you.
Thank you very much, Professor Tyagi. And before I begin, I would like to first acknowledge the organizers of this conference, Professor Dalal and his team, for giving me this opportunity to share some thoughts on some of the work that we have been doing on this interesting topic. Of course, I also have to acknowledge all the contributions that my students have made. I get an opportunity to present their work. It's their hard work that I'm essentially presenting today. So before I get started, I also want to congratulate the organizing team for taking up this challenge to have this conference conducted on a virtual mode. That's a very bold step, and we are used to FMFP in the physical mode, and we hope that next time it will be indeed that way. And so before I get started, just to set a tone, bird's eye view of what this area is all about. Essentially what we are trying to do here is to understand some aspects pertaining to instabilities in compressors and where does it fit in the overall aviation center. So my talk is essentially biased towards shows sort of progression of how aviation has come about from the time it's essentially a tube and wing configuration, but that is expected to
ask questions. Thank you.
Thank you, Professor Tyagi. Turbines and compressors, and today's talk I'll essentially focus on the compressors. And what you see here are typical efficiencies that modern day individual compressor or turbine efficiencies touching 90s and beyond. So the question expected to, or some of the aspects which will need significant attention are to do with emissions efficiency as well as stability control. So the Advisory Council of the European Union came up with a set of guidelines long back stating that by the year 2020, that is the current year, we should have achieved some of these targets, which are quite substantial in terms of how these are going to be achieved. And they also came up with a roadmap as to how this can be achieved. And some of the crucial areas, of course, not all of them, some of them which are listed are to do with aerodynamics, heat transfer, materials, and cooling. And our interest is primarily in the aerodynamics of turbo machines. And I will primarily focus on one of them in today's talk, which is to do with stability in compressors. So I'll begin with a classical cartoon of complexities in turbo machine. This is from textbook by Professor Lakshmi Narayana, who is sort of considered as a guru in turbo machines, which highlights all kinds of complicated flow features that one would normally encounter in these kind of flow situations. One of the prominent ones being tip leakage flow, and you will hear this throughout the talk today, which I will refer to as TLV, tip leakage flow, and tip leakage vortex, which is basically the flow which leaks from the pressure surface to the suction surface and forms a vortex, and obviously results in a certain amount of efficiency loss. So in today's talk, I'll focus on a few of these aspects, largely tip leakage flow and tip leakage vortex and its interaction with the leading edge shock wave, which you would normally see in a high-speed compressor. We will also try to see how the inflow distortion or inflow non-uniformity interacts and affects the performance by having influence on the way the shock and the leakage vortex interacts. I'll also talk about a little bit about the scrubbing loss in one of the slides later on. So those of you who are familiar with compressor performance map would be able to relate to this chart shown here, which is a very important map as far as aero engine designers are concerned. This is a very significant aspect in the overall engine performance itself. So compressor performance map is expressed in terms of mass flow rate, which is corrected or non-dimensionalized in a certain way, and pressure ratio, and also the various speed lines, constant speed lines, which are shown here in purple, and the efficiency constant. So without going into details of the performance map itself, what we are interested in is this blue line that you see here, which is sort of the instability limit or the stability limit, whichever way you look at it. So this is the limit of stable performance of a compressor. So if you try to reduce or throttle the compressor beyond this, the compressor is going to go into stall or surge, which are essentially instabilities in compressors. And there are a lot of work which has happened over the years to understand these instabilities. One of the famous work from MIT, which came up in 2009, talks about how one can correlate the tip leakage flow with the shock wave, and the way they interact would essentially dictate whether the instability is going to be induced abruptly or whether it will be induced in a gradual manner. So there is spike inception versus modal inception, which came up around 2009 from MIT. So with that background, I will first begin with some of our very recent work, and then I will probably flash back a few years to highlight some of the work we did several years back as well. So this is a typical bypass turbofan engine, which usually has a fan in the front, which is what you would see normally when you board an aircraft. This is what you see, the fan of the engine. And we have tried to understand how the fan behaves under various inflow conditions and how the leakage flow and the shock wave of the fan can have a very strong coupling, and that sort of dictates the stability mechanism in fans. So what is shown here are essentially the relative Mach number plot, which is from our computational simulation. So I'll talk about RAND simulations as well as unsteady RANDs in a few slides later, and our understanding of what the physics is from this. So if you look at it closely, you will see that this is the fan blade and the direction of rotation. The leading edge of the fan has a shock wave, and there is also a leakage flow which is from the pressure surface to the suction surface. So the leakage flow is going to be this way. So there is going to be an interaction between the shock at the leading edge with the leakage flow, and the resulting blockage actually changes its characteristic as you go from the peak efficiency point towards the vortex breakdown or the instability point. So at some point, the compressor, as you throttle the mass flow, the leakage vortex is going to disintegrate, resulting in increase in the blockage in the passage, causing instability to be incepted. So this is something we observed as part of our work rather recently. Now, we further extended this work to understand what happens if the flow itself is non-uniform. An example could be this: an aero engine which is cruising at some altitude would have a flow which is relatively uniform, and if it happens to be at an inclination, let's say during climb or even at high angle of attack flights, a part of the flow is likely to be non-uniform or distorted, which is what is shown here. So if I take a section at the engine face at the compressor entry, this sector there where you can see non-uniform flow coming in will show up like this. So if you take 4 different sectors in this plane, one which is right in the core of the distorted sector, one is upstream of it, one is at the inlet of the distortion sector, and this is far away from distortion. What happens to the flow in these different sectors? So if you look at this a little more carefully, the region A, which is essentially in the core of the distorted sector, you will notice that the shock wave is detached. So you can see here the dotted line indicates where the location of the oblique shock is. It is a detached shock there. The interaction between the shock and the leakage vortex in this region happens to be weak. Whereas if you look at the region which is just outside the distorted sector, which is sector B, the oblique shock is attached, it is closer to the leading edge, and there is a stronger interaction between the leakage vortex and the oblique shock, resulting in increased blockage. and you move further to the other sectors, the sector C, which is the undistorted sector, as well as the sector D, which is where the distortion is just beginning, you will see that the way the leakage vortex and the leading edge shock interacts are quite different. And each of this sector does have a different effect on the way the compressor is going to behave. So let me, and if you look at the way the shock wave is a little more closely, we also notice that the shock angle itself is different between the distorted sector versus the undistorted sector, and that also gives us significant clues as to what is likely to happen when this shock wave interacts with the leakage flow downstream. So I hope the animation is coming through given the bandwidth. So what we tried to do as we did an unsteady RANs to understand how these different behave, and as the blade approaches the distorted sector and as the blade leaves the distorted sector, how the distortion sort of behaves. So we get an idea as to how the breakdown of the leakage vortex happens when the interaction between the leakage vortex and the shock wave is strong, versus when the flow is in an undistorted sector, the leakage vortex and how it sort of moves through the passage is something that we can visualize in time. So we do see that in the undistorted sector, over a period of time, the blockage sort of grows in time to an extent that it starts forming patches of what are called stall cells, which eventually cover the entire annulus of the compressor, resulting in onset of the instability. So that was sector A and C versus D and B. So without spending more time on this, I essentially wanted to highlight the fact that the interaction between the leading edge shock versus the leakage vortex is a strong function of the quality of the flow that the compressor is going to face. So distortion is indeed going to have a very significant effect on the way in which the leading edge shock wave interacts with the leakage flow. So that was rather recent work that it's still ongoing, and I would like to go a few years past, sometime around 2007, 8 to 9. That was the time we started looking at instabilities in a little more detail. One of my first PhD students who was working at that time looked at instabilities in a low-speed compressor, and also to try and sort of figure out mechanisms by which we can control these instabilities. So this is a test facility we used to have in those days, which has undergone a lot of changes now. And using casing-mounted Q-light transducer, we had the unsteady pressure traces, and using the pressure data, we came up with a mechanism by which we can inject air from the casing to see if we can energize the casing boundary layer and prevent the instability. So you can see the actuators here close to the leading edge, and we had a feedback control mechanism which helped us in delaying stall by a certain amount of time. So before I go into that, the nomenclature that we've used, this is there are two types of disturbances that we are interested in. One is what is referred to as a long length scale disturbance, LLSD, which is when the disturbance covers about 40% or more of the circumference of the fan. And if it is less than that, this is referred to as short length scale disturbance. So this is a nomenclature which around the late 90s, a lot of work happened where people have come up with this kind of a nomenclature for these disturbances. So when we started this work in those days, we had these pressure traces, and just based on visual inspection of the pressure traces, it was becoming very difficult for us to make much sense out of the data that we had. And so around the late 90s, also saw that there was a lot of work on trying to use better methods of signal processing to see if we can make better sense out of this data. So one such tool that we came across, which was very interesting and useful, was wavelet analysis. So we used wavelet analysis in those days back in 2009 to convert the pressure traces into a frequency spectra. And from this, we found that we could indeed get better information about the stability mechanism and the onset of those. So from the frequency spectra, we could identify the short length scale disturbances that you see here, as well as long length scale, and infer what causes the onset of these instabilities. And based on this, we came up with a mechanism to control these instabilities. As you can see here, this is the pressure trace, and we see the disturbances beginning to grow, which is when, if this is allowed to continue, we would have the onset of instability that you see here. So using the casing injection, we could delay the onset of stall, and that was essentially through our understanding of instability through the wavelet analysis. Let me skip this in the interest of time. And the other interesting thing that we worked on is on casing treatment, which essentially looks at what we did in the previous study was to externally inject air. Casing treatment uses air which is already there in the flow downstream where the pressure is higher, divert it in an efficient manner upstream to energize the flow. So this is already used in Eurofighter, in one of their the military jets. Problem with this is efficiency penalty. So we had a fairly long collaboration with NAL Bangalore, where we developed quite a few innovative casing treatment methods, which not only improve the stability margin, but also without the loss of penalty, which is rather unique in terms of the other contemporary work which has happened so far. So this is the geometry which was developed, which promises fairly substantial stall margin or stability margin improvements with little loss in efficiency. And what it does is basically there is a chamber here which is upstream above the compressor blade itself, which efficiently diverts the flow from downstream to upstream without too much loss in efficiency. So we see that we can actually shift the stall frequency, and the amplitude as well as the frequency is shifted substantially with the use of these casing treatment geometries. So what was done here was essentially the fact that the flow from the downstream is diverted through the plenum above the casing through these slots which we had carefully optimized without the loss of efficiency. So this is something that has resulted in improved stability of the compressor with minimal loss in efficiency. In fact, in some configurations, we actually see about 1% improvement in the efficiency. So moving on, I would also talk about some aspects pertaining to blade shape modifications that we did as part of our study. We have also come up with some innovative blade shapes that you see here, which are relatively less sensitive to tip leakage flow effects and losses thereof. So that's some work we did a couple of years back. And some of the recent work, I'll spend another 4 to 5 minutes highlighting some of the recent ongoing work. This is a picture that you saw in the very first slide, which is an open rotor demonstration, which is currently underway in Europe, which promises substantially higher fuel efficiency. So we have been doing some work in contra-rotating fan for some time now. And some of the recent work where you can see the blades mounted here, the rotors rotate in the opposite direction. We started this work about 7-8 years back. We had some initial work on various inflow conditions on a high aspect ratio fan. And we have now developed a new fan, which is a medium aspect ratio fan, and trying to continue our work on stability analysis in this. So here again, if you look at the unsteady pressure traces at different rotational speeds, depending upon the speed of rotation of both the rotors, the stability mechanisms could be quite different, and that's something that we have attempted as part of the ongoing work. So we observe that if you change the rotational speed of either of the rotors, the instability inception could change from a long length scale weak strong to a weak long length scale depending upon how the rotors are rotating. So what we have seen is that if the downstream rotor rotates at a higher speed, it allows the stability margin to be of the compressor stage to be better would be if they were all rotating at the same speed. So we have also done some analysis of the leakage flow and the mechanism of this thereof, and I will not really go into details of this. So the wavelet analysis, we have made further improvements from what we did in 2007, 8, 9. We have a much better understanding of how we can use wavelet analysis to infer the inception of instabilities in these kind of applications. So the other ongoing work is on tandem blade. In fact, a lot of work has happened in IIT Bombay long back. Professor Saha, who is in the audience, I believe, had done a lot of work in tandem blades long back in the 90s. And we have now extended much of this in terms of understanding of the placement of the tandem blade. So this is how a traditional blade would be, a single blade. A tandem blade is basically splitting the blade into two so that the flow from the pressure side can leak into the suction side and energize the flow on the suction surface. So that is the basic concept of tandem blades. So current work involves understanding the flow physics as well as eventually extending it to a contra-rotating situation. So combination of the previous work as well as a tandem work. So the test rig that we have currently looks at how we can optimize various parameters ranging from the spacing between the blades as well as the axial overlap and so on. So what we see here is a very interesting flow physics. This is a single rotor that would normally see the leakage flow from the pressure surface to the suction surface. We also notice that there is a scraping vortex here, an enlarged view is shown here. And in a tandem, of course, we have not been able to locate a scraping vortex because of the fact that the chord is much lower than what it would be if it was a single blade. So scraping vortex is absent in a tandem blade, and therefore the associated mechanism of interaction of the scraping vortex with the leakage vortex is absent in a tandem blade. We have also looked at how the various clearances of the front blade versus the aft blade can influence the interaction between the leakage vortex from the front blade with the leakage vortex from the rear blade. So unlike a single blade where there is just one leakage vortex, in a tandem blade you will have a leakage vortex from this blade, you will have a leakage vortex from the second blade. One would also have a flow which is coming from the passage itself. So there is a very complex interaction between these three different flows which one would see in a tandem blade. So this work is still ongoing, and one of my PhD student is currently working on this as well. So before I go to the last slide, I would also like to highlight one aspect pertaining to not just the compressor, but a component which comes downstream of it in the engine configuration that we saw in the very first or second slide, that the flow from in a bypass turbofan, a part of the flow goes into the core of the engine, what you see here as the red path. And this is a duct flow which derives its flow from the fan. And so instabilities from the fan can also get transmitted towards the downstream component to the further stages downstream. So we are also trying to understand how the instabilities can get carried through the duct to the downstream stages. And what we have seen is that depending upon how you do the analysis, much of it can get attenuated. If you just use a radial profile, this is what you get at the station. Whereas if you do a steady RANS versus unsteady RANS, the amount of information that is actually translated downstream could vary depending upon what kind of analysis methodology is used for the kind of study that is being done. So this is something that also we have done in the recent past. So in the interest of time, I will go to my concluding slide here. As I said in the very first slide, This is a very interesting and challenging area because we are looking at components which are already nearing its peak performance. Turbine efficiency is close to 95, compressor close to 92, component efficiencies. Scope for further improvement is going to be incremental. That is already known, but those incremental performance improvements are also important from the aviation perspective. So stability of a compressor, as we have seen, is very sensitive to the tip clearance flow and how it interacts with the leading edge vortex or the non-uniformities that you can see. So that the complex interaction between them plays a very important role in the overall physics governing these flows. And the presence of non-uniformities, as we have seen, further complicates the already intricate flow physics in these kind of applications. So ongoing work as well as future work will essentially look at some of these unconventional concepts like tandem or contra-rotating casing, many more as well. The mechanisms are yet to be fully understood, and I think there is enough scope to understand our the complicated flow physics in these kind of flow situations even better, and that's where we are headed in the years to come. So the takeaway message is that a better understanding of instabilities can possibly lead to better design strategies, and that's very important for future aero engine technologies which are going to come up, and that's where this incremental improvement will indeed play an important role in the performance of the engine itself. So with that, I would like to stop here, and thank you very much for your time and patience in hearing me out. Especially post-lunch session is always a challenge, and I would be happy to take any questions that you may have.
Thank you very much, Professor Pradeep. I extend a big thanks to you on behalf.
Yes, sir. Yeah.
Hello. Hello.
Good afternoon, everyone. We are starting this session on fluid structure interaction. This session will be shared by Professor Amresh Dalal from IIT Guwahati. I request Professor Dalal to please start this session.
I welcome you to this session on fluid structure interaction. So first paper is paper number 47. So I request the organizer to play the video, then we will take the questions from the audience. And I request audience, if they are having any question, please raise your hand. Thank you.
Researchers, our work is on the bistable flow-induced vibration characteristics of a D-section cylinder. Flow-induced vibrations are caused primarily by two governing mechanisms: vortex-induced vibrations and galloping vibrations. Galloping leads to much higher vibration amplitudes as compared to VIV. Recently, significant studies have been carried out on the development of efficient energy harvesters based on flow-induced vibrations, like vortex-induced vibrations for Aquatic Clean Energy Project, a water-based energy harvester, and wind-induced flutter energy harvester project, an air-based energy harvester. Barrero Gill have one of the significant contributions in exploring the energy harvesting potential from galloping. Zhao observed a vibration amplitude of 4 diameters for a D-section cylinder. However, Dyke and Lanewell observed a requirement of minimum angle of attack for onset of galloping. Therefore, a study is performed to investigate the FIV response of a D-section at high reduced velocities, where possible low angles of attack may be present. The D-section cylinder is elastically mounted in a flow of Reynolds number 200. The structural system is allowed only to vibrate in the transverse direction to the flow with a mass ratio of 10 and damping ratio 0.01. The Reynolds number is based on the structural diameter and the flow velocity. The mass ratio is defined as the ratio of structural mass with respect to the mass of fluid displaced. The damping ratio is the ratio of damping coefficient with respect to the critical damping coefficient. The reduced velocity is calculated with respect to the structural natural frequency. The table shows list of the non-dimensional and dimensional parameters used in the present work. Most of the symbols are used only in the article and not in the presentation. Later, the required galloping characteristics are investigated using Den-Hartog galloping criteria. The fluid domain governing equations include the continuity equation and the Navier-Stokes equation. The single degree of freedom elastically mounted structure can be modeled using structural vibration equation. The no-slip boundary condition is imposed at the fluid-solid interface. A sharp interface immersed boundary method based in-house solver is used to solve the coupled fluid structure system. The solver was initially developed by Mittal and co-authors at Johns Hopkins University and later extended for VIV and thermal buoyancy characteristics by Garg et al. The domain is divided into structural cells, fluid cells, and ghost cells. The image point is calculated as the mirror image of the ghost cell center about the structural boundary. The velocity at the ghost cell is imposed as equal in magnitude and opposite in direction with respect to the velocity at image point, thus satisfying the no-slip boundary condition at the interface. Based on the previous studies utilizing the in-house solver, a domain size of 47 diameters in x direction and 30 diameters in y direction is used, with minimum grid size of 0.02 diameters near the structure. A constant inflow velocity is imposed on the left wall. A fully developed boundary condition is imposed on the right wall. The free slip boundary condition is imposed on the top and bottom wall to simulate the open domain vibration system. The structure is placed at a distance of 15 diameters downstream and 15 diameters above the bottom left corner of the domain considered. Several verifications have been previously performed on an in-house solver, including the VIV characteristics of a single cylinder. This indicates a different excitation mechanism. Some of the recent studies on D-section structures have shown the presence of galloping vibrations for the structure. Therefore, a galloping tendency study is required for understanding the galloping behavior of the structure. The Den-Hartog galloping criteria is used to study the galloping tendency of the structure. The structure is studied for changing angles of attack of flow from 0 to 20 degrees as a result of transverse velocity of the structure. The magnitude of apparent flow is the vector sum of incident flow velocity and structural transverse velocity. The change in lift and drag coefficients is used to calculate the gradient of structural force with the angle of attack. The negative regions correspond to the negative damping introduced into the system and induced galloping vibrations. For angles of attack smaller than 8 degrees, the structure has no galloping tendency and therefore a minimum transverse velocity or the critical velocity is required to induce the galloping vibrations into the system. As indicated by the galloping tendency study, the maximum velocity of the structural vibration attained during the cycle decides the maximum angle of attack induced during the cycle, and a minimum 8-degree angle of attack is required for inducing galloping vibrations in this particular D-section structure. Therefore, the maximum velocity attained by the structural system at various reduced velocities is compared. The black line corresponds to the critical velocity corresponding to the 8-degree angle of attack responsible for inducing galloping vibrations. As evident from the plots, the desynchronization at higher reduced velocities is due to the inability of the structure to attain critical velocity of structural vibrations. When the initial excitation is provided to the structure, the critical velocity is attained due to the extra energy provided by the initial excitation, and therefore self-sustained galloping vibrations are induced. To summarize, we studied the D-section FIV response in a RE200 flow for mass ratio 10 and damping ratio 0.01. The structure exhibits galloping vibrations at reduced velocity less than 10, irrespective of initial excitation present or absent. The bifurcation into two stable vibration states is observed with variation in initial excitation conditions. The galloping tendency study predicts a minimum angle of attack for inducing galloping vibrations. At 8 degrees, at high reduced velocities, the fluid structure system is unable to attain the required angle of attack due to reduced velocity of vibrations, and therefore undergoes galloping vibrations only after getting a sufficient amount of initial excitation. Thank you for your time. Are there any questions?
Now I request from the audience to ask any query if you have. Hello, is there any query on this presentation? Hello, is there any query from this presentation? Hello, is there any query from this presentation? Okay, thank you. Now I request the volunteer to display the next presentation.
Sir, a MS scholar from Department of Mechanical Engineering at IIT Madras, working under supervision
Hello?
of Silicon theory.
Yes, I were playing the video.
Today I am going to discuss effect of blockage and mass ratio on vortex-induced vibration of a square cylinder. Let's move to next slide. These are the outline of my presentation, and I'll follow the same order throughout the presentation. Flexibly mounted block body in a flow can undergo structural vibration due to periodic vortex heading in the way. This is known as vortex-induced vibration, as shown in attached video. The BIB of block bodies has been studied extensively due to its practical importance in various engineering applications. For example, it is important in design of offshore structures such as riser tubes and subsea pipelines. And the heat exchanger tubes can undergo vibration due to BIB. It provides another method of power extraction from flow energy. Objective of present study is to study the effect of blockage and mass ratio on weight unsteadiness, force coefficient, and cylinder response in transport direction. Figure 1 shows two-dimensional schematic of computational domain for vortex-induced vibration of an elastically mounted square cylinder confined in a rectangular channel. Square cylinder of side D placed at a distance of 10 d from inlet. Length of computational domain taken to be 35.5 d. Parabolic velocity profile has been implemented at inlet. No slip and impermeable boundary condition has been applied on cylinder and top and bottom wall. In present study, square cylinder flexibly mounted and cylinder movement restricted to move only in transport direction. Structural damping is considered to be very small and may lead to large amplitude vibration. Figure 2 shows grid distribution around the cylinder. Grid has been generated using commercial software ANSYS ICMCFD 18.1. Structured quadrilateral mesh has been created in a rectangular box near the cylinder, while triangular mesh is generated in rest of the computational domain. The mesh moving scheme is selected in such a way that the rectangular structure mesh moves along with cylinder and unstructured mesh deforms and remeshes after each time step. In the previous slide, we discussed about parabolic velocity at the inlet. Here equation 1 is and whereas image is maximum velocity at the inlet, maximum velocity at the inlet, and y is y distance from center, and h is the height of the conformation. The resolution can be defined as equation number 2. Blockage ratio can be defined as the ratio of side of cylinder to the height of the channel. Blockage ratio takes value of 0.05, 0.0, 0.17, and 0.2. Whereas mass ratio is the ratio of mass of cylinder to the mass of displaced phase. In present study, the value of mass ratio is considered to be 2.5, 5, and 10. In the present study, continuity momentum equations have been solved for the fluid flow, whereas equation of cylinder motion is solved for the movement of cylinder. To solve above drawing equations, finite volume based commercial software analysis equivalent 18.1 has been used. Simple algorithm has been used to resolve coupling of pressure and velocity, and shift the integral freedom solver has been employed to solve equation of cylinder movement. Grid and time independent study has been carried out to optimize computing cost and to confirm temporal accuracy. For grid independent study, different grid distribution around the cylinder and near cell size has been considered. Now, where the optimum value for number of grid around the cylinder was found 160, and the nearer grid size found to be 0.005 D. Whereas optimal time step was found 0.00. To confirm accuracy of present numerical schemes, the validation has been carried out considering same geometry and flow condition are reported in Sen and Nickel. The values of maximum amplitude of oscillation, mean the coefficient RMS value of CL, and Stroll number has been compared with values reported in Sen and Nickel, and it shows good agreement with the reported value. And these schemes have been used throughout my numerical study. Figure C illustrates what is the contour of different value of blockage ratio and mass ratio, and Warren-Kerman and vortex strip have been observed. Size and shape of vortices have been affected with further increase in blockage ratio from 0.1. The effect is significant for mass ratio equals to 5 and 10 at blockage ratio equals to 0.2 as depicted in figure 3D. The figure 4 depicts transfer velocity signal in the wake of oscillating cylinder for different value of blockage ratio and mass ratio. Signals are more or less harmonic. However, their amplitude changes with change in blockage ratio. It was observed that very constantly oscillates with increase in blockage ratio for mass ratio equals to 10, resulting in a decrease in signal amplitude as illustrated in figure 4C. Effect of blockage ratio on Stroll number for different values of mass ratio has been depicted in figure 5. As blockage ratio increases from 0.05 to 0.1, the Stroll number decreases slightly and then increases with further increase in blockage ratio for all the values of mass ratio. The increase in Stroll number is also apparent from vorticity contour as streamwise distance between vortices decreases. Figure 6 shows variation of maximum amplitude of vibration with blockage ratio for different values of mass ratio. For mass ratio equals to 2.5, maximum amplitude of vibration first decreases with increasing blockage ratio for 0.05 to 0.1, and then increases with further increasing blockage ratio. Whereas for mass ratio equals to 5 and 10, maximum amplitude of vibration decreases with increasing blockage ratio. Maximum value of Ymax observed for mass ratio equals to 2.5 and blockage ratio equals to 0.2, whereas minimum value of Ymax observed for mass ratio equals to 10 and blockage ratio equals to 0.2. Variation of mean drag coefficient and RMS of RMS value of lead coefficient with blockage ratio corresponding to each value of mass ratio have been depicted in figure 7 and 8. Here, mean drag coefficient decreases with increase in value of blockage ratio from 0.05 to 0.1, and then increases with further increase in blockage ratio for mass ratio equals to 2.55 and 10. Difference between mean drag coefficient is insignificant for mass ratio equals to 2.5 and 10 up to blockage ratio equals to 0.17. And in figure 8, it can be observed that CLRMS decreases monotonically with increasing blockage ratio for mass ratio to 10.
Similar purpose.
For all the values of blockage, whereas CLRMS is minimum for mass ratio equals to 5 for all the values blockage ratio. These are the conclusion of my parent study. For mass ratio equals to 10, wake unsteadiness gets suppressed with increasing blockage ratio, and size of vortices reduces with increasing blockage ratio for each value of mass ratio. Maximum value of mean drag coefficient and RMS value of lead coefficient have been observed for blockage ratio equal to 0.2 and mass ratio equals to 2.5. Maximum amplitude of oscillation has been observed for blockage ratio equals to 0.2 and mass ratio equals to 2.5. For mass ratio equals to 10, maximum amplitude of oscillation decreases monotonically due to suppression of wave unsteadiness with increase in blockage ratio. It has been observed that for mass ratio equals to 2.5, amplitude of vibration is enhanced with increasing blockage ratio, whereas for mass ratio equals to 5 and 10, amplitude of vibration gets suppressed with increasing blockage ratio. So from above observation, it can be concluded that it is not advisable to use a body of low mass ratio value and square cross section shape inside a channel with high blockage ratio. These are the references that I have used in train study. Thank you.
Thank you. Now I request the audience to ask for any query if they have.
Yeah, sir,
Hello?
I have a question. Hello.
Please.
Yeah.
Please.
So, what type of boundary conditions you used for velocity at outlet?
The velocity at outlet considered to be like it is symmetry boundary. Hello. Zero gradient velocity has been, yes, like zero gradient velocity has been considered at the outlet of outlet.
So, have you tested this convective boundary condition for outlet? Because the convective boundary condition is more suitable than other boundary conditions for these types of vertex setting closure.
That comes with this. Pardon, sir, can you repeat?
My question is that have you tested this convective boundary condition at outlet?
No, sir, I am not. I'm not.
Because convective boundary condition actually is more suitable than other boundary conditions for the types of vertex setting flows. Hello.
Yeah. Good afternoon, sir. This is Prashant, one of the co-author of this paper. So I just want to extend whatever my presenter has said. Like, we have not yet tested the convective boundary condition, but in the present study, the domain length that we have considered in the streamwise direction, that is sufficient, and we have referred to the journals that they have considered pressure outlet boundary condition for a particular domain. So domain length is such a high distance or such higher length that its effect, pressure outlet boundary condition would have negligible effect on the vertex setting. So that we have referred different papers. On that basis, we have selected.
So your basically physical domain is finite or this infinite length?
Finite length, sir. Finite length.
Oh, your physical domain also finite length.
Okay. Yes, sir. Okay. Yes, sir.
One more thing. How you solve these governing equations? I mean, you use this simple algorithm.
Yes, sir. Simple algorithm. Yes, sir.
So simple algorithm, basically you discretize the equations and write the code or something else. I mean.
No, it is in Fluent. We have solved in Fluent.
Okay, so all the things are implemented in Fluent software. Eh?
Yes, sir. Yes, sir. Correct, sir. Yes, sir.
So what's your input from to this software while solving?
Yeah, we have used our own UDF. That is the user defined function for the vertex induced vibration. And then we have validated, and whatever the study that we have carried out that is not present in the literature. So it is extension of the previous studies, we can say.
Oh, okay.
Yes.
Okay, fine.
Thank you, sir. Thank you so much, sir.
Okay, presenter, I have one or two questions. Okay. Now, why did you carry out your study at Reynolds number 100? Hello?
Yes, sir. Like, I want to study this at Reynolds number 100 because I want to I start this with Reynolds number 100 with this effect can be observed for higher Reynolds number also. So in order to check whether this kind of effect is available at low Reynolds number, and then moving to the higher Reynolds number will be easy.
Okay. Yeah, sir, something I want to add, whatever my presenter had said, the R equal to 100 that we have considered is due to the main motive of the present study is to study the effect of blockage. So not the effect of Reynolds number. So we are studying the effect of blockage, and we have considered an infinitely long cylinder. So at R equal to 100, flow is 2-dimensional. It is not 3-dimensional. So if we go after 150 or 200, the flow will be 2-dimensional. So there will be a transition. So we have taken a safe value at R equal to 100 such that the flow will be 2-dimensional, and blockage effect will also not cause any kind of 3-dimensionality in the flow domain. Thank you, sir.
Okay. Now my second question is, you have chosen some 4 different blockage ratios, correct? Hello?
Yes. Yes, sir. Yes.
In your study, you have selected some 4 different blockage ratios. What are those blockage ratios?
Yes, sir. 0.05. Yes, sir.
0.05 and then?
0.1, then 0.17 and 0.2.
No, 0.17 and 0. The second one. How did you arrive at this blockage ratio? On what basis?
I just took it with increasing blockage ratio. There is no reason for selecting these blockage ratios, but I just to study the effect of blockage ratio, I just took some the step values like 0.05 to 0.1, like it is double, and then 0.17 and then 0.2.
No. Is there any logic?
Sir is asking that what is the definition of blockage ratio in your case?
Yeah. It is like D by L2, a characteristic length of the cylinder divided by width of the domain.
Yeah, that's fine.
Okay. No, but that 0.17, how did you? Why did you choose 0.17? That's what my question is.
Yes, sir. I got your question. So L2 that have been considered in the most of the study like 16D, somewhere it is 12D, somewhere it is 10D. So we have considered a range. I think Sambit has considered from 10D or 8D to 20D. So all the ranges we have covered in this, and we have seen how the blockage is affecting our flow characteristics. So whatever it is in literature below also and above also, both the values we have considered. L2 value, that is width of the domain.
That means you wanted to validate your work that reported in the literature, correct?
No, literature, they have not done any study on the effect of blockage ratio. They have studied the flow characteristic considering fixed L2, that is fixed width of the domain. In some of the literature, you will see L2 equal to 10D, somewhere it will see that L2 equal to 12D, in some literature it may be 16D, in some literature it may be 20D. But we don't know how the blockage is affecting, that is not yet reported. They have considered a fixed value of L2 for a particular study in a particular literature.
Okay. The third question is in the conclusion, the last point you have written that it is advisable to go for higher blockage ratio, correct?
No, it is not advisable to like use. Yes,
you said that
it is
in
not
the last
advisable
point
to use.
It is not advisable.
Yes, sir. It is not advisable to use this lower mass ratio bodies in higher blockage ratio.
Okay.
Why? Because its frequency will be very high and this amplitude of vibration will be very high, which any structure we need to avoid that kind of vibration and frequency.
Okay, thank you. Thank you.
Thank you so much.
Is there any other question from the audience? Is there any other question from the audience? Is there any other question from the audience? Okay, thank you very much, the author and the presenter and the co-author. Now I request the volunteer to display the next lecture.
This is Dr. Ganesh. I've joined.
Oh, you have joined?
Yes.
Okay, thank you. Continue.
Okay, sure, Professor.
Okay, thank you.
Configurations of cylinders using proper orthogonal decomposition. I am Parashuram, and this work was done with the guidance from Dr. Anubhav Sinha. I shall first introduce you to the topic of our work, along with a brief information about the previous work by other researchers on this topic, the novelty of our work, followed by the modeling details, the results which we have obtained, and finally the conclusions drawn and the references cited. Flow past a cylinder and various arrangements of multiple cylinders have been a subject of interest to a lot of researchers in the past due to its applications. And a large number of these depend on the wake structure. Thus, the determination of wake structure is a subject of particular interest. In the current study, two configurations of cylinders have been examined, the side-by-side cylinder and the oscillating cylinder. In the case of the side-by-side cylinder, the separation distance was varied, and in the case of the oscillating cylinder, the oscillation amplitude was varied. Previous research on the side-by-side cylinder setup was performed by many researchers including Wang and Zhou, who presented experimental observations on the three regimes of wake behavior, Supradeepan and Roy, who presented numerical results on the effect of separation distance between the cylinders, Karini and others, who have observed flip flow instability for very low separation distances, Leo and Jaiman, who presented DMD of vortex-induced vibrations of flow past side-by-side cylinders, and Kun and others, who have presented numerical results of wake structures for different separation distances. Moving on, in the case of oscillating cylinders, previous research by Carberry and Sheridan presents the experimental observation of transition in wake structure with increase in forcing frequency. The work by Gulminov and Quetti presents numerical results of shedding patterns for different forcing frequencies. The work by Kim and others presents LES of turbulent flow with different forcing frequencies which are close to the Kármán frequency, and other researchers such as Ongoran and Rockwell and Liu and Dalton. Although significant work has been done on each of these configurations independently, the aim of this study is to present a comparison of these two configurations. What is of interest in this study is to compare these two configurations which have been studied independently so far. The wake structures are compared using POD modes, and analogies are drawn between the oscillation amplitude for the oscillating cylinder case and the separation distance from the side-by-side cylinder case. The pictures presented here depict the computational domain used for this study. The left picture depicts the side-by-side cylinder case and the right picture depicts the oscillating cylinder case. A velocity inlet boundary condition is used on the left edge, slip wall condition on the top and bottom edges, and pressure outlet boundary condition on the right edge. The cylinder is a no-slip wall boundary, and in the case of the oscillating cylinder, the center of the cylinder is sinusoidal motion, which is presented in the slide. A laminar unsteady pressure-based solver is used, and the Reynolds number is 100 based on the cylinder diameter for both the configurations. Further, grid independent study was conducted and the details are presented here. The picture shown in the slide corresponds to the lift coefficient on the top cylinder for the 5D spacing case of the side-by-side cylinder configuration. Moving on to the results of this study. The figure shown in the slide presents the mode energy content of different modes for the side-by-side cylinder configuration on the left and the oscillating cylinder on the right. It can be observed that the rate of decrease in energy with the mode is rather steep for the 5D spacing case for the side-by-side cylinders, and it decreases with the spacing. In addition, while the rate in 2.5D case is somewhat closer to the 5D case, it is quite different compared to the 1.3D case. In the case of oscillating cylinder, the rate of decrease of the two cases studied is close and similar to the 2.5D and 5D cases of side-by-side cylinder. Comparing the modes of different spacings of side-by-side cylinders, it can be seen that the 1.3D case exhibits strong interactions, 2.5D case exhibits moderate interactions, and the 5D case exhibits weak interactions. And in the case of the oscillating cylinder, the A0.75 case represents an oscillation amplitude of 0.75 times the cylinder diameter, and similarly the A1 case represents an oscillation amplitude equal to the cylinder diameter. It is observed that the wake structures from both cylinders have strong interaction for 1.3D case, moderate interaction for 2.5D case, and almost no interaction for the 5D case. This behavior is further confirmed by higher modes. For 1.3D, Mode 1 and Mode 2 show stream of vortical structures formed by the combined influence of both the cylinders. Mode 3 shows two different vortical structures, but they too have a strong interaction. On the other hand, the vortical structures formed by both the cylinders in the 5D case appear to remain independent. Almost no interaction between the stream of structures is observed till Mode 3. The separation of 2.5D being an intermediate separation between 1.3D and 5D shows intermediate behavior. The vortical structures formed interact, but to a lesser extent than the 1.3D case and a greater extent than the 5D case. The difference in behavior of vortical structures in these three cases can be attributed to the difference in separation distance between the cylinders. As evident, the case with the largest separation distance, that is 5D, shows independent vertical structures, while the case with the smallest separation, that is 1.3D, shows highly interacting structures. Coming to the oscillating cylinder case, as can be observed here, the A0.75 case forms two different structures which do not interact among themselves, while for the A1 case, the two vertical structures formed show a strong interaction. This difference in behavior can be attributed to the difference in speed of cylinder motion. A1 has oscillations with a higher amplitude while the frequency of oscillation is same for both the cases. Hence, A1 has to move faster to cover larger distance at the same time. This difference in speed gives rise to a difference in vertical structures. This trend appears to be analogous to the side-by-side cylinder case discussed previously. A0.75 case is observed to behave similar to 5D case, while the A1 case appears to be analogous to the 2.5D case, especially in near cylinder region. It is intuitive to assume that the cylinder with larger amplitude of oscillation will behave similar to the cylinder separated by larger distances for side-by-side cylinder configuration. On a concluding note, numerical simulations have been performed for flow-pass side-by-side cylinders and transversely oscillating cylinder, and the wake structures were captured using POD. These POD modes help in comparing and understanding the wake structures of these two configurations. For the side-by-side cylinders case, the 1.3D case exhibits strong interaction, 2.5D case exhibits moderate interaction, and the 5D case exhibits weak interaction among the wake vortices. On the other hand, in the case of oscillating cylinder, the A1 case exhibits moderate interaction, which is similar to the 2.5D case of the side-by-side cylinders, and the A0.75 case exhibits weak interaction, similar to the 5D case of the side-by-side cylinders. Hence, the separation distance forms the analogous parameter for speed of oscillation of the cylinder. These are the references which were cited in the paper.
Okay. Any questions from the audience to the speaker? Questions from the audience on the presentation to the Okay, I have a couple of questions. This is Ganesh from IIT Palakkad, and I just wanted to know what further conclusions could you draw from these results? For instance, it is quite well known that if the separation distance between the cylinders is large, the wakes wouldn't interact and the cylinders would actually behave as if they were independent. So does it really require a POD analysis to bring out the fact that there will be a stronger interaction when the cylinders are closer and a very weak interaction when the cylinders are farther apart? Is it really required to do a POD analysis to gain this information?
So, Dr. Ganesh, I'm Anubhav here. So basically, the focus is not on the three side-by-side cylinder. The focus is to compare side-by-side with oscillating cylinder. Okay, so we know that we know how these structures behave, but how the POD modes compare and what additional information we can extract. So that was the objective.
Okay, but are the modes similar between, let's say, oscillating cylinder and side-by-side cylinder? Because I didn't seem to see any comparison of the modes, similarity in the modes.
Yes, so if you look, okay, I think because the results was presented on different slides, if you look at, if you refer to the paper which is submitted, so you can see that there is some similarity, especially in the near wake, near the cylinder region, we can see some similarity between oscillating and side-by-side cylinder.
Okay, so you are therefore you are using that to conclude that there might be the amplitude of oscillation could be used in a way similar to the separation distance between the side-by-side cylinder. Am I right?
Yes. Yes, correct.
Right. Any other questions for the speaker?
Hello.
Yes.
Hello.
Yes. Hello.
I have one minor doubt. Why you are using the term side-by-side cylinders? It is not clearly saying anything unless you see the diagram. Can there be a better nomenclature for this? Side-by-side cylinders, when you say it is no, yeah.
We could have said in tandem also, but generally literature people refer to this name, side-by-side cylinder.
Yeah, no, you can improve the name. What is that? You can always improve the name. You need not stick to what is written in the literature. But when you say side-by-side cylinder, it is very difficult to understand. You can write something else, maybe tandem, oriented towards the flow, something like that. Side-by-side can be this way also. One behind the other also. One behind the other is also side-by-side. Correct? No, this is just a suggestion. Okay.
Thank you. We'll keep that in mind.
Any other questions from the audience? Any other questions? Okay. If not, let's thank the speakers and move on to the next presentation.
Thank you.
Thank you.
Hello.
Welcome everyone.
Hello.
Hello.
Yes, Professor.
Let me ask one more question. What is the future direction of this work?
I think
they left.
So basically, we are trying to explore more of the effect of this frequency and oscillation. So we are planning to explore how this oscillating cylinder behaves, and then we'll also compare with side-by-side cylinder. But the focus will be on oscillating cylinder.
That I understand, but in future, what is your plan?
So
after this, how you are going to extend the work? That's what I'm asking.
So that's what I said, that we have in this paper we have presented only two frequencies, two oscillation amplitudes. So now we are looking into different frequencies and a more different range of amplitudes for the oscillating cylinder.
Okay. Okay. Thank you. Thank you.
Thank you, Professor.
Let's move on to the next paper. Could you kindly play the video? Yeah.
Everyone, to the short presentation of our one of the recent research work. Our paper number is 107. The work is being entitled as Fluid Structure Interaction Analysis of Flow Through 3-Dimensional Hyperelastic Flexible Tube using OpenFOAM. Myself, Jijoderic Abraham. I am a junior research fellow from the Department of Mechanical Engineering at Visvesvaraya National Institute of Technology, Nagpur. These are the rest of our team members. We are being supervised by Dr. Trushar B. Gohil. Coming into the content of this presentation, the following aspect of the work will be discussed in this presentation. We'll be having a brief introduction followed by stating the objectives. Then we'll have a glimpse on the methodology adopted for this work. Then followed by a discussion on the results, and then summarizing the conclusions, and then acknowledgement. So coming into the introductory section, FSI in flexible tubes are encountered in a wide variety of biomedical cardiovascular conditions. Not only in cardiovascular conditions, you can see it even in many naturally occurring phenomena and even in many complex engineering problems. So specifically, if you consider the biomedical applications, you can see in there are some different cases. Like first one is a flow through a normal artery. Second one is a case of blood flow through some specific aneurysm cases, and third one is a case of flow through the atherosclerosis condition. In all these conditions, what we have to note is that we may require different mechanical constitutive laws to mimic these phenomena. So from literatures, what we have observed is most of the previous work concentrated on linear elastic tubes. And if you see the papers on the last decade, there has been some attempt to address the nonlinearity of these vessels using Saint Venard material. And the experimental studies reveals that the Neo-Hawkian and Mooney-Rivlin material models will be capable of will be able to mimic the flexible tube behavior in real world applications. So considering that aspect, we have set the objective of this study as the following. First one is we want to implement these hyperelastic solids in open form to do the FSI analysis. Then the second one is we want to compare the effect of this specifically 3 hyperelastic constitutive models, and namely Saint Venard, Neo-Hawkian and Mooney-Rivlin models on simulating a particular case of propagation of a pressure pulse through a 3D tube. Then we want to analyze the effect of Poisson ratio of these 3 constitutive models in analyzing the rate of change of volume in the fluid domain. Coming into the methodology, this is the general flow chart of the FSI solver in open form. So here we can say that this can be divided into 3 segments. Initially, we have a mesh solver, so that will deform the mesh. Then we have a section for solving our fluid domain. Then whatever we have found, the pressure and viscous stress will be transferred to the solid domain as in the form of traction. Then we solve the constitutive expressions for solid. Then we'll come up with some sort of displacement of the solid deformed domain. That displacement we'll be checking it with the fluid displacement. Then if it is too much, then we'll be under relaxing. If it is a convergent criteria, then we'll be moving on to the next time loop. So this you can say that this is a strongly coupled to partition approach that we have used in the current study. And considering the higher deformations in the case of solid, we have formulated the fluid governing equations in arbitrary Lagrangian form. That's why the velocity terms are expressed in with relative to the surface of the deformed cells. Then we have the governing equation for the solid, which is the linear momentum equation, where we are equating the momentum of the solid with the momentum caused by the traction as well as the bodily forces. Okay, traction is being represented in terms of a vector dot product of vector normal vector with the Cauchy stress. So we'll move on to the different constitutive models. So in this particular study, we have considered 3 constitutive models. These are the expression for the constitutive models. So in the case of Saint Venard, the second Piola-Kirchhoff stress is related to the green Lagrangian strain. Green Lagrangian strain can be related to the displacement and tensors as expressed here. So here this the third term represents the nonlinearity. Here the nu and lambda represents the Lane constant. The second Piola-Kirchhoff stress can be related to the Cauchy stress with the help of deformation gradient. Clearly, I have directly expressed the relation for Cauchy stress in the case of Neo-Hawkian and Mooney-Rivlin as follows. And here K represents the bulk modulus, and here A and B are the constants coming from the experimental field. So these expressions you can get more in-depth knowledge from the following references that I have listed here. Okay, this is the classic books on mechanics of solids. So coming on to the particular case of our analysis, we have a 3D tube which have a length of 0.05 meter and the diameter of 0.1 meter and the thickness of 0.01 meter. And here we have the interface where we supply the non-slip condition and the coupling in terms of velocity, traction as well as displacement. So the important point to note down is the boundary condition, that is the inlet boundary condition, that is a pressure inlet, and we are supplying the pressure of up to 0.03 second, then we are detaching it. So the pulse will be moving propagating over through it. And the other aspect we had to consider is the mesh, and we have used a conformal mesh. The green portion will represent the solid domain, blue portion will represent the fluid domain. These are the properties that we have used for the defined for the materials. For the fluid, we have defined the density as 1000 kilogram per meter cube. So solid, it is 1200, which means the density ratio is 1.2. And this is the kinematic viscosity and the Young's module we have considered. The Poisson ratio we have varied from 0.2 to 0.49. This whole test case, like in the flow condition and the boundary case, which this test case is initially used or we have adapted this test case from M.A. Fernandez and M.A. Bubashir. Then coming into the results and discussion section, this same test case was again used by J. Duroot, and they initially that test case was initially others used it for linear solid, but De Groot et al. Used it for non-linear Sen-Venard material. So we use that the transient deformation pattern that De Groot have plotted, and we have tried to match our transient pattern with that. And this is the pressure contours that we have obtained, and this is also similar pressure contours were plotted by De Groot. We tried to match with that, and our contours were matching exactly. Since the deformation is low, as in the case of De Groot, what we have done is we have magnified the displacement by a factor of 10, and then we have projected, we have presented the pressure over it. Okay, we have. Then moving on to the our results section, you can see that we have studied the effect of constitutive models. So we have combined the effect of 3 constitutive models. Even though it looks very closer in the overall figure, if you put some like localized zooming, you can see that the Monet-Rivlin material exhibit the higher rate of deformation, followed by Neo-Hawkian and Sen-Venard material. The other observations that we have to consider it is that the quantitatively, the time average rate of absolute change of volume for Neo-Hawkian and Monet-Rivlin models is 7.59 and 7.81% higher than the Sen-Venard material. Okay, so then we'll move on to the effect of Poisson ratio. What you can see is the change in Poisson ratio pattern is almost same in all the 3 materials, but however, changing it from 0.2 to 0.3 will not show any change in notable change in all these 3 materials in the most of the time of the cycle. However, but during between 0.04 seconds to 0.08 second, the 0.02 Poisson ratio will show a higher rate of deformation, and 0.049 will show a completely different behavior from the rest of the 2 Poisson ratios. Initially it shows a lower rate of deformation, then in the middle region it shows higher rate of wiggles, then even the rate of compression is higher in the case of Poisson ratio 0.49. A close quantitative observation reveals that in the case of Neo-Hawkian model, the increment in Poisson ratio from 0.02 to 0.3 and 0.3 to 0.49 results in average increment of 19.61 and 61.15% in the total deformation rate. Corresponding rate in the case of Monet-Rivlin is 28.54 and 62.52. So what you can observe is, even though it looks similar, in the case of Monet-Rivlin, Poisson ratio has more effect. So coming into the conclusion, we are able to simulate the 3D flexible tube using with the FSI of 3D flexible tube with hyperelastic material models using OpenFOAM. Then we observed that the rate of deformation is higher for Monet-Rivlin, followed by Neo-Hawkian and Sen-Venard material. And the Monet-Rivlin material exhibit a slightly significant change in the rate of deformation with the Poisson ratio. The changing in the Poisson ratio from 0.2 to 0.3 doesn't exhibit any notable change in the case of total rate of change of volume. However, Poisson ratio 0.49 exhibit a considerable variation in the deformation pattern. On an average, maximum rate of compression for Poisson ratios 0.49 is 25 to 28% higher than that of 0.29. We would also like to acknowledge Department of Science and Technology and Science Engineering Research Board for providing the fund for the computational facilities required to execute the current research work. And these are the remaining references. Thank you.
Yeah. Thank you. Questions, please. Questions for the speaker? Okay, I have a couple of questions. In the boundary conditions that you were showing, it
Yes,
appears
sir.
that you have given u equal to v equal to 0. I mean, is that right on the surface of the tube?
What, sir?
Because
Let me check.
the boundary conditions on the surface of the tube are set as u equal to v equal to 0. But the tube is allowed to, it's a flexible tube, right? So the surface of the tube would move with a certain surface velocity. So is the implementation of the Navier, I mean, the no slip boundary condition correct, or is it a typographical error?
See, actually, what happened in open form terminology, we'll be defining some sort of moving mode only. Like it's a topographical error. Actually, it's a coupled boundary condition there.
Okay, and that's fine. So it's essentially a no slip boundary condition, but it appears that in the presentation it's not written as u equal to us v equal to vs. Rather, it's written u equal to 0 v equal to 0. I think that's what led to the confusion. And secondly, when you say dv by dt, yeah, you are referring to the rate of, I mean, the time rate of change of volume.
Yeah, the entire volume of the liquid domain.
In the tube, right? Okay.
Yeah,
fine.
Under
in the
volume.
tube. Okay.
Yeah.
All right. And could you also shed some light on how you have done the FSI, the coupling? I mean, could you mention something? Because
coupling or implementation of hyperelastic materials.
Right.
See, actually, in open form, you have that provisions for different, like the solver have different modules for fluid and solid. Implement like similar a template, and you can do you can change the expression for it. That's what I have done.
Yeah, that I understand. But could you tell us as to which terms were added in the? I mean, there's a coupling between the fluid and the solid, right? So the constitutive model, solid constitutive model should affect the fluid.
Anyway, these don't things won't come in the coupling. It will come in the solid part of the like solver.
Yeah, but how is the solid solver coupled to the fluid?
See, that's what I'm saying. Coupling is done in a different way, but you have that provisions for like you can isolate the solid part. There is a like if you check the solver, the files of solver, there we had to work on only on the solid part. Like you like if in that what you say in that you can if you go in deep of that. You can see the mechanical files where it is written for linear geometry.
Okay.
Linear, not linear geometry. What is it? Linear models. So there you have to like you have to make a similar template, and you have to change for whatever constitutive models that you want to implement.
Okay. You know, my question specifically was on how you are accounting for the boundary condition at the fluid solid interface.
Okay, boundary conditions. See, anyway, already I have used the inbuilt boundary conditions only because this moving wall boundary condition is already there in the FSI solver.
Okay, fine. All right. Yeah. Thank you. Any other questions?
Yes, I may have one question, sir.
Okay.
Yeah, please.
It is which types of the grid used here, a Lagrangian grid or it's a Eulerian grid?
Grid you are saying, or the expression, sir?
Grid.
See, the grid, this mesh I have prepared from ICM CFD only. So it's like a
conformal mesh. Like there is one-to-one matching between the fluid and solid domain.
But I think to model the solid and fluid both, we need two different types of the grid. Generally, we say either linear in grid or the Lagrangian grid.
Single grid, you can split into different modules of the test case. Like you define, you prepare the model in such a way that you can later split it into test case into different modules. Like it depends upon the structure of the test case. Like some of the test case explicitly have different modules. Some may have like a common module.
Okay, I think in immerse boundary method, generally both the grids are modeled separately, and then we are doing the interaction.
No. This is it's almost like we are using it separately because we have separate modules for solid and fluid solvers. So they are that will be working on a fixed portion. So the grid is different only for a different domain. It's different from modules.
Okay. Thank you.
Okay. Thank you.
Any other questions? Okay, if there are no other questions, let's thank the speaker and let's move on to the next presentation.
Thank you.
Thank you.
Good morning to all. My name is Ishwaran, working as scientific officer in Indira Gandhi Center for Atomic Research. My topic for this conference is fluid structure interaction analysis for beyond design basis earthquake and wind load estimation for a liquid effluent tanks of a nuclear power plant. Nuclear power plants and many oil gas industries use the liquid storage tanks for storing liquids like water, oil, chemical fluids, and liquid wastes. During seismic excitation, these tanks are subjected to the hydrodynamic forces. This is particularly important for the tanks containing the radioactive liquid wastes, in which the loss of liquid is not permitted by any means. If the sufficient freeboard is not provided, then the roof structure should be designed in such a manner to resist the uplift pressure due to the sloshing of liquid. In past years, heavy damages had been reported due to the strong earthquakes. I have listed here the few strong earthquakes which created the heavy damages to the industries and its liquid tanks in the past years. These are the snapshot of liquid tanks was taken during or after the earthquake. Coming to this is called elephant wood buckling, and this one is the diamond buckling. If the seismic load is more than the design limit, this kind of damages are possible. These are all few literatures available on liquid sloshing along with the fluid structure interaction studies. Two different magnitude of earthquakes have been considered for the seismic design of a nuclear power plant. The first one is OBE, which is reasonably expected to be experienced at the site area once during the operating life of the plant. The return period of the OBE is 100 years. The SSE is the second one, which is the maximum level of earthquake prone motion. It has a very low probability of being exceeded, means it has a return period of 10,000 years. We have found that very few literatures are available for the beyond design basis earthquake along with the consideration of FSI. And you remember that in 2011, the Fukushima nuclear accident in Japan was categorized as the beyond design basis event. Here, the tsunami and earthquake is hit the site together. Fast reactor nuclear plant, liquid waste will be treated in liquid waste management plant. These are storage pools, a different storage pool for a different purpose located in the liquid waste management facility. These tanks should be qualified for the seismic for the safe operation of the plant. This is the one of the tank in that facility. These tanks are designed as per ASME section 3 subsection ND. Now here in this work we are going to do the beyond design basis earthquake qualification of this tank. Here we are going to use the SSE level of load for the seismic qualification. For solving this, we are doing the two approaches. One is the American Society of Civil Engineering Code guidelines, and the second thing is the FSI-based numerical method. In 1963, Kausner has developed a mathematical model to estimate the liquid force in the liquid tank by considering the total fluid mass into two different groups. The first one is a convective mass, second one is impulsive mass. The impulsive mass is nothing but the liquid mass which will oscillate along with the tank wall during the tank excitation. But the convective mass will oscillate independently during the tank excitation, that called as lossing mass. Now the spring mass damper system has the properties, static properties and dynamic properties. From that the liquid loads and moments have been calculated. From that the stress on the tank wall also estimated. The American Society of Civil Engineering Code giving the guidelines for the design of liquid tank, mainly they are using from the report TAD 7024, which is based on the Kausner work. Now this spring mass damper system available for only for the simple tank like rectangle and cylindrical tank. Methodology for the numerical approach. The seismic analysis carried out on the liquid tank considering the fluid structure interaction effect using FEA-based free source code CASTM developed by CEA France. Here you can see that this is a tank wall and the fluid domain. This is a bottom and top plate with the stiffener. Here the tank wall and the top and bottom plate with the stiffener is modeled with the 2D cell element, and the fluid element is discretized with the 3D fluid element. Now the boundary condition is here, the bottom place is restricted for the translation motion, and the fluid domain except the top, the side wall and bottom sides are connected with the coupled with the tank wall. Now here the fluid structure interaction is considered by appropriately coupling the nodes between the fluid and structure. The ground response spectrum is used as the input for the spring mass damper system. With the numerical method, we need the transient time history. For that, the ground response spectrum compatible time history being generated in 3 directions. That this time history is used as the input for the numerical approach. These are all tank design parameters calculated using spring mass damper model. That is a ASE 2007 code guidelines. Here the first 1 to 6 are giving the geometrical property like convective and impulsive liquid mass and frequencies, and the 7 to 13 are showing that forces and moment and slosh height from the liquid, and the 14 to 19 is for the tank wall stresses calculation. These formulas are given in the ASE guidelines. Now the second method, numerical method. Initially we have done the self-weight analysis. This study will help us to find that whether that our liquid load transfer to the tank wall correctly. That means our coupling is perfect or not. Theoretically, we can calculate the tank wall hoop stresses is rho g h into r by t, the theoretical value, and numerical value. The theoretical value is coming 19.56 MPa. And the theoretical value, numerical values are coming 19.76. That means very close. That means our liquid load is correctly transferred to the tank wall. So in these FSI problems, we have to always ensure that the load will transfer correctly to the structure wall. And the second is that load, the total deformations are within the design limit. That also ensure. In the numerical method, now we are performing the model analysis. The eigenvalue analysis is performed to extract the more natural frequencies and corresponding mode shape from the domain for the liquid as well as the tank wall. The first 4 lowest frequencies are for the liquid is shown in the top figure. That the lowest frequency is 0.385 Hz, and the similar way the tank wall lowest frequency is 19.3 Hz. This is the second mode tank wall frequency, 43.2 Hz. In the numerical method, finally, we are doing the time history analysis. In the time history analysis, the 3-directional acceleration input has given us an input to our numerical model, and the fluid response have been taken out. The vertical liquid height is called as sloshing height that have been captured and shown here. The frequency of the slosh height is around 0.337 Hz is the major dominant frequency, which is very close to the first mode frequency of the liquid. And the slosh height we observe is 593 mm, which is the freeboard we have 625 mm. Since the sufficient freeboard is available here. This is the earthquake load on the tank wall. The maximum stresses is found at the discontinuity location at the bottom of the tank. Here, due to the earthquake load on the tank wall and the hydrodynamic load from the liquid waste, the bottom of the tank wall has experienced the maximum stress. After the earthquake load, the wind load calculation also performed. Here, the drag force is estimated as 8.7 kilonewton per meter square. The formula given in IS 875 Part 3 Indian Code. Now, the similar way, the CFD method also have been performed. The cross flow analysis is performed, and the putting the tank wall as the bluff body in the domain. And then here also the drag forces has calculated 5.3. As expected, the design values are little higher. Now coming to conclusion, we have calculated the various load, dead load, wind load, and earthquake load have been calculated already. We calculated as given in the guidelines. The load combination have been taken. Earthquake load and wind load we should not take together. So the combination one is the self weight alone, and combination two is self weight with the earthquake and self weight with the wind load, and the combination two is not for the design basis load. And the combination 3 is a beyond design basis load, which is the SSE level of earthquake, and the wind load we have taken 10,000 years. For the different load combination, the stresses are summed up and shown here. Here the stresses from the numerical and stresses from the spring mass damper. If you compare the spring mass damper system, stresses are little higher than the numerical value as expected, because the numerical one is the accurate value, and the spring mass damper we are calculating with some extra margin, so always the values are little higher than the numerical one. And here when we are comparing with this the stresses with the allowable stress, that we have the extra margin 2 times to 3 times, so this tank is safe for the SSE level of load. And coming to slosh height, the slosh height is 593 mm under the SSE level of load, and the freeboard available is 625. So the tank never reached slosh height, sloshing is never reached the roof of the tank. That means we have sufficient freeboard is available here. And since it's the spring mass damper system, we have the formulas for the simple geometry like rectangle tank and cylindrical tank. If we have some other than the cylindrical tank, rectangle tank, asymmetric tank, or some different geometries, we don't have the formula. So that time we can use this numerical method to bring the confidence that numerical techniques have been solved and be compared with the existing formula in this work. Thank you.
Thank you. Questions for the speaker, please. Questions from the audience? Dr. Ishwaran, I have a quick question. In the comparison where you were checking whether the simulation was able to correctly reproduce the hydrostatic pressure distribution with the self weight, the error seems to be a bit significant. I think it's around 1.5 kilopascal difference was there. Is that because of the coarseness of the mesh resolution or something else?
Yes, actually here I think we had the very close, that results are very agreement range only, the 19.56 and 19.13 in terms of megapascal. But still, as you said, if you define mesh and maybe we can expect some higher results. Still, we are, I know I have the very good, means finally the design road is always higher than the numerical. That's why for the validation purpose this way been taken. But when we are dealing with the asymmetric tank or some different tanks, definitely we need to go for some higher resolution meshes.
That's recently. Okay. My next quick query is that the numerical simulation produces stress levels that are smaller than what you get from the caudal provisions, right?
Yes.
With the spring mass. Yeah. So even when the tank is asymmetric, let's say, is it okay if we use the same caudal provisions and expect that the values are going to be high or more conservative? So it's okay, or is it really necessary that one needs to do a numerical simulation itself?
Yes, sir. Actually, it's a very good question. Still, actually, in industry, we are following the old formulas only, and the formula is available for only simple tank like rectangle and cylindrical. Suppose if you have the different tank like a cylindrical, horizontal cylindrical tank, till now we don't have any formula. And even famous project like ITER in France, they also have suffered, and engineer is confusing how to use these formulas. And overestimation also a problem to industry. It leads to cost, additional cost and all.
Yeah.
And
exactly.
Suppose even though it is okay, it is overestimating. Always we are going in the higher estimation. That is a one thing. And the other thing is, suppose the tank is asymmetry, and here we cannot always say that it is that the design load is a higher load, because in the asymmetric we have to take the correct convective mass and impulsive mass, which people will confuse, and they will take if they take the wrong impulsive mass and convective mass, it leads to the lower value and then the numerical.
Yeah, that is right. Thank you for the clarification, Dr. Ishwar. Any other questions? Any more questions? Yeah. If there are no further questions, we will let's thank Dr. Ishwaran for his presentation. Thank you very much.
Nice
over to the next.
Professor Ganesh Natarajan.
Yeah, thank you. So let's move over to the next presentation. Yeah, please.
Hello, I am Ekede. In next couple of minutes, I will explain some of our results from the ongoing research on numerical study of dynamics of freely falling rectangular plates. Let me quickly introduce the problem and its background and where we currently stand. Thin leaves, paper curds, they actually fall under their own weight. However, when the density ratio between the object and the surrounding fluid is near about 1, then the trajectories through which the object falls becomes complicated, and it's a subject of fluid mechanical studies. It involves complex fluid structure interaction, stability of the trajectories. In stable trajectories, the established regimes are mainly 3: flutter, which tumble, and the chaotic regime. To universally obtain different regimes, different shapes of plates are actually unified according to the dimensionless moment of inertia, which will be defined later on. From 0.16 to 0.4, it is known as flutter, which is shown in the right here. Tumble, sorry, the flutter. The tumble proceeds from 0.4 to 3, which gives us an impression of complete rotation, and the flutter to tumble transition occurs generally near about 0.4, which is generally known as chaotic regime, which shows the signs of both flutter and tumble. In the current study, we have added multiple plates to see the effect of the proximity of each plates on the stability of the trajectories and the role of complex vorticity dynamics in deciding their trajectories. As the current study involves multiple plates, it is essential that we model the collision of the plates, as during their stable or unstable trajectories, they may collide with each other. And if the collision is not properly modeled, the ensuing trajectories may not be resolved accurately. In the current study, we have used the solid modeling of repulsive force by Guwahati. In a nutshell, that model is actually based on two penalty parameters. Here, as it can be seen, using lambda and epsilon. The role of lambda can be thought of as a threshold. That is, when the nearest distance between two solid objects is less than lambda, the repulsive force quickly becomes non-trivial. Otherwise, it remains trivial. On the other hand, the penalty parameter epsilon actually gives the repulsive force a impulsive nature. As the shortest distance between two objects goes to 0 or they come very close to each other, the repulsive nature of the repulsive force is reflected as in the limit it approaches 1 by epsilon. Lambda is the threshold value, as I just now mentioned. It was observed in the reference that for density ratio 1, lambda 2 to 4 grid spacing and epsilon square of the grid spacing gives the most optimized result. It is also quite clear that while calculating the repulsive force, the shortest distance between the objects needs to be calculated accurately. So now the equations. We have 3 degrees of freedom for the plates x, y and theta, the continuity equation and the momentum equation for the incompressible constant density fluid flow. These equations are solved using second order semi-implicit finite volume technique using diffuse interface image boundary method. We have used a highly diagonalized C precondition bicycle step for all the resulting linear system of linear equations. The grid spacing used is 1 by 100, that is 10 raised minus 2 with delta T 10 minus 3. Nearly 8 million cells are used for all the calculations, consuming nearly 6,000 core hours for each case. 2 cases are tested and it can be seen in the right. The main control parameters for this study is the density ratio. As I already have mentioned, the non-dimensional moment of inertia I star, which actually demarcates different regimes. For the current study, we have used 4 different orientation of the plates. One is converging, C, one is vertically separated, B, the third one is horizontally separated, H, and the diverging setup. In all of these setup, the angle with the horizontal is 45 degrees. I will only present the results for one flutter case and one tumble case. Let's start with the flutter one. We have computed the flutter case at I star 16, 0.16. The 4 cases we have shown in the right hand side, 4 trajectories and the vertical displacement with time. As it can be seen, the C being the convergent setup, the plates collide frequently, which prevents any stable trajectories, while for V and H we can see parallel fluttering, and for D we see independent flutter of the plates. From the vertical locations of the plates, it is observed that for V and H case, intersection of the trajectories occur at some point of time, and after that the trailing plate actually overtakes the leading one. It is clearly seen that the initial orientation of the plates have a strong bearing in the final stable trajectories. Let's see a real-time animation of the fluttering. As we can see in the C setup, the plates are colliding frequently. For V and H, parallel fluttering continues, while for D, because of the large separation distance, the plates continue with independent fluttering, while the vorticity field becomes clearly widespread. Next, we take up tumble at I star 0.6. Again, the trajectories are shown at the top, while the monotonic increase of angular position is shown at the bottom. It can be seen that again the tumble proceeds after initial fluttering transients. One very important point to note here is V and H2 are the two setups where the plates finally settle to a stable tumble, but at two different heights. D gives a symmetric independent tumbling, while C at much later stage settles to a stable tumble regime. If we see the angular orientation with time, it is quite clear that C has a longer transients, while V and H quickly settles to a tumble regime, and D almost from the beginning gives us two different direction of rotations. It is also to be noted that D setup being divergent is nearly behaves as if the two plates are independently falling under their own weights, which was also observed in case of flutter. Let's see a real-time animation of the tumble. As you can be seen, C setup again suffers from too many collisions even at the initial time, while V and H setup quickly shows that plates settle at two different heights and continue to tumble, while D, the plates moves in the two different directions and gives a cleaner trajectories with the tumble. Vorticity dynamics for multiple plates become even more complex than the single plate. Here, 4 different orientations are shown with the vorticity field near the plates. First of all, the characteristic lengths of the vortices set from the trailing edge of the plates nearly constitute the length scale of the entire vorticity field. It can be seen that the maximum such length scale increases for V and H setup. A steady gliding, which is defined as unidirectional motion of the plate, actually favors 2S shading mode. Cleaner von Karman vortex state can be seen for the first case for the flutter. Large scale vortex merging is observed for the V and H case. And while for the D setup, again we obtain a clear Karman vortex strip. It is believed that the near the plate, the vorticity field has a significant role to play in deciding the stable trajectories. Let us now summarize the main findings. We have seen stable trajectories for both flutter and tumble heavily depend upon the initial orientation of the plates, while the converging orientation for all the regimes suffer with too many collisions leading to unstable trajectories. Flutter proceed with parallel or independent mode depending upon the initial orientation. Stable tumble always proceed at different heights. Diverging plates the plates in the diverging orientation behaves as independent plates. And in vorticity dynamics, we have observed large-scale vortex merging for V and H case, vertical and horizontally separated setup, while clear Karman streets are generally observed for the steady gliding and the D setup. Thank you very much for your time.
Thank you. Questions for the speaker, please.
Hello, I have a question.
Yes, please.
Arnab, this is Atul Sharma.
Yes.
I'm very happy to see the fantastic vortex shading. It's a very challenging problem. I appreciate
appreciate the effort in doing that, and it's very important, scientifically very exciting and interesting and challenging problem. I was just wondering whether I had missed whether you have shown validation, because showing validation for this problem, whether the literature is available, I'm wondering.
Yes, in the first one slide, I have shown a comparison study from a previous work where only one single plate was used, and it's a very famous paper by Anderson.
Yeah. So single plate, and now you are doing study with multi-plate using some collision model, correct?
Yes. And also for multiple plates, we have validated with the test problem given in the Guwahati itself for a sedimentation of two particle problem.
Oh, good. And that validation probably would have been a better validation to show, because I was just wondering the testing of your collision model, correct?
Yes, correct. You are right.
Okay. Now, as far as the numerical challenge, although you have not mentioned in this talk, but can you answer the biggest numerical challenge in this problem?
See, these problems, as I mentioned, roughly speaking, these calculations mostly are 8 to 10 million meshes, though it's uniform, because most demanding problem is we cannot use non-uniform grid, because the vorticity field and the importance of fluid mechanics is felt everywhere uniformly. That's why grid spacing cannot be non-uniform everywhere, but that acts as an advantage. But the main difficulty is the domain size, because many a times it is seen that the domain size has to be very large so that we can actually finally obtain a stable trajectory. And because of large domain size, mesh size becomes extremely fine sometimes, and the calculation becomes lengthy, and it takes time.
Okay. No, I'm just wondering, when the plates comes to closer, whether is a numerical instability issues you face?
No, see, for the collision model itself, the collision model basically is, it has two penalty parameters. One parameter takes into account the proximity of the two plates. If the two plates come closer to each other, then lambda, a repulsive force starts switches to non-trivial form, and as they go closer to each other, that repulsive force becomes larger and larger, and that model itself prevents them from colliding with each other.
Okay, sounds good. It will be wonderful if you extend this one for a flex. Please continue.
We have not found any numerical instability when the plates are actually coming closer to each other. However, as far as the linear solvers are concerned, yes, when they approach each other, the system of equations becomes relatively stiffer.
Yes, that's what it would be wonderful if you can extend this work with flexible plate where they can deform also in future. But I highly appreciate the work and look forward for publication in this area.
Okay, thank you.
Yeah. Thank you, Professor Sharma. I think Arjun John, please proceed with your question.
I just have one question. During the fluttering for the decays, I was wondering why it is not symmetric in the initial trajectory for the two plates.
Can you repeat the question, please, again?
During the flutter case, for the diverging decays, I was wondering why the trajectory of the two plates were not symmetric when you show the plot or the animation.
Frankly speaking, if I have to answer that, our experience has been this problem is extremely unstable, in a sense that if we carry out the same problem twice, we will not end up getting the same trajectories. So it is we have seen that although it is expected that the divergent setup is something where the plates are unlikely to collide, and since they are going apart from each other, we are likely to get a symmetric fluttering about the mid-vertical plane. But because of unavoidable numerical issues, those two trajectories are not exactly symmetric, but they are nearly symmetric about each other.
Okay, thank you, sir. That's all.
Any other questions from the audience? I just have two quick questions, Dr. Day. What is the relative size of the plate with respect to the grid size? I mean, thickness of the plate to the grid size.
Yeah, see, as far as I remember, the thickness for the flutter case is actually the problem started from the, as I mentioned in Anderson paper. They actually carried out a experiment in using aluminium foils in water. There, the thickness was 0.014 centimeter. Now, as far as in using non-dimensional dimensions, I have kept the grid spacing nearly same as the linear elements of the object, and the thickness of the plates are taken as 3 grid cells. So you can say, in our case, the thickness is 0.03.
Okay, all right. And any thoughts on whether the conclusions would be significantly different if there is a change in the collision model?
I think so, because if the collision model is not accurate enough, then there is a high chance that the two plates may change their orientations and their way of moving completely after they actually go apart from each other after coming in proximity to each other. It is the collision model actually who is preventing them from coming into each other, and definitely this will have a strong bearing on the final stable trajectory.
Dynamics. Yeah. Thank you, Dr. Day. If there are no further questions, let's thank the speaker and move on to the next presentation. Thank you.
Thank you.
Good afternoon, everyone. Myself, Jyoti Prakash, Scientist B, working in CWPRS, Pune. Now, I'm going to present transit analysis of a long raising mean of a lift irrigation scheme. What is hydraulic transit phenomena? It is an unsteady flow, generally known as water hammer, is transmitted as a pressure wave in the pipeline system. Water hammer in pipe networks result from an abrupt change in the flow velocity, abrupt closing or opening of liquid flow in a pipeline by means of various kinds of valves, as well as uncontrolled pump starting or stopping. Why transient analysis is required? Transient analysis is important to be considered during design, maintenance, and operation of water supply systems. It can cause high pressures and negative pressures and potentially damage the system. Thus, the pipeline should be designed either with suitable diameter and wall thickness to sustain transient pressures, or with appropriate water hammer control devices to withstand the associated maximum and minimum pressures. The present study was conducted for the Columbia Lift Irrigation Scheme. The pumping station of Columbia Lift Irrigation Scheme is located on upstream of Balagan Barrage of Godavari River in Nanded district and is envisaged to lift through 10.92 kilometers long MSP. The scheme has an irrigation potential of 4,000 hectares. An intake structure is located in the river wherein 3 vertical pumps are deployed to discharge 2 meter cube per second of water through the rising main to deliver water at 60 meter high throughout the year. Due to this high head and low discharge, the pumping station is provided with 3 numbers of vertical turbine pumps, which are running in parallel together to meet the design discharge. Methodology used for transit analysis. The transit analysis was carried out by using software available with CWPRS, which is based on method of characteristics to solve the water hammer problems. MOSC is a popular method for handling hydraulic transients, which converts the two partial differential equations of continuity and momentum into 4 ordinary differential equations. These equations are solved numerically using finite difference techniques. The transient analysis was conducted for the rising main from NRV to delivery reservoir for critical operating condition of power failure and sudden stoppage of pumps in the system. The following 2 conditions were considered to carry out the analysis. The first condition is analysis without safety devices is carried out to find out maximum and minimum pressures existing in the rising mains of the pumping schemes. And the second condition, analysis with safety devices is carried out to find out the effect of safety devices on maximum and minimum pressures for rising mains of the pumping schemes. The following procedure was used for the analysis. First, model the pipe network for all the pipelines case by case in software platform. Perform transit analysis of the network without any production device. Then check for steady state conditions for validate of data and to detect any possible errors. Then check the maximum and minimum pressures developed in the pipelines. If it exceeds the limiting values, select a suitable safety device to mitigate the such pressures. Then perform transit analysis of the network with air walls distributed along the rising main and examine the likely extent of pressure fluctuations. If the production is found to be inadequate, addition of zero velocity walls are tried. Still the production is found inadequate, then addition of air vessel is tried. If the production is found adequate, the volume of air vessel is slightly reduced. The entire procedure is repeated till optimum sizing of air vessel leading to acceptable maximum and minimum pressures are obtained. The study was conducted for 7 different cases. The case 1 shows the maximum and minimum pressures of pipeline without safety devices. It is observed from the graph that there were appreciable pressure fluctuations. Hence, safety devices are necessary to control the negative surge pressures. Then case 2 shows that analysis with 22 air walls. There is a marked improvement in negative pressure region, but still the negative pressures are not acceptable. Again, the case 3 and case 4 shows that analysis with zero velocity walls along with air walls, but the values of pressures are not improved. Then case 5 shows that analysis with air vessel of 150 meter cube capacity along with 6 air walls. It is seen that the minimum and maximum pressures are well within acceptable limits. Further, the analysis was conducted to optimize the capacity of air vessel with case 6 and case 7, which shows the analysis with air vessel of 100 meter capacity along with 10 air walls for which the maximum and minimum pressures are well acceptable. The figure shows the air vessel details along with its connection to rising main, and the below table shows the location of air walls on rising main. It is concluded that analysis has a basis to adopt user-friendly, indigenously available safety device without any requirement of import of parts, cost effectiveness, feasibility at site, and equipment that are adaptable to system users with proper training is recommended. The optimum size of air vessel was finalized after analyzing the pressures in the rising main of Columbia lift irrigation scheme. The pumping system needs a protected device in the form of air vessel of capacity 100 meter cube and a total of 10 air walls. By this, reliability of Columbia electrification scheme is ensured for continuous operation. Thank you for your kind attention.
Thank you. Now it is open for questions. Any question from the audience? Professor Day, any question? Arjun? Arjun, your hand is raised. Do you want to ask any question?
Sir, there is some problem with the sound of the presentation. I'll reshare the presentation.
Okay, so if there are no questions, we will move to the next presentation. Rajkumar, please play the next presentation.
Hello everyone, I am Akash Bhuiya from the Department of Aerospace Engineering, IIT Kharagpur, and I will be talking on a numerical study on the drag reduction of a circular cylinder at low Reynolds number with 2 contra-rotating control cylinders. So what is the motivation behind the work? We see a large number of areas where we see the flow is being separated, particularly in case of bluff bodies. So typical bluff bodies are like large trucks and vehicles, and also major bluff bodies in the aerospace sector is on the rotor hubs, landing gears, pylons, etc. that sees major flow separation and the regular vortex shading that creates an unsteady wake. It puts the dynamic loading. So we need to reduce the drag as well as we need to suppress the vortex shedding, and so we need the control techniques. In this case, we have done the active flow control technique with control cylinders. So active control means it's with the supply of external energy. So here we have the domain setup where the 2 contra-rotating control cylinders are placed at some distance of 0.01 d gap and the dimensions of the main cylinder is d and the control cylinders is d by 20, and they are rotating at a non-dimensional speed of alpha. So alpha is defined as r omega divided by u naught. So u naught is the free stream speed. So we have placed the control cylinder at some angular position theta with respect to the wake center line, and theta is varied as 30, 45, 60, 75 and 90. Alpha is varied as 0, 1, 2, 3, 4 and 5, and the gap between the main cylinder and the control cylinder is fixed at 0.01, and the Reynolds number is also fixed at 100, and we have simulated all the cases and we have obtained the drag reduced by this control mechanism, and also we have calculated the power consumed by the control cylinders. So these are some of the computational solver details that we have used in ANSYS Fluent. So the time step size was 0.01 d by u naught, so it is non-dimensional time, and the nearby mesh size is del s is equals to 1/1000th of the diameter of the main cylinder. So we have used the simple coupling velocity, pressure velocity coupling, and the special discretization was done for the least square gradient base for the gradient, the second order for the pressure, and second order upwind for the momentum. And we've also used the second order implicit formulation for the transient formulation. So here we have the grid independency tests, and we have also shown the basic structure of the mesh. So we have triangular unstructured grid near the wall and structured rectangular grids in the outer domain. Here we see the domain independency tests that is shown in the table. So we have varied the domain size and we have sticked with the domain size D3, 45 cross 30D, and also we have shown the quite accurate validations with Mittal 1999. So we have classified the flow into 5 types. So type A corresponds to the unsteady vortex shedding in the wake. So we see normal von Karman vortex streets. In type B, we see steady primary recirculation region attached to the main cylinder. So we can see in the adjacent picture. So in type C, we see steady primary recirculating region, but that is detached from the main cylinder. In type D, we see no recirculation region in the wake. And in type E, we see secondary recirculation region that rotates in the opposite direction as the main primary recirculating region. And these secondary regions are attached to the control cylinders. So here we have the classification map plot. So we see that for all theta at alpha is equals to 0, we see the regular vortex shading. So there is effectively the cylinder is not rotating and we effectively see no control of the flow. But particularly for alpha is greater than 2 and theta greater than 45, the steady primary recirculation region that is attached to the main cylinder, so that is the type B flow. And for alpha is greater than 2 and theta less than 45 degree, we can see both type C and type D flows for theta is equals to 45 and 60 degrees. So, and for theta is equals to 30 degree, there is an additional feature. We see secondary recirculation region that is appear in the wake of the main cylinder that is attached to the control cylinder, and it rotates in the opposite direction as the main vortex that is being shed from the main cylinder. So in the second part, we see how the aerodynamic forces are varied as we change the position. So here we characterize the lift forces on the main cylinder. So we see that with increase in alpha, the CL max gets reduced. So this CL max is for the main cylinder, it gets reduced, and CL max follows a parabolic pattern with change in theta. So the minimum CL max is obtained for theta is equals to 60 degree, and for alpha is equals to 1, we see that the vortex shading has been completely suppressed and we get a steady flow for theta is equals to 60 degree at alpha is equals to 1. Another important observation is that for theta is equals to 75 degree or 90 degree, the main cylinder and the control cylinder acts up to form a single bluff body that offers more blockage to the incoming flow, and thereby it increases the CL max and it's more compared to the bare cylinder. So here we have the plot of the drag coefficient versus theta at all alphas. So drag decreases with increase in the rotational speed of the control cylinder. And to quantify the drag, we have split it into pressure drag and a viscous drag in the right hand side picture. So we see that the viscous drag is almost constant with the increase in rotational speed, but the pressure drag has been reduced further by the increasing the rotational speed, and the range of the pressure drag is much more than the viscous drag. So to explain the pressure drag reduction, we need to see the pressure recovery and its variation with theta as well as its variation with alpha. So in the left hand side picture, we see the time average pressure coefficient compared along the wake center line of the main cylinder for all the theta and alpha is equals to 5. So here x is defined from the center of the main cylinder. So we see that for theta is equals to 30 degree, we see the lowest pressure recovery, but it increases as consequently for theta is all the rotations rate to 5, and that is along the line joining the main cylinder center point as well as the control cylinder center point. So here we see the pressure jump, so that is maximum for alpha is equals to 5. So before we calculate the efficiency factor, we need to see the force exerted on the control cylinders. So we know that the drag and lift coefficient increases with increase in the rotational speed. That can be explained from the Magnus lift point of view. We also see that the drag coefficient decreases with increase in theta. That is due to the wake of the control cylinder at theta is equals to 90 degree that hits the main cylinder, and it generates a region of high pressure that decreases the drag. At the same time, the lift coefficient is very small when theta is equals to 30 degree because the circulation generated is very less, as a result of which the lift is very low. So now we can calculate the power coefficients. So we have the rotational power as well as the translational power. Rotational power is calculated from integrating the shear stress over the control cylinder as it rotates, and translational power can be calculated by multiplying the free stream velocity with the force exerted on the control cylinders. So Fx and Fy are the forces acting on the control cylinder. So that can be non-dimensionalized by the free stream speed as well as the diameter of the main cylinder. So here we see that the translational power increases with increase in theta as well as with alpha, and the rotational power increases with increase in alpha but almost remains constant with theta. So it doesn't vary with the position of the control cylinder. So it is important to know that why we are calculating the translation power. It is because to measure the amount of force or the amount of power expended so as to keep the control cylinders in its place. So now we can define the efficiency factor. So efficiency factor can be defined as a reduction in drag coefficient per unit power consumed. That's the power, both rotational and translational power. So del CD is the drag reduction, that is equal to the CD without the control cylinder, that is 1.36 for case of a bare cylinder at Reynolds number 100, minus the CD that we have obtained after we are putting the control mechanism. So that can be divided by the total power expended. So the factor of 2 comes in because we have 2 control cylinders. So we see from the right hand side picture that efficiency factor is maximum for theta is equals to 60 degree at all rotational speeds. So, and we also see that efficiency factor is maximum for alpha is equals to 2, and it decreases considerably for 3, 4 and 5. So it is because we need to spend more amount of power to rotate the cylinder at higher rotational speeds. So that decreases the efficiency of the control mechanism. So to summarize the entire work, first we have classified the flow into 5 types. Then we have quantified the drag and the lift coefficient and its dependence on the position as well as the rotation speed. We see the maximum drag reduction obtained for position theta is equals to 45 degree and 60 degree. And then we have defined an efficiency factor and we obtained the maximum efficiency at theta is equals to 60 degree for all rotation speeds. So this is the position where the flow separates for a circular cylinder at Reynolds number 100. And if we place the control cylinder exactly at the point of separation, that will be very effective.
Now I request the audience, if you have any questions, the speaker can take questions.
Hello.
Yeah, please.
I have one question. So, how to find this position of the flow separation actually? You have to find this by visualization or some, I mean, mathematical conditions for this.
So to find the location of the, because the flow separation
yeah.
of flow separation at the controls, sorry, the circular cylinder, that has been well established before. So that is around 120 degree, around 60 degree at Reynolds number 100. So that can be shown from the vorticity plots also. The vorticity at the separation should be 0. So
okay, means by visualization. Huh? Okay,
from visualization, as see that the vorticity is 0 at the point of separation.
So no, vorticity.
And also from the streamline pattern, we can see the separation.
Okay.
I have two doubts. One is, as you have shown, like the translation rotational power, is it not for the translation power also you have to integrate over the surface of the cylinder? Because the forces acting on the surface of the cylinder changes from point to point. So like the rotational power, for the translational power also it has to be integrated over the surface of the cylinder.
Actually, the drag we have that is why we have obtained the force on the cylinder, control cylinder. So when we calculate the force, so we integrated the force over all the surface, and then we calculate the force. So once we have the force on the control cylinder, we can just multiply with the free stream. So that is how we calculate power, the force into the velocity. So that's how we can do it. So once we have the force on the control cylinder, we know the power, translational power.
I wonder how, rather why the efficiency is defined with input as the coefficient of pressure. Can you comment on that?
Sorry, sir, can you please repeat the question once?
Can you please comment on the expression for efficiency where you have used input as the coefficient of pressure, output is the drag, and input as the coefficient of pressure? CPT plus CPR used in the denominator.
No, that is not pressure, sir. That is the power coefficient. R denotes for rotation and T denotes for translation. So CPR means the rotational power coefficient.
Yeah, thank you. Yeah, that what I was expecting.
Yes, sir.
Any other questions from the audience? If not, then we can move to the next presentation, which I suppose is the last one for this session.
Thank you, session sir. We will start our next session shortly. That will start at around 4:15 p.m. Good afternoon, everyone. Welcome to this session on propulsion and power. This session will be shared by Professor Neeraj Kumbhakarna from IIT Bombay. I request Professor Kumbhakarna to please start this session.
Hello, am I audible? I'm
Yes,
Neeraj.
sir. Yes, sir, you are audible.
Yeah, thanks. Okay, so do we get started with the session right away?
Yes, sir, we can start.
Okay, so the first paper in this session is from Amit Kumar Yadav et al. And it deals with the effect of nanoparticles on combustion performance of isorocene sprays. Okay, so isorocene is kind of the trademark fuel of ISRO. It's a liquid fuel that they use in their rockets. And here we have a team from ISRO presenting it. Welcome. Yeah, please get on with please start the presentation. Who do we have from this team? Yeah, please get started. Yeah. Okay. Have we started? I'm not seeing the video running.
Yes, sir, we're starting this.
Okay. Okay. Yeah.
Dear all, I am Amit Kumar Yadav from Liquid Propulsion System Center, Trivandrum, and presenting the work on effect of nanoparticles on combustion performance of isorocene spray. This work was supported by my senior colleague, Varghese Maithur Tanikal, Ashish MP, and John Taragan. This work was initiated because it has been observed that by adding the nanoparticle into the isorocene, it increases the convectivity transfer coefficient. Higher convectivity transfer coefficient results in lower mass flow rate of propellant required for cooling, which results in a larger concentration of the mass flow rate of propellant passing through the main chamber and participates in combustion at uniform mixture ratio, and which results in better performance. Adding the nanoparticle in isorocene increases the density, which reduces the stage mass. Addition of nanoparticle into the base fuel in isorocene is not just a mixing. The solution should be colloidal. Colloidal solution of nanosized material is termed as nanofluid, which was set by Choi in 1995. The size of nanoparticle should be less than 100 nanometer and the quantity should be less than 1% by volume. In this slide, the experimental setup used for nanofluid preparation is shown. There are various methods to prepare the nanofluid available in public literature. In this work, two-step method is used. Under the two-step method, the first step is generation of nanoparticle, which was done by procurement in this work, and the second step was to prepare the colloidal solution. The colloidal solution was prepared using ultrasonication machine, which is shown in the right column. The main part of ultrasonication machine is ultrasonication probe, and the processing of ultrasonication probe was controlled by a control unit, and solution was prepared in a jacketed vessel, and the jacketed vessel was used because there was heat addition during the ultrasonication process. To remove that heat, there was water flow maintained at 22-degree temperature using a chiller. And the nanofluid was prepared by adding graphene, having a specific surface area 300 meters square per gram. It was like a disc shape, and it was added in isolocene by a concentration of 0.2 percentage. And this concentration was chosen because it has given a maximum burning rate in the rapid combustion experiment. Experimental setup for doing the combustion experiment is shown here. In the left column, schematic diagram is shown. We had a nitrogen cylinder at 50 bar with the help of pressure regulator and pressure gauge. Outer pressure was maintained 2 bar, and with 2 bar pressure, this nanofluid tank was pressurized, and which was causing the fuel to flow and pass through the injector. Similarly, air cylinder was at 50 bar, and with the pressure regulator and pressure gauge, air outer pressure was maintained 5 bar, and air mass flow rate was measured using a mass flow controller, and mass flow rate of air was maintained 0.2 gram per second, and the mass flow rate of nanofluid was also 0.2 gram per second, which was measured using weighing method. And once the fuel and air passing through the injector created the spray was ignited using a pilot flame, and the species and temperature distribution of the spray flame was measured as 2 locations from the injector face, that is 15 centimeter and 20 centimeter from the injector face, and 5 mm from the injector center line. And flame structure was captured using a high-speed camera with 500 frames per second. And in the right column, the injector detail is shown. We had a CFXL injector used for spray combustion experiments, which is having a central liquid flow, and through the annular gap, air flow was maintained, and the air and fuel were meeting in a recessed volume to create the spray. Flame structure has been demonstrated in this slide. We can see the top one is showing the flame structure of pure isolocene, and the bottom was showing the flame structure of the isolocene loaded with graphene nanoparticles. These are the 400 frames average data, and the edges of the flame are shown in the right column. By seeing the edges, we can see that the flame lift-off height is increased due to addition of graphene nanoparticles, and flame width has reduced. Effect of nanoparticle on flame temperature and CO concentration of the flame is shown in this slide. In the left column, we can see the flame temperature at 2 various locations at 15 centimeter and 20 centimeter in the flame for pure isolocene and for graphene loaded isolocene. So there is a reduction when we are adding the graphene nanoparticle in the isolocene. This reduction on the flame temperature is attributed to radiation losses from the flame due to addition of graphene nanoparticle. Here in the right column, first row, CO concentration at 15 centimeter from the injector face is shown for pure isolocene and graphene loaded isolocene flame. Similarly, in the bottom column at 20 centimeter from injector face, we are seeing the CO concentration for pure isolocene and graphene loaded isolocene. But we can see there is a reduction in CO concentration due to addition of nanoparticles. Summary is that mass flow rate of nanofuel and air is maintained as 0.2 gram per second for the same pressure drop, and flame lift-off height increased by 36% and flame width decreased by 28% due to addition of graphene nanoparticle in isolocene for the same mass flow rate. Flame temperature and CO concentration measured at 2 axial locations, that is 15 centimeter and 20 centimeter from injector face, shows reduction in temperature as well as reduction in CO concentration. Thank you.
Hello everyone, I'm Dhanlakshmi Sellan from IIT Hyderabad, working under.
Okay, so yeah, thanks to
Dr. Amit Kumar for the presentation. Yeah, audience can now ask questions if they have. I think you can just raise your hands and yeah, questions from the audience. Okay, so maybe I can ask a couple of questions. So if we say that addition of nanoparticles increases the frame lift of height, are there no negative consequences of the lifting up of flame?
Yeah, sir. Good afternoon, sir. I am Amit here.
Yeah. Hello, Amit. Yeah.
Yeah. Yes, sir. I saw that you are the session chair actually. So this is actually, sir. That's right. There will be increase in flame lift off height because we had used air here, and what we have found that in the previous like before the spray combustion experiments, we had done the spray characterization also.
Okay.
Having the same injector, we have found that there is increase in the droplet size due to addition of the nanoparticle. So that is increase in the droplet size actually reduces the evaporation rate, which is resulting in the combustion performance actually. So it is a negative remark, as you said. It will be a negative remark. But we had subsequently we have conducted a lot of experiments using oxygen also, which will be more practical for the rocket application. So there we had seen that it will improve the performance, although there will be definitely reduction in spray characteristics.
Okay. So in spite of the adverse effect on spray characteristics, the nanoparticle, the positive effects outweigh the negative effects, is what you're saying.
Yes, sir. But we have to use the oxygen when we will be using oxygen for combustion, then it will improve. In case of air, what we are seeing that if overall, if you see the expected increase in flame lift height has not been observed, because if you see the same whatever increase was happen in the spray droplet, if that proportionate increase flame lift of height would have been increased more, but due to the higher combustion rate, the flame lift of height is reduced less, increased less actually.
Okay. Yeah. So when you use oxygen, that will be in cryogenic form, right? It will be liquid.
Yes, sir.
Yeah. But now I think air you are using it in gaseous form.
Yes, sir. In current experimental setup, we are using air only. But once it will come to actual level, definitely it is semi-cryogenic. So our oxygen will be actually oxygen has combusting in two forms actually, two phases. In our gas generator, or you can say pre-burner, it will be in liquid form. But once it comes to main thrust chamber, it will be again in gaseous form. Yeah.
Okay, good. Yeah, so good research. Thank you. Right.
Thank you, sir.
Thank you. Yeah, if there's still someone in the audience who wants to ask questions, they can go ahead, or we can get started with the next presentation then. Okay, so for the next presentation, we have a team from IIT Hyderabad.
Hello, sir.
This is
Hello.
Yes.
Yeah, my question is to the paper which was presented right now. So you had used a shear coaxial injector, right? And through the middle, I see you had injected fuel. Middle inner core.
Yes, sir.
So if you see the history of rockets where shear coaxial injector has been used, they usually prefer on the annular side, and the inner side essentially has the oxygen coming out. And the reason is because and the fuel is injected at very high density. Was there any specific reason why you're injecting through the middle tube? Because I wonder how the mixing will happen and how ignition will happen, because they inject fuel at higher velocities on the outer core so that it gets entrapped inside the high oxygen which is coming, oxidizer which is coming through middle.
No, actually in the shear coaxial injector, we had given the recess volume, sufficient recess length is provided, where the air and liquid before coming to the injector completely from the injector into the chamber, they will be having sufficient volume available where they will be mixing actually. And moreover,
Yeah, true.
yeah.
Okay.
And
But
we had
I just
actually,
had a question on this.
yeah, both varieties of injector is there actually in the history. If you see,
I think you need to check on that, please, because this is, I think, what I'm sure. Because if you take F1 engine, J2 engines, or any engine you take, whatever shear coaxial injector in context with shear coaxial injector, oxidizer always pumped in middle through middle. You can have a check on it. I mean, there are a lot of people working on that. Okay.
Okay.
Yeah. So, okay, so that was a good presentation. Let us move on to, we have a team from IIT Hyderabad presenting on LPG stratified turbulence flame, investigation of LPG stratified turbulence flame. So, yeah, we can get started with the presentation.
Hello everyone, I'm Dhanlakshmi Sellan from IIT Hyderabad, working under the supervision of Dr. Saravanan Balusamy. I am presenting on title of Investigation of LPG stratified turbulent flame using simultaneous over star CS star chemiluminescence. The outline of the presentation is objective of study, application, why the LPG is used here, swirl stabilized burner which is studied here, experimental setup, and premixed and stratified flames which are studied here, experimental results, conclusion, acknowledgement, and references. The objective is to study the effect of stratification on the LPG air flames using chemiluminescence imaging, to study the effect of swirl on the LPG air flames using chemiluminescence imaging. Starting with why liquefied petroleum gas is selected for this study. We know that world is shifting from fossil fuel to the zero carbon emission, but the immediate shift from fossil fuel to the zero carbon emission policies is likely to be impossible. Therefore, we need intermediate alternative fuel which has a low carbon emission, also fulfill the energy requirements. Therefore, LPG can be used as an intermediate fuel because it is clean burning, availability, low particle emission, low NOx and nearly zero SOx emissions. LPG evaporize at the atmospheric temperature and pressure easily, so there is no leakage issues, and instantaneous control of flame temperature LPG is possible, and it is environment friendly fuel with easy handling. Coming to the application, the swirl stabilized burner used here is replicate the laboratory scale of gas turbine combustor. Moving to the burner design. The image shows the designed and fabricated swirl stabilized axis symmetric burner. Here we can see the cross-sectional view of the burner. The burner is configured with a bluff body and 3 annulus. The inner annuli allows the premixed flow with equivalence ratio of pi, and the outer annulus allows the premixed flow with the equivalence ratio of pi 2. And here the co-flow air is used to avoid the environmental disturbance. And 2 swirlers, inner and outer swirlers, are used here for better mixing. And this shows 3D metal printed swirlers which is used here. Here, because the effect of swirler is studied, 2 types of swirlers we are introducing. One is low swirl with 30 degree and other one is medium swirler with 45 degree. Next we will look into the experimental setup. The flow configuration along with the burner is shown in the schematic. Here we can see the compressed air line and the fuel air flow rates are controlled by mass flow controller and allowed to mix in the feed line. The premixed flow with equivalence ratio pi1 is allowed to enter into inner annulus of the burner, and the equivalence ratio with pi2 is allowed to enter into outer annulus of the burner. Only compressed air is allowed to outer flow. Next, moving to the optical setup of the chemiluminescence imaging. Two ICCD cameras are used to simultaneously capture the OH star and CH star. Here, the ICCD cameras are capture the intensity of the chemically excited radicals. One ICCD camera is equipped with OH star filter and another one is equipped with CH star filter. The wavelength of the OH star filter is 309 nanometer and the wavelength of CH star filter is 431 nanometer. The photographic image of the experimental setup is shown here. Because premixed and stratified flames are special concern here, let's get some idea about it. Premixed flames are nothing but the flame front propagates into the homogeneous mixer field, whereas the stratified combustion is nothing but the flame front propagates in inhomogeneous mixture field, where the inhomogeneous mixture field exists in flammability limit. So coming to a point where how the premixed and stratified flames are introduced here. Premixed flames are introduced here by keeping pi1 and pi2 are equal. Then stratified flames are introduced by keeping inner equivalence ratio richer and the outer equivalence ratio leaner. Basically, it is a back supported stratified flame. Okay, why stratified flames? Compared to other mode of combustion, stratified flames has extended flammability limit, broader reaction zone, and higher flame speed. Coming to the operating conditions, images are captured for four stratification ratios. The stratification ratio is nothing but the ratio of equivalence ratio at inner to the equivalence ratio at outer annulus. So basically, when we see the inner equivalence ratio is equal to the outer equivalence ratio, we are introducing premixed flame. When both are not equal, we are introducing stratified flame. So from stratification ratio 1 to 4, we are moving from premixed flame to stratification flame. Coming to the experimental results, here instantaneous CH star chemiluminescence images which are captured for various stratification levels at low slow flow conditions. So in the first image, the premixed flame, we can clearly see the CH star intensity is uniformly distributed, whereas when we move to the premixed to the stratified flames, the CH star intensity is non-uniformly distributed. This clearly tells us the stratification is introduced in the flow. Here contour shows the intensity of simultaneously captured OH star and CH star chemiluminescence for low and medium swirl conditions. The upper row shows the low swirl flow condition and the bottom row shows the medium swirl flow conditions. Here we can see the premixed flames are so elongated compared to the other stratified flames, which is similar in the case of medium swirl condition also. So in case of premixed flame, the reaction zones are moved little away from the burner. But when we shift from immediately from premixed flame, in the stratified flame, the reaction zone is brought next to the exit of the burner. But further increasing the stratification leads to move of reaction zone away from the burner exit. If we further increase the stratification level, that may lead to lean blow off. So this can be used as a good indicator for blow off. Here we can see even though the outer equivalence ratio is below the flammability limit, still the flame is stabilized because of inner rich conditions. So basically stratification level that stabilizes the flame. Coming to the medium swirl flow conditions, the flame becomes further compact because of the fast mixing at the burner exit. So it keeps all the in all the conditions we can see the reaction zone is just exit of the burner. That is because of fast mixing, the hot products mix with the fresh gas and that stabilize the flames. From simultaneously captured overstar, series star, chemiluminescence intensity, we have calculated equivalence ratio. This contour shows the equivalence ratio for premixed and stratified flames at both low and medium swirl flow conditions. Here, the equivalence ratio is calculated based on the correlation provided by the Hartley-Lucas group. In their study, they have shown that the equivalence ratio is independent of strain rate for propane flame. So here, because we have used a LPG flame with 76% of propane, we considered this correlation and calculated equivalence ratio. So when we consider the premixed flame, we can see the equivalence ratio is uniformly distributed. Where we move to stratified flames, it has a equivalence ratio gradients. That is inhomogeneous mixture field. We can see that. So basically, this increase the flammability. It shows that the increase in flammability limit in stratified flames. Here contour shows the probability distribution of equivalence ratio for a low and medium swirl conditions. Again we can see compared to the premixed flames, all the stratified flames has a more equivalence ratio distributions. This tells us the flammability limit is increased in the stratified flame. Again, in the stratified flames, all the distributions are looking similar. So when we see the intensity contour, we have seen that the structure of the flame is more or like same. So here also we can see the equivalence ratio distribution also is similar for all stratified flames. Conclusion from this study is the spatial distribution of OV star and CE star are observed from the simultaneously captured OV star and CE star chemiluminescence images under low swirl and moderate swirl flow. The increase in swirl effect promotes the mixing of LPG and air. Therefore, the structure of the turbulent LPG air flames at premixed and stratified conditions is more compact than low swirl. The reaction zone located near the exit of the burner for medium swirl, which shows the delay in blow up, and the non-uniform equivalence ratio distribution is observed in stratified flames compared to the premixed flame. Some of the references are provided here. This work is supported by Department of Science and Technology, India. The authors grateful to the MHRD for research fellowship. Thank you.
Okay. So yeah. Audience, questions are invited from the audience. Okay, so maybe I can ask a question or two. So this we have yes. One of the present. Yeah, we have one of the authors here, right? Okay, so the swirlers that you have used in the setup. So based on what were those designs arrived at? So this 6 degree inclination, 24 degree, the 24 degrees.
Yes, sir.
Yes, go on, please.
Sorry, once again.
I think it's slide number 6, if I remember it correctly. The swirlers had some particular design, the angle of the blades and all. So I think it was 6 degree and some other angle, the two swirlers that were used.
We have used a clockwise direction swirlers.
Pardon?
You are asking the direction of the swirler, sir?
Not the direction, the design of the swirler. So you have when the blades are inclined at 6 degree in one swirler, and in the other swirler they are inclined at some other. So how do you decide on those angles there? What should be the dimensions in this of the swirler?
We need actually based on the swirl numbers, we design the swirlers. So we can get the swirl numbers with the diameter and the swirl angle. So we have used 35 and 40 degree to get a low and 30 and 45 degree to get a low and medium swirlers.
Okay, and
So we basically diameter
please go on.
and the swirl angles to get the swirl numbers.
Okay,
And
okay,
whatever we have used is the clockwise direction swirlers.
Sure, great. Yeah, Professor Anubhav Sinha has a question.
Yeah, I have a small question. So you have referred to the paper by Hardalupus group for calculating equivalence ratio.
Yes, sir. Yes, sir.
So can you, I have not seen that paper. Can you just comment on whether the conditions or what fuels were used and whether it is directly applicable to something like of your configuration?
The thing is here always the equivalence ratios depends on the strain rate. Whatever Hartlopus team they have come up with independent of the strain rate, this propane flame the local equivalence ratio is independent of the strain rate. That's what they have reported. So mine is LPG and considering 74% is propane. So I have taken that relation and just have applied that. Yes.
Okay, sorry. My question is that whether they have the similar type of structure or whether they are having a swirl flow. What type of configuration was used?
No, sir, their structure is different. They have done it for a pre-mixed flames.
Okay.
Okay.
Thank you.
So would the same correlation, would it be
Yes.
Would it be okay to use the same correlation for a different setup? Because it seems to be an empirical correlation which would be specific to a given case. So would it be okay to use it here? I think that's what Dr. Anu also wants to ask.
That is totally based on the intensity. Whatever they have done is like they have taken the chemiluminescence intensity. So that doesn't have to do anything with the configurations or something, but that have to do with the flame. So they have done it for a pre-mixed flame that I have taken the relation and used for my pre-mixed and as well as stratified. And whatever I have reported here is like I can't quantitative data directly, I can't take it, but I can just qualitatively tell how my local equal distribution is there all over my flames.
Okay.
Okay, thank you.
Okay. Yes. Yeah. Any other questions from the audience? Okay. Okay. So if there are no more questions, we can thank the speaker. Thank you. That was a good presentation. So let us move on to the next presentation. That's as per our schedule. So, okay. Yeah. So, okay, numerical simulation of liquid jet breakup. Libin Abraham et al. From SJCET Palai. Good. Yeah. So let's get started with the presentation.
Members, myself Libin Abraham. I'm just completed MTech from Department of Mechanical Engineering SJCET Palai, and I have done my MTech thesis from Propulsion Research and Studies Entity Liquid Propulsion System Center ISRO Trivandrum. This paper is on the topic of numerical simulation of liquid jet break and co-authored by Sharmista Chaubey and Justin Jones. Here is the outline: introduction, motivation, objective, numerical methodology, results and discussions, conclusion, acknowledgement, references. Here is the introduction. First one, atomization. The transformation of bulk liquid into sprays using atomizers or nozzles. The liquid jet of heat is disintegrated by the kinetic energy of the liquid or by the exposure to high velocity air or gas or by mechanical energy applied. Combustion of liquid fuels in diesel engines, spark ignition engines, gas turbines, rocket engines, etc. is dependent on effective atomization. Most of the atomization process occurs in cross-flow conditions. Here right side the figure shows that the injector nozzle, then spray formation region, and then spray region, liquid core, primary breakups, large liquid bodies, secondary breakups, then spherical droplets, droplet transport, then at the end the evaporation of the breakup process. Atomization of liquid jet in cross-flow has two parts. One is primary breakup and second one is secondary breakup. Then two distinct mechanisms for the jet primary breakup. One is column breakup and second one is surface breakup. In the surface breakup regime, liquid fragments such as ligaments and drops are separated from the jet surface. In the column breakup mechanism, the entire liquid jet undergoes disintegration into large liquid lumps. During the process of secondary breakup, ligaments and drops break up into small droplets. Here right side the figure shows that the Z direction, in Z axis there is a cross flow velocity UG and VG is in direction. There is a nozzle velocity, injection velocity, and the figure shows that the liquid jet went towards right side because of the cross flow from left side. And here is the liquid column, and then surface breakup, then ligaments and droplets spray to column breakup location. Then motivation. All engines of launch vehicles are extensively tested before being inducted into the flight. The flame deflector is cooled by injecting large quantity of water into the exhaust plume at various locations. Here right side figure shows that the rocket engine, and it is tested before inducted into the flight, and the various locations. Here is the schematic diagram of the testing region. Here is a nozzle inlet, and here the water is injected in various locations to avoid the melting of the concrete pit and wall. And then breakup of liquid jet into droplets determines many important parameters in combustion of fuels and spray cooling of various systems. And the jet breakup characteristics are usually determined by experimentally for specific applications, but experiments cannot be done for very large jets like those used for rocket engine test facilities. Moreover, only limited information can be obtained from experiments for the dense jet region where primary and secondary breakup occurs. Numerical modeling can be useful tool in understanding breakup process. First one is objective. The two model breakup of liquid jet in cross flow in ANSYS Fluent 2019 R1. Then to understand the feasibility of the interface tracking methodology and the complex interface evolution observed in the liquid jet in cross flows, and also providing useful observations regarding the physics like effect of liquid jet trajectory, breakup length involved in the breakup mechanism, which is a relatively different Weber number and momentum flux ratio. Then we have to DPM transition tool is used to determine breakup character. Here is the numerical methodology steps. First one is geometric modeling, then mesh generation, then setup and solution, results and post-processing. Geometric modeling is done in ANSYS design modeler, then mesh generation in ANSYS mesh, then setup and solution in ANSYS Fluent, then result and post-processing. There is a stepwise procedure in numerical methodology. Here, cut cell mesh is used for minimize the blended eddy simulation turbulence model. Then post-process in DPM spray. Then set up animation sequencing and here is the geometry of jet in cross flow. Here is the geometry, and from left side here is the air cross flow, and from the air cross flow wall 2 millimeter nozzle for liquid jet, and the dimension is 6 into 2 mm. Momentum flux ratio according to the case 1 14 and Weber number 119 and Reynolds number 10923, and case 2 velocity is 534, momentum flux ratio 18 19, and water jet velocity 22, cross flow velocity 123, and momentum flux ratio 26 and 255. Then water jet velocity 19, 28, and momentum flux ratio 374 and 30. Here bottom table shows that the parameters used in simulation. There is a temperature, liquid density, or are explained in this table. And then result and discussions from Fluent. We will get the visualization of the liquid jet, and here is a liquid jet trajectory, primary breakup, and here from the cross flow is here, and here is the liquid jet from the bottom. And in the first case there is a momentum flux ratio 14 and Weber number cross flow is 190, and in case 2 the momentum flux ratio 18, Weber number cross flow is 19. And here is the secondary breakup is avoided. It shows only the primary breakup. And the third case is Weber momentum flux ratio is 26 and Weber number cross flow is 255. And case 4 the momentum flux ratio 374 and Weber number cross flow is 13. Here is no breakup because it is heated top of the geometry. And after I will explain. Here is the animation, this sequence of sample of primary breakup and secondary breakup. Here is a liquid jet core, and then it disintegrates into ligaments and breakup regions. And from left side there is a cross flow is here. It is the case 3. Then here is the case 4. It hit top of the geometry. There is no breakup is we cannot see. It is the figure, the trace of liquid jet. In x-axis there is a lateral direction and y-axis axial direction of liquid jet. Here is a case 1, case 2, case 3 and case 4. From this we can get the jet deformation occurred due to the momentum exchange between liquid and gas particles. The liquid jet bend in the direction of cross flow. From the all 4 cases, momentum flux ratio 14, 18, 26 and 374 respectively, which gives clarification of relation between momentum flux ratio and jet penetration. Then increasing momentum flux ratio generally increases jet penetration deeper into the top. Then we will get the second observation, liquid jet breakup length. Here the figure shows the axial direction and lateral direction. In axial direction there is a cross flow velocity. In lateral direction there is a liquid jet velocity. Here the column breakup point, the first point breakup point. Then in y-axis there is a column breakup height, and then z-axis there is a column breakup distance. Column breakup in this figure from we can get the column breakup distance 5.2, column breakup height 8 mm. And then second figure we will get the column breakup distance 2.1, column breakup height 8.5, and column breakup distance 3.5 and column breakup height mm. And here is no breakup because it top of the geometry. And then we will get the observation. Figure shows the diagram of liquid jet breakup in YZ coordinate. From these figures we get column breakup height is mostly related to non-dimensional number momentum flux ratio. Momentum flux ratio of case ABC are 14, 18, 26 respectively, and also column breakup height is 8 mm, 8.5 mm, 10 mm. Similarity results illustrated that the column breakup height is directly proportional to momentum flux ratio Q. Then momentum flux ratio increases, column breakup height also increases. Here D is provisional as further studies are needed to be conducted to completely understand the breakup phenomenon. Then the conclusion. This study was done basically to understand the feasibility of the interface tracking methodology to handle the complex interface evolution observed in the liquid jet in cross flows. Then a numerical investigation on 3-dimensional confined jet in cross flow is carried out. Breakup position of the jet column mainly depends on the relationship between the air momentum and liquid jet momentum, which is called the momentum flux ratio. Increasing momentum flux ratio generally increases the jet penetration deeper into the domain. Column breakup height is directly proportional to momentum flux ratio Q, which means momentum flux ratio increases, column breakup height also increases. Here is the reference. Thank you.
Okay, so questions are invited from the audience. Yes. So what turbulence models were adopted for this simulation? Okay. Am I audible? Do we have anyone of the authors to answer questions? Hello?
Yes, you are audible.
Okay, okay. Yeah. Yeah, so do we have questions from the audience? Yeah, if not, I just put the question. So what are the turbulence models that were used? Yeah. So Professor Anubhav Sinha is there. Professor, you can ask your question.
Yeah, I wanted to know about case 3. They have shown a video. So generally for what is the Weber number, and for that range that they have mentioned, we generally see something called back breakup that I don't see in that video. So can they comment on what model was used and why we don't see back breakup in that particular video?
Oh, yeah, that's a valid question. Yeah, do we have anyone from the authors? Hello? Probably don't have any of the authors here.
Okay, thanks.
Okay. Okay. So if that is the case, I think the appropriate thing to do would be to move on to the next presentation. Okay. So right. So we have a team from IIT Madras to talk about crosswind flow and intake aerodynamics. Yeah. Please play the presentation.
Hello everyone, I'm Sumit Sarvankar from Department of Aerospace Engineering, IIT Madras, and I'm going to talk about the effect of crosswind flow on intake aerodynamics. A brief overview is shown here. At first, we are going to talk about the motivation for studying crosswinds. Then we move on to discuss about quasi-3D duct, mesh generator, boundary conditions, and the solver used. Later, we will discuss about the validation and some parametric studies based on the effect of Reynolds number and mass flow rate through the main exit and spill exit. We'll also discuss the sensitivity of turbulence models. Finally, we conclude the key observations from the study. At first, let us throw some insights into the motivation of the study. Let's look at the typical turbofan engine. The purpose of an intake is to supply smooth air to the engine. The PIV image of an intake shows how the turbulent structures in the flow are killed as it enters the intake. With the increasing demand for high efficiency and fuel efficient aircraft, the trend is shifting towards high bypass and low fan pressure ratio engines. As a consequence, the intake diameter has become larger. Larger intakes have larger wetted area, which results in additional drag. In order to compensate for the weight and drag penalties, shorter intake with slimmer lips have been used. However, an intake with slimmer lips is more prone to flow separation at off-design conditions due to high incidence, ground vortex ingestion, and strong crosswinds. Several investigations have addressed the effect of these off-design conditions. In this study, we are going to focus on the crosswinds flow. Let us go through the numerical setup used in the study to simulate the flow under crosswinds. In order to model crosswinds, the quasi 3D duct is extracted from a full 3D engine simulation. The streamlines are released from the fan face and are tracked till the inlet. The figure shows a 20-degree sector rig extracted with the help of 2 spinner lines, 2 intake lines, and 2 midlines. A recent study by Young et al. Suggests quasi 3D simulations are economical, and it is 50 times faster than a full 3D engine simulation. A figure on the right bottom corner shows the experimental setup conducted by Wakelam. The current study is based on the 90-degree sector rig with an additional spill exit, which is incorporated to bleed a desirable amount of mass flow from the inlet and to allow the development of a fresh boundary layer formation on the intake lip, as it occurs on a real engine. Pressure inlet and pressure outlet conditions are used at inlet and both the outlets. The inlet is maintained at atmospheric conditions with turbulence intensity of 5% and turbulent viscosity ratio is 10. For the baseline case, static pressure at the main exit is 90,300 Pascal and that of spill exit is 92,500 Pascal. Further, these conditions are varied to carry out parametric studies. Reynolds number for the baseline case is 310,000, which is also varied to study the effects of Reynolds number on the flow field. The computational domain is discretized using a structured mesh comprising of 2.4 million cells, of which about 1.8 million grid points are clustered within the C mesh around the intake. The average Y plus value is 1.136 around the intake lip and is good enough to capture the viscous effects within the flow. The sensitivity of the turbulence models is tested. It will be shown in the subsequent slide that K omega SST model is found to be accurate for a wide range of mass flow rates passing through the engine. The simulations were carried out using the commercial software ANSYS Fluent 18.1 version. Let's discuss the results obtained in the current study. We will start with the validation for the baseline case. The baseline case is validated by comparing 3 key parameters against the experimental data. First is ISM, isentropic Mach number, and is given by the relation as shown. The variation of the ISM over the intake lip along the streamwise direction were obtained using K omega SST and SA model. The plot suggests both the turbulence models are in good agreement with the experimental data. However, K omega SST is more accurate in predicting the ISM peak. Further, grid sensitivity is analyzed using the K omega SST model by doubling the number of grid points in the circumferential direction. The results obtained using both these meshes are in good agreement with the measurements. Hence, 2.4 million mesh size was chosen to report the parametric studies. Another key parameter is the normalized pressure in the radial direction across the fan face. The fan face is at x equals to 0 and the radial profile across which gives us the pressure distribution. It can be seen from the p-norm plot that both the turbulence models gives us consistent results with marginal difference. Furthermore, the p-norm distribution obtained for different meshes overlaps. The third key parameter is the axial variation of the acceleration parameter on the windward side of the intake lip. In the plot, the experimental data and threshold for relaminarization are overlaid for comparison. From the figure, it can be seen that the baseline case attained relaminarization, which is consistent with the experiments. Also, the acceleration over the intake is an order of magnitude higher than the threshold value for relaminarization. Hence, it is difficult to control the flow over the intake by enhancing turbulence on the windward side of the lip. After validating the baseline case, let's move on to some parametric studies. First of all, let's discuss the effect of Reynolds number. The Reynolds number of the flow is varied by changing the reference molecular viscosity in the Sutherland's law. At fan phase, contour plots are obtained for two different Reynolds numbers. We observe that higher value of Reynolds number promotes attached flow, as it is evident from the contours that high Reynolds number flow remains undistorted at the fan phase. In the radial direction, pressure distribution is plotted and the relevant experimental data compared. We observed attached case agrees well with the experiment, however discrepancy was observed for the separated case. This can be attributed to the well-known deficiency of Rand's model to predict largely separated flows. Moving on to the next parametric study, effect of main exit pressure. The flow physics of the problem is mainly dependent on the mass flow rate passing through the engine, which can be controlled by varying main exit pressure conditions. The distortion level varies with the mass flow rate and can be calculated using distortion coefficient. Here P naught bar and P bar are area weighted average stagnation pressure and static pressure at the fan face, and P naught inlet is the inlet stagnation pressure. In the line plot shown, we see the variation of distortion coefficient with the mass flow rate at the fan face. Let's take a look at the pressure contours at the fan face. For low mass flow rate, the flow separates due to adverse pressure gradient. With increase in the mass flow, the flow remains attached for the intermediate range. With further increase in the mass flow rate, a strong shock is encountered at the leading edge of the intake lip and flow separates downstream. Taking radial profile of normalized pressure shows that the stagnation pressure loss due to the low speed separation is larger than that of shock-induced separation. On the other hand, stagnation pressure loss is minimal for the attached flow. To conclude, three different flow regimes are identified: low speed separation, intermediate attached flow, and high speed separation. For the same three cases mentioned earlier, let's take a look at the Mach number contour at z equals to 0 plane. For examining the Mach number contours, we can clearly observe the distortion levels with the help of streamlines overlaid. The low speed separated flows encountered large circulation zone than the shock induced separation. Further, if we observe ISM in the streamwise direction for these three cases, we see highest ISM peak is achieved for high speed flows where the intake lip reaches transonic speeds. On the other hand, peak significantly drops for low speed flows. Let's move on to the discussion on the effect of spill pressure. The mass flow through spill can be controlled by varying the spill pressure. As the mass flow through spill decreases, the stagnation point moves towards the spill, as a result of which additional favorable pressure gradient accelerates the flow, which can be useful in suppressing inlet flow separation. However, by comparing the two contours corresponding to spill pressure 40,000 Pascal and 92,500 Pascal, we only observe a marginal shift in the stagnation point and the minimal effect on the flow physics. Now we proceed on to the sensitivity of turbulence model. Let's discuss the sensitivity of the turbulence models for low speed separation. We tested SA with curvature correction, and K omega SST models. We found that the conventional SA model failed to predict low speed separation. However, SA with curvature correction and K omega SST models gave us consistent observations. That is, both predicted the low speed separation effectively, as it is evident from the contours and p-norm plots. Now we move on to the key observations from our study. To conclude, we performed economic computations using quasi 3D duct and validated with the experiments. We also observed the evident nature that higher value of Reynolds number promotes attached flow. While varying the mass flow rate through the engine, we identified three different flow regimes. We observed low speed separation for low mass flow rates due to the adverse pressure gradient. Then we also observed the distorted flow due to the high speed shock induced separation. However, the flow attaches at intermediate mass flow rates. By varying spill pressure, we only observe the marginal shift in the stagnation point on the windward side of the lip. We found SA model failed to predict low speed separation. However, SA with curvature correction and K omega SST model can be used for a wide range of mass flow rates. We thank FMFP organizing committee for giving us this opportunity to present our work.
Okay. Yeah, questions from the audience. Please go ahead. Okay. So can you please elaborate a little bit on what do you exactly mean by quasi 3D? So we have a 2D simulation, but then what exactly is done with the third dimension there?
Okay. So actually, if we go to one of the previous slide, there we have seen that this the duct is extracted from a full 3D engine simulation. So in those terms, we can extract a lip rig, which is good for low speed separation, or we can extract a sector from the whole engine.
Yes.
So though that we are referring to as quasi 3D duct, which is extracted from a full 3D engine.
Okay. So, but in the sense of simulation, it's a 2D simulation then.
No, sir. We are trying to capture 3D effects just by using the sector. So if we are taking a slice, that will be 2D. But since we are taking the sector to incorporate the effect of 3D effects.
Okay. So it's not a full 3D simulation of the engine, but you are solving the Navier-Stokes equation in 3D only.
Yes, sir. So those streamlines which were extracted gave us the quasi 3D duct.
Okay. Yeah. Yeah, floor is still open for audience if anyone wants to ask questions.
I have a question on that isentropic Mach number. We say that it is a Mach number without losses, right? Hello.
Yes.
Please go on.
Yeah. So so how it is essentially bringing out the relation for various mass flow rates and that is at low speed and high speed, because you chose that as a parameter. What was the motivation for choosing that? Because I believe losses will be more and the pressure ratio would be falling down.
Yes. So we took the isentropic Mach number on the over the intake. So by plotting that, we can see for high speed flows, we see the ISM peak achieved was quite higher than that of the low speed separation. So that peak drops at the towards the leading edge. So we can get an estimation if we are varying the mass flow rate. We can plot various plots of the ISM, and also we have validated the baseline case. So that was also matching well with the experiments. So yeah, to conclude, we can say if you are plotting the ISM for various mass flow rate, you can see how what are the peak you are getting, and the trend is giving us the right observations or not.
Okay, so what parameter you could suggest if I have to go for more actual case, looking up with losses, because I believe that is the major thing in intake parameters.
Yes, so we must have seen that pressure norm distribution, which tells us the stagnation pressure losses and if there is a separation or not. That can be a key parameter to understand how is the flow behaving at the fan phase. Also, there is one acceleration parameter which we also mentioned and matched with the experiment. So from that plot, we can say if the flow is getting relaminerized or not. So those can be the few parameters. And to match, we have experiments or CFD data from the earlier results by Vikram.
Okay, thanks.
Yeah, if there are no more questions, we can move on to the next presentation. Thank you. Let's thank the speaker. Yes. So from space propulsion to aerodynamics, now we move on to IC engines. First such paper in the series, and okay, this is from the home team. Okay, so let us see what they have to say on fuel substitutes for biodiesel for diesel. Yeah, please play the presentation.
Hello friend, this is Ganesh Gowde from NIT Warangal, working under the guidance of Dr. Jinnaga Srinivaslu. Today I am going to present on Impact of biodiesel blend as a fuel substitute for diesel on methanol dual fuel SCCI engine performance. This is the overview of my presentation. The basic working principle of SCCI engine is the combination of SI and CI engine. Outside the combustion chamber, there is a lean homogeneous charge prepared passes into the combustion chamber. Due to the compression, that homogeneous charge got compressed low. Suddenly its temperature and pressure got increased low. It reaches to its autoignition temperature and then spontaneous combustion may happen. Due to that, power stroke and simultaneous exhaust stroke will get. Here is a lean homogeneous charge mixture is used. That's why the combustion temperature is very low. Due to that, NOx emission of the SCCI engine is very low. Again, SCCI engine having a homogeneous mixture, so soot emission will reduce. SCCI engine can operate at more than the 15 compression ratio, and the thermal efficiency of this engine is more than the SI engine. This SCCI engine having fuel flexibility, we can use any fuel into the SCCI engine. Here is no throttle losses, so it may impact on improving the thermal efficiency. SCCI engine having some disadvantage, like as this engine getting difficulty to start in cold condition. This engine is not able to control the combustion. Whenever the load increases, then fuel rate also increases. So pressure rise rate and heat release rate will be more with the increasing load. So here no control on the combustion. This is the major problem of this SCCI engine. This whole combustion is happening at low temperature. So CO and SC emission is more for SCCI engine. Some researchers overcome these challenges by using some methods. Like a cold start capability, they improved by using a glow plugs, or they can start the engine at a spark ignition mode and then shift to the SCCI mode. Then extending the operating range of engine, they use a dual fuel mode operation. Some use the fuel blending, some use the VCR engine or EGR mechanism like this. SC and CO emission, they controlled by the catalytic converters. But the main problem of this SCCI engine is to extending the operating range or to run the engine at high load condition. For this, some researchers use a dual fuel mode engine, means two different fuel having a two different auto ignition temperature, so they can easily run at every load condition or high load condition. So like this, Mahala and its co-researchers use a dual mode combustion engine. In this they use the biogas and diesel. Biogas they delivered with the inlet air, and diesel they injected at the end of compression stroke. In this they got a low NOx and soot emission, but there is a high CO and SC emission occurred. Then Junior perform experiment on ethanol diesel dual fuel SCCI engine. In this they reduce a 60% NOx emission, but here also SC and CO emission got increased. Benages also run the engine. They use RCCI engine mode. They use the gasoline and diesel fuel. They perform the experiment at 25 load conditions, and they got the Euro norm 6 emissions, like as a NOx and soot emission got reduced very drastically. Then Pedala and co-researcher also used dual mode SCCI engine. They used ethanol and diesel. Here 60% ethanol fraction was allowed, because after that if we increase the more than 60 ethanol fraction, then misfiring may be happen. So here they use up to 60% ethanol fraction. Then Lee et al. Used a dual mode combustion. They use a natural gas and diesel with the EGR. So Kaveri suggested that RCCI, means reactivity control compression ignition, is the best combustion to control the combustion and to extend the load condition. So from this we find some research gap. Dual fuel SCCI engine is the best combustion mode to extend the load limit of SCCI engine. But here is a SC and CO emission will be more. but various researchers suggested that biodiesel blend can reduce the SC and CO emissions. Also, very little literature is available on biodiesel blend instead of diesel in methanol dual fuel SCCA engine for the reduction of SC and CO emissions. A very few researchers have studied comparative study of methanol with diesel and methanol with the biodiesel dual fuel SCCA engine performance. So by understanding this research gap, we decided to run the engine on methanol with diesel or methanol with biodiesel. So to convert the SCCA engine, we select the single cylinder Kirloskar engine, which having a 3.5 kilowatt power. Constant RPM engine we selected, and we used a carburetor to prepare a homogeneous charge. So this is the schematic diagram of our dual fuel SCCA mode engine. Methanol is passed through the carburetor. In the carburetor, inlet air and methanol got mixed. Homogeneous mixture is prepared. That mixture passes into the cylinder, and at the end of the compression stroke, diesel or biodiesel will inject. To measure the exhaust gases, exhaust emissions, we use a 5-gas analyzer, and to measure the smoke opacity, smoke meter is used. Here, load is controlled by the dynamometer, and total engine is a computerized engine. That PV data is recorded into the computer, and according to that, the heat release rate, pressure rise rate, P theta diagram is all graph we will get. Then to prepare the homogeneous charge, this is a 500 cc Royal Enfield Micar VM 28 carburetor was used, which having a constant mass flow rate of a methanol fuel here. Here we use a Z60 for supplying the constant mass flow rate of methanol, that is 0.588 kilogram per hour. So before going through the experimentation, we find out the accuracies and uncertainty of our measured parameters. Then some fuel properties also measured. This is a result and discussion. In this result and discussion, methanol with diesel, methanol with biodiesel, and conventional diesel engine is compared. Here, the methanol with diesel having more ignition delay, because methanol having a high auto ignition temperature, it extending the start of combustion point. But if you use the biodiesel instead of diesel, then the inherent oxygen of biodiesel will promote the combustion and reduce the ignition delay. As we can see into the figures 2, that ignition delay is reduced, so that pressure curve is shifted towards the TDC. But in figure 3, the pressure rise rate, we observed that pressure rise rate is not high in the case of methanol with diesel or methanol with the biodiesel. Means pressure rise rate and heat release rate is in control, means there is no chance of the knocking. Figure 5 mentioned that ignition delay and combustion duration. Ignition delay, we can say that methanol with the biodiesel reduced compared to the methanol with diesel, because biodiesel having oxygen which is promoting the combustion, so it is reducing, means early start of combustion may happen into the methanol with methanol with biodiesel dual fuel SCCA engine. But combustion duration of both engine is reduced compared to the conventional diesel engine. SC and CO emission is reduced a lot in the case of methanol with biodiesel compared to methanol with diesel, because SC will immediately combine with the oxygen and it will convert to H2O, and CO, if combined with the oxygen, it will convert to CO2. Hence the CO and SC emission will reduce in the case of methanol with biodiesel. The smoke opacity also reduces in the case of methanol with biodiesel. But in terms of NOx emission is a little more compared to the methanol with diesel. for methanol with biodiesel. Brake thermal efficiency got improved for methanol with biodiesel dual fuel SCCA engine. This overall performance we can see into the figure 9 that overall performance CO, SC and smoke emission got reduced for methanol with biodiesel by percentage. We calculated by percentage. Positive value mentions the reduction, negative value mentions the increased value. Means CO, SC and smoke emission got reduced compared to the methanol with diesel dual fuel SCCA engine. But NOx emission got increased in the case of methanol with biodiesel. So this is the overall conclusion of our presentation, that methanol with biodiesel reduces the methanol with diesel or biodiesel reduces the inlet steam cylinder pressure rise rate and heat release rate. There is a drop of NOx and smoke opacity compared to the conventional diesel engine. But it revealed that methanol with diesel was given the lowest NOx compared to the methanol with biodiesel and pure diesel mode engine. Smoke opacity in the EM100 with diesel was more compared to the EM100 with biodiesel because methanol has a high latent heat of vaporizing. It reduces more inlet gas temperature and initiates the incomplete combustion, which assists to produce the more smoke opacity. So like this, methanol with biodiesel giving a overall good performance compared to the methanol with diesel. These are the references which we referred.
Okay. Yeah, so this is a popular topic, IC engine fuel blends. We would expect to have some questions from the audience here. So, yes. Yeah, please go ahead. Yes. Oh. I can see a raised hand there. Ganesh Gavle, you are the presenter itself, right? Yeah. The floor is now open for the audience to ask questions. Okay. So here, if we talk about this methanol fuel blend causing incomplete combustion, what would one say about carbon monoxide here? So NOx was analyzed. Overall combustion delays and efficiencies were looked at, but what about CO emission?
Hello?
Yes.
Sir, Ganesh is here.
Yeah, please go on.
Sir, please ask again because my network lost.
Okay. So what I was asking is, we have looked at efficiencies, NOx emissions, ignition delays, but what about CO? Because if as per what is surmised, addition of methanol additive is going to give going to cause incomplete combustion, then it's probable that the CO in combustion products might go up. So
yes, sir. In the case of methanol with diesel, means methanol for port injection, means through the carburetor and diesel. That in that case, the CO and SC will be high. Okay, but hello.
Yeah, go on.
Am I audible?
Yes, yes.
But if you substitute instead of diesel, biodiesel, means NIM biodiesel we use there. So in that case, there is a variation. Means CO and SC will reduce because again, methanol having some more latent heat of vaporization. So it is producing incomplete combustion there. But if you are injecting the biodiesel now, that time it is increasing somewhat combustion temperature and it is reducing CO and SCL.
Yeah, but then how do you compare the other performance parameters for biodiesel with respect to, say, normal diesel?
Normal diesel means conventional means actually we run the engine on conventional diesel mode.
Then we convert that engine into the SCCI mode.
HCCI, yes.
Dual fuel SCCI mode. So in that two type experiment we did. First of all, we did the methanol with diesel. Means to ignite the homogeneous charge, we injected the diesel. Okay, this one set of experiment we did, and later instead of diesel we substituted biodiesel B20, biodiesel 20. Okay, that time somewhat performance improved compared to the methanol with diesel.
Okay. Okay. Any more questions from the audience? Okay, if that is the case, then now we thank the speaker, and I think we have come to the end of this session, right?
Yes, sir. This was the
Yeah. So thanks to the speakers for sending in their papers, sending in their videos. Thanks to the conference organizers for arranging everything. So thank you very much, and we come here. We come to the close of this session. Thanks.
Thank you, Professor Kumbhakarna, for sharing this session. So
thanks.
with this,
my pleasure.
We have come towards the end of today's presentation session in Hall 1. Thank you, the audience, for joining all the sessions. We will meet tomorrow again. Thank you.
Okay. Yeah.
Thank you.
Good night.